this video, you will learn how to create 5 games in Python. And while doing it, we will touch on all the major parts of the language. We will cover classes and inheritance, dunder statements, working with lots of files, storing permanent data. We'll even cover decorators and multiple inheritance. On top of that, you will also learn how to organize and manage larger projects. Via that, you will go very quickly from a beginner to a more confident and advanced coder. And you get to do all of it while shooting at skeletons. In terms of requirements, I do expect you to know the basics of Python, like using functions and different data types, and you should have at least once created a class yourself. If you don't know what any of that means, check out my introduction to Python. And if you want to take your knowledge to the next level, check out this video's sponsor, brilliant.org. They offer courses on a broad range of subjects, like math, data science, and software development. For every subject, you can start from scratch or jump straight into a course. Either way, you will get to a competent level fast. That is because all lessons are highly interactive and engage you in a hands-on way from the start. Not only is this a fun way to learn, it's also great at getting you to develop problem-solving skills and understanding underlying principles. You can access Brilliant from your computer or via an app. It's super accessible. So instead of wasting your time on TikTok or Twitter, you can build a powerful habit that will make you a more competent person. Brilliant also keeps on adding new content. Just recently, they added a section on Python and expanded their AI courses. So check it out at brilliant.org/clearcode. You will get a 20% discount, and the first 30 days are free, so not much to lose. Alright, to get started with game development, we need to go over some basics. And don't worry, this won't take long. In the most basic sense, video games function like movies. You simply draw one image after another, and then you play some sound. The only difference is that video games dynamically generate each image. So while a movie like the first Lord of the Rings has 260,000 frames that never change, a game like Super Mario can generate infinite frames and draw each individual one dynamically, depending on things like player input and enemy movement. But that's basically it. Usually games run at 60 frames per second, and on each frame, the game first checks some basic things, like player input, timers, enemy movement, or item interactions. Once it has that information, it calculates where things need to be. And once that is done, it draws a frame. Doing this over and over again will get you a video game. To implement all of that, we will use pygame, Python's default game framework. Although pygame doesn't actually do that much. Primarily, it allows you to draw images and play sounds, get user input, and then get and set the positions of objects. There are a few more things that pygame does beyond that, but those are just add-ons to make your life a bit easier. The advantage of that approach is that pygame is really easy to learn. We will cover all of the basics in the first game. The downside is that you cannot rely on pre-made tools that you would expect in a game engine like Godot or Unity. Those have fancy parts like physics engines or network management. Although this isn't necessarily a downside, since you are forced to build your own components, you get much more practice at problem solving than a game engine user. And if you want to do something else, like data science or AI, you can switch much more easily. And those fields have better salaries and nicer work environments. You really want to keep your options open. Because of that, especially when you are getting started, I would always recommend to start with a really basic tool, like pygame, and then switch to a proper engine later on. That being said, if you want to jump straight into a game engine, check out my introduction to Godot 4. Anyway, let's go a bit deeper into pygame. The two most important concepts that you need to learn are surfaces and rectangles, or rects in short. Surfaces are just images. It could be an imported file or some text. Although it could also be an entire window. Basically, for every pygame project, you create a special surface that serves as the window. This is called the display surface, and on that you place other surfaces. The other concept is a rect, and that one is supposed to wrap around a surface and then place it in a specific position. Via those rectangles, you also get collisions. If you then add some basic input, you are already close to a game. The one last thing that we need is to keep on drawing new frames. For that, we are using a simple while true loop. Inside of it, we get the user input and calculate where game objects need to be. And from all of that, we are drawing a new frame. This we do over and over again, until the player gets defeated or wants to quit. And that is all you need for the basic theory. Just 2 more things before we get started. Number 1, you need to install Pygame. However, if you look online, you can find 2 versions of Pygame. Pygame itself and Pygame CE. Short for Community Edition. The version that you want to use is Pygame CE. This one is more modern, has more features, and is more efficient. It is also the only version that is actively worked on. The original Pygame is basically abandoned at this point. You shouldn't use it anymore. That being said, Pygame CE is backwards compatible with Pygame. If you have that one installed and you find an old Pygame project, you can run it just fine. To install it on Windows, you either open the PowerShell or the terminal and then type pip install pygame-ce. On macOS, you open the terminal and type pip3 install pygame-ce. That brings us to the second part. You will have to download some resources. If you look at the video description, you can find a link to a GitHub page with all of the project resources. Download those to get the graphics and the audio files. There's also a Google Drive link in which you can find the code for each chapter and the final games. With that, we are ready to go. And the first game will be the Space Shooter. Via that, we are going to cover all the basic concepts. You can find all the files in the folder Space Shooter. And the first thing that we have to cover is how to create a basic window. This part isn't going to be terribly exciting, but it is going to be the starting point for basically everything else. So we are going to create a window, we're going to give it a custom title, and we are going to fill it with a background color. After we have that, we can work on the finer details. But first of all, we have to cover some basic groundwork. And there are 2 concepts you have to understand to get started. The first one is the display surface. This is the main canvas that we are going to be drawing on. Or in other words, this will be the window for the game. And inside of this window, we will display everything else. Also, we can only ever have a single display surface. Besides that, we are going to need an event loop, which is going to check all of the events. These events could be keyboard, mouse, or controller input, or it could be timers. On top of that, it could also be UI interactions. For example, if you want to press X to close a window, this would also be an event. So we have to capture that if we want to be able to close our game. Something that is really fundamental, so we have to cover it right away. In fact, what I would recommend before you are even starting to code is to open the documentation. If you go to the Pygame CE website, you can go to documentation, and there you see a link to every important topic of Pygame, along with a quick start guide and a few more tutorials. Being able to read this website is incredibly important to understand Pygame. So ideally have this thing open on the side while you code along. Also, what you can see is a quick start guide. We are going to create something fairly similar in this section, although it's going to be a bit simpler. Here I am in the code editor, and inside of the project, you can see the folders I talked about earlier. We have a couple of images, we have a couple of audio files, and inside of the code folder, there's nothing at the moment. Now for this project, I only want to have a single Python file that I am going to call main.py. Later on, we will work with multiple Python files, but that's not an issue for now. Now the first thing that you have to do to use Pygame is to import it, which you do with import pygame. And after you have written this line, run the code, and you should be seeing your Pygame version, your SDL version, and your Python version. If you are getting an error message at this point, something went wrong with the import, so check that. After we have that, you want to do a general setup, which first of all means that we have to run pygame.init. This initializes Pygame and is really important for everything to run properly. That being said, you don't have to worry about the fine details that much. Just make sure that you are always including it. After we have that, we want to create a display surface that we also want to store inside of a variable. Now for the name, very often you are seeing screen, although I prefer to call it display surface because that's a bit more descriptive, but both are totally fine. we will need pygame.display.set_mode, along with a tuple that defines the width and the height of this window. These two numbers you usually create inside of separate variables to access them later on. In my case, I want to create a window width and a window height variable. I want to go with 1280 by 720. And then copy those two numbers and paste them into the tuple. And with that, we are creating a window. If I now run the code, we can see a window for a very short amount of time. And that is the intended experience. What is happening now is that we are importing pygame, we are initializing it, and then we are creating a window. But after that, the code is ending, hence everything disappears, including the window. Because of that, we can only see the window for a fraction of a second. To fix that, we have to make sure that this code runs forever, or at least until we want to close it intentionally, which we are going to do via a while loop. And for now, I'm going to set this to while true. That way, if I add the pass in there and run the code again, we can see the window forever. However, if I now try to close it, nothing is going to happen. Or, well, the game crashes. So I want to close all of this, and then add just a bit more code. Inside of this while true loop, we have to do two things. Number one is the event loop. Once we have that, we can actually close the game. Besides that, I want to draw the game. I don't think I have to explain this part. First of all though, for the event loop, we can get all of the events with pygame.event.get. And to access all of them, we will use a for loop for event in pygame.event.get. In there, we can check for keyboard input, for mouse input, for timers, and for UI interactions. Or in other words, we can check if the user wants to close the game, which we can check via the type of the event. If event.type is equal to pygame dot, all in uppercase letters, quit. That is a constant that stands for closing the game, which we are going to do via another variable called running, which by default is going to be true. And then for this while loop, we're going to set this to while running. And if the if statement triggers, we will set running to false. If I now run all of this again, I can close the game, and we are closing everything. There's no more error message, so this looks pretty good. Although there's one thing you should always do after this while loop, and that is pygame.quit. This method is essentially the opposite of pygame.init, meaning it uninitializes everything, so we are making sure we are closing the game properly. Most of the time, if you forget this one, it's not going to be causing too many issues, but sometimes it can cause a bug or at least weird behavior. So make sure to include it. And this would be the most common way for a very basic pygame setup, which means after that, we want to draw the elements of the game. And for that, we always have to call one method, which is called pygame.display.update or flip. Both methods do the same thing. They take all of the elements that we have run in the while loop before and then draw them on the display surface. The difference between them is that update updates the entire window, while for flip, you can specify that you only want to update a part of the window, which in most cases you don't really want to do. So I usually use update by default. That one is a bit simpler, but both are totally fine. So then, what can we do to draw the game? And for now, let's say I want to fill the window with a red color. How can we do that? For that, you want to look at the documentation. So far, we only really worked inside of pygame. So in there, we have called pygame.init and pygame.quit. Besides that, we have looked at pygame.display, and in there, we had set mode, which does a whole bunch of things. The return value of this is going to be a surface. And if you go all the way to the top, there we have another section called surface. So if you click on that, you can see all of the methods available for a surface. And the one that we care about at the moment is pygame.surface.fill. Click on that, and then you can call fill along with a color. You could specify a few more arguments, but we don't really care about that. Which means, back inside of pygame, I can get rid of the comment and then get the display surface along with the fill method. In there, we will need a color value. And the easiest way to get colors in pygame is the name of a color. For example, red. If you now run the code, this feels a bit intense, but we are getting a red color. So that is working really well. You could also use blue in there. There are a whole bunch of colors you could be going with. To get all of the available colors inside of the pygame documentation, you want to go to color, and there, if you scroll down just a bit, you can see the name colors. So click on that, and then you get a pretty long list of all of the colors you could be using here. This list is quite extensive. But anyway, with that, we have a pretty good starting point for pygame. And to finish off this part, let's do an exercise. I want you guys to read the documentation and change the title of the window. And as a reminder, here's a link to the documentation. Pause the video now and try to figure this one out on your own. If I run the code again, and if you look in the top left, you can see that our window title is pygame window at the moment. And we also have the icon of pygame. The icon I am going to keep, but the title we do want to change. How could we do that? For that, you want to look at the documentation, and this part is under display. There we have already used set mode. And if you scroll down a bit, we also have set caption, this one. Set the current window caption. To use it, all you really have to do is call pygame.display.setCaption and then insert some kind of string. Which means, back inside of the code, after we are creating the display surface, I want to call pygame.display and then set caption. For this one, we are going to need some kind of string. Let's call this one the space shooter. If I now run all of this again, in the top left, you can see that our title has changed to space shooter. Perfect. So with that, we have finished the first part of pygame. Although you might have a question. If you look at the documentation, how could you know that changing the title of the window was inside of display? And well, sometimes in documentation, you simply have to look around to find the right answer. Pygame ultimately doesn't have that many components, so if you know a little bit, you should usually have a good idea of where stuff is. That being said, you can use Google quite easily. For example, if you look to how to change pygame window title, then you find a whole bunch of answers. So if you click on the first one, they get pygame.display.setCaption, along with a string, so should be fairly straightforward. Alternatively, you could also use ChatGPT. If you look for how to change pygame window title, you should be getting a pretty decent answer. There you go, this worked pretty well. Although for a bit of caution, when you're using an AI tool, the answers can be wrong or at least incomplete. So don't expect anything great from it, but for very simple questions, it can be really good. Anyway, with that, we have a basic window. So now we can start drawing our game. The next important part is displaying graphics. And by the end of this section, we will display an imported image and a generic plain rectangle. On top of that, we will also be able to move things in a very basic way. Although that, for now, will be fairly experimental. Now, there are two ways to display graphics in pygame. Number one, you could show an image or a text via a surface. And number two, you could draw pixels straight away. Using a surface is the most common way, and this is what I'm going to focus on in this section. Although later on, we are also going to draw pixels straight away. But for now, the topic that we have to focus on is a surface, which can display an image or a text. Usually, a surface in pygame is just an image, so a PNG or a JPEG. There are lots of supported file formats, a plain area, or some rendered text. Or in other words, if you want to create a surface, you can either create a plain surface with pygame.surface, and then you specify a width and a height inside of a tuple. Besides that, you can import a surface. This happens with pygame.image.load, and then you specify a file path to some kind of JPEG or PNG file. Finally, if you want to have a text surface, you would need a font, and then you render that font. If you want to anti-alias the text and the color that you want for that text. The text for now isn't too important, I'll cover that later, but we will create a plain surface and import an image and create a surface that way. Before that though, we have seen a display surface and now we are covering a regular surface. And those two are called very similar for a reason, because they are, well, very similar. The important difference between them is that the display surface is the main surface that we are going to draw on. It's basically the main window of the game. There can only be one, and it will always be visible. A normal surface, on the other hand, is an image of some kind. You can have as many as you want, but they will only be visible if they are attached to the display surface. And this is another step that you have to go through. But other than that, the two share quite a few attributes and methods. For example, you can fill both with a color via the fill method. The one that we have already seen to fill the background color. Anyway, with that, we have covered all of the theory. Let's do some coding. Back inside of the code editor, let me run the entire thing. We have a window with a blue background. Now I think the blue background is a bit strong. Let's go with dark gray instead. That one looks a lot better. After that, I want to create a surface, which we can store in a variable. I usually call this one surf. To create a basic surface without any kind of import, you want to run pygame.surface, which you have to call and then insert one argument, which is a tuple with a width and a height of the surface that you want to create. Let's say I want to create a surface with a width of 100 pixels and a height of 200 pixels. If I now run the code, nothing is going to change. And that is intended. Because this surface, while it does exist, needs to be attached to the display surface. Only then will it be visible. And for that, we have another method that we have to call inside of our game loop. We first of all need a target surface, which in our case is the display surface, and then the method blit, which stands for block image transfer. It's a fancy way of saying that you want to put one surface on another surface. This method wants to have two arguments. The first one is a surface that you want to put on this other surface, which in our case is the surface, the one we have just created. And then we need a target position. This can be one of two things. It can be a tuple with an X and a Y position. It could also be a rectangle that we're going to cover in the next section. For now though, we have to specify two numbers. Let's go with 100 and 150. If I run the code now, we can see a black rectangle inside of the window. So that is definitely progress. However, I want you guys to think about one important thing, and that is why this rectangle is in this position. Or in other words, how do we go from this number to this position? That's a really important thing to understand. For that, we have to cover just a bit more theory. So, here is our display surface. This has a width and a height. Now in my case, the width is 1280 and the height is 720, although you might have different numbers. The specifics here really don't matter though. Combined, those two numbers are going to give us a coordinate system. And the really important thing about this coordinate system is that the origin point is in the top left. Now, if you're only familiar with high school math, you probably have seen coordinate systems that look something like this, where the origin point is in the bottom left. So if you increase X, you go to the right, and if you increase Y, you're going up. We are doing something fairly similar, except that we are inverting the entire thing on the vertical axis, which means if you increase X, you are still going to the right. However, if you increase Y, then you are going down. Now, this system initially can be really confusing, and it does feel somewhat counterintuitive. That being said, most game engines work with this coordinate systems, and you do get used to it quite fast, so it's not too bad. But anyway, the one thing that you really want to remember is that the origin point is in the top left, and that means that moving to the right means you are increasing x, and moving down means increasing y. Or if you want to go up, you want to decrease y. And inside of the game, we have placed a surface something like this. Now in this case, I believe that we have moved 100 pixels to the right, and then we moved 150 pixels down. And then we have placed the top left of the surface. At least for now, we are always placing the top left of the surface. But that is basically it. If you understand that system, you can place surfaces on the display surface. So inside of the code, if I run all of this again, we have started from the top left. This is our origin point. Then we moved 100 pixels to the right and then 150 pixels down. And then placed this point along with the rest of the surface. You can also change these numbers. For example, the 100 could become a 300. And if I then run the code, the surface is a bit further to the right. If I make this number much larger, let's say 1100, then we are going all the way to the right. The same thing we can do on the vertical axis, although here we do need to be a bit careful. The larger this number gets, the further down we go. Or in other words, if I set this to 400 and run all of this again, the surface is going down. Whereas if I set this to a 0, then we are all the way at the top. And also, by the way, you can make these numbers negative. If I set this value to negative 150, then the surface starts to disappear. But let's not do that. This is much better. Also, what you can do, like we have done for the display surface down here, you can fill the surface. Surface.fill, and then you can specify a color. Let's say a color we haven't used yet is orange. If I run the entire thing again, we get a surface with another color. And that would be the most fundamental way to display a graphic inside of Pygame. And what we can also do at this point is to create a very basic animation. The way that is going to work is, at the moment, we are always displaying this surface in this one particular position. But that number we could change. For example, I could set an x position, which by default is 100. And if I then change the x position to the x variable and run all of this again, we cannot see a difference. However, if I increase x by a certain amount, and let's say by 0.1, and run all of this again, now our rectangle is moving to the right. Not at a constant speed, and this doesn't look great, but at the very least, we have a start. And to understand what is going on here, we have to go back what I talked about in the beginning. To create any kind of video game, you basically draw a whole bunch of frames, which we are doing with a while loop. This thing is being run multiple times per second, and every time we are drawing it, we are filling the background color with this surface, and then we are drawing the surface in a certain position. And since we are changing that position, we are basically creating an animation by placing it in a different position on every single frame. That's, in the most basic sense, what a video game really is. And if you want to have a really interesting effect, if you don't fill in the background color and run all of this again, you can see that we are getting, well, something different. What happened here is that Pygame does not remove the previous image. We are simply drawing on top of it. So if you don't fill in the entirety of the display surface, you can see the last frame, which sometimes can be an interesting effect, but basically always you want to avoid it. It can lead to some funky behavior. So let's keep on filling the display surface, and if I run all of this again, we get a very basic animation. With that, we have a basic surface, and let's rename this section to a plain surface. Because next up, I want to create a surface by importing an image. Whenever you are importing an image, you are converting it right away to a surface. And for now, I want to go to images and then import player.png, or this file. And all of this we want to store in another variable. Let's call this one player_surface. To import a surface, we will need pygame.image.load along with a file path. We want to go to images, and in there we have player.png. Here's our image folder, and in there we have player.png. Now, for this file path to work, you need to be inside of the project folder. Or in other words, this is the folder you need to have open inside of VS Code. If you only had the code folder open, or you're using something like Sublime Code, you have to specify the file path from main.py, in which case you would have to go up a folder first. I'll talk about this in just a second. But use either one of those two if you're getting an error. In my case, if I run the code now, we are not getting an error message, so the import has worked. If you do get an error, you probably have to add this bit to it. Anyway, with that, we have another surface, which means when we are drawing the game, we can blit the player surface instead of the surface we have seen earlier. And if I now run all of this, we get the player ship. So that is looking really good. With that, we have a really basic import, and there are other images you could be importing. For example, we have meteor.png, and we have laser.png. Although in my case, I want to use player.png. There are three important things you want to keep in mind when you're doing any kind of import in Pygame. The first one is that depending on your code editor, you might need a different relative path. So when your code editor tries to find a file, VS Code always starts from the main parent directory, which in my case is the entire project folder. But Sublime, another code editor, would start from the Python file itself. Meaning in there, you have to specify that you want to go to the parent folder first, and then from there you want to go to images and then to player.png. Let me actually demonstrate. Here we are back in the code, and at the moment, we are going to images and then to player.png. And let's do all of that in the project folder right away. So the file path we have specified is we are going to images and then to player.png. And this is what we are importing. That is working because currently inside of VS Code, we have this project folder open, and this is our starting point. However, if I change this and only open the code folder, so now I only have main.py, and this is our starting point. If I now run the code, we are getting an error because there's no file player.png in images. To actually get that, we want to go up a folder, and then we should be finding the file. And now all of this works again. So always be really careful when you are importing something via your code editor. You should be aware of where the starting point is for the directory. Now that being said, what you could also do is go to your file and then copy the absolute path. That would also work. But I tend to prefer relative ones just to be a bit clearer. Anyway, in my case, I always want to have the project folder open. So I'm going to select this one and don't save. So we are keeping open images and then player.png, which is going to work just fine. The next issue that we have to work on is that depending on your operating system, you might need a different slash in the file path. Or in other words, if you look at this path and this path, one has a forward slash and the other has a backward slash. When you go to Windows or Mac OS or Linux or some other operating system, they all have some kind of preference. Now, usually they are quite intelligent and would accept both, but not all the time, and you do want to be careful here. So ideally, all of this should be dynamic, which we can do via another inbuilt Python method. That one is called join, and you want to import it all the way at the top via from os.path import join. All that this one is going to do is it takes a couple of folders or files and then joins them together with the appropriate file path for your operating system. The way you would use it, let me create a path via the join method. In there, you want to insert a couple of arguments that define the file path. So in my case, I want to go to images and then to player.png. And if I print that path, you can see quite well what's going to happen. We don't need the window, and from this print path, we are getting images and then player.png. And there you can actually see that on Windows, the default slash is this one, while I have used this one. So ultimately, my operating system is happy with either, but it would be better to use this one just to be a bit more consistent. So instead of using this hard-coded path, you want to use the join method along with the file path. If you run all of that, you're getting the same outcome, and your code is just a bit more robust. Finally, there's one more thing that we want to cover, and that is when you're importing an image, you want to convert it to a format that Pygame can work with more easily. That is going to increase our frame rate by quite a bit, and converting is actually really easy. You only really have two options after you have imported an image. If the image has no transparent pixels, then you want to call .convert on the surface. If it does have transparent pixels, then you want to call convert alpha. And then you are done. It's super easy to do. Or in other words, back in the code, after we have imported an image, I want to call convert on it. That way Pygame can process this surface much more easily, so we get better performance. But if I run all of this, we now get black stuff around the ship. That is because the ship has alpha values, which means instead of convert, we want to use convert alpha. If I now run all of this again, we get the ship again, and this looks pretty good. So whenever you are importing surfaces into Pygame, you either want to call convert or convert alpha, and then you are improving your performance substantially. Although if you don't do it, usually it's not going to cause an error. You just get a lower frame rate. But anyway, with that, we have covered surfaces. So at this point, you can import a surface, or you can generate a surface from scratch and then place it on the display surface. You can also move it around, although this we have to refine later on. Which means we can finish up this part by doing an exercise. I want you guys to import the star.png image, and then place 20 stars randomly on the display surface. Using randint for that should be the best way. Pause the video now and see how far you get. I want to create a star underscore surface, which we can import via pygame.image.load. And the thing that we want to import is star.png, a fairly simple image. To create a file path, we want to use join, then go to images, and in there we have star.png, which we also want to convert alpha right away. If I now run the code, we are not getting an error message, so this part has worked fairly well. Which means now we have to place all of these star surfaces on the display surface using a blit method. Now we want to place 20 of them, but for now, let's simply place a single one. I want to call display surface.blit with the star surface and the position. Let's go with 300 and 500. If I now run all of this, we can see a star. So that's a pretty good start. But I want to place 20 stars in a random position. For that, all the way at the top, I want from random import rand int. And then use a for loop for I in range 20. And then display surface.blit with the star surface, and then I need a random x and a random y position, both of which I'm going to create via random integer. For the x position, I want to go from 0 all the way to the window width. And for the y position, random integer from 0 to the window height. And with that, we are getting a lot of stars in a random position, but not in the way that's intended. Although it's a good error to talk about, because what went wrong here is that we are getting a new random x and y value on every frame of the game. That way the stars are moving around at random, which is looking really, really bad. One way around that would be, after we have imported the star surface, I also want to get star underscore positions, which we can create via a list comprehension. I want to create a tuple with an x and a y position for I in range 20. And then both x and y are basically going to be what we have created down here. So I can cut out this part and then add it there. With that, we are getting 20 start positions. And those we are then going to use inside of this for loop, which means for position inside of the star positions. And then display surface.lit with star surface and the position. Once we have that, we are getting all of the stars always in the same position. So that is looking much better. We are nearly done. There's just one more thing that I do want to cover, and that is that the drawing order really matters. At the moment, we are always displaying the background color, then we are drawing the ship, and then we are drawing all of the stars. Because of that, the stars will be on top of the player, which itself is on top of the dark gray background. Or in other words, if I run display surface.fill after the ship and after the stars, then we can only see the background. And that should make sense. We are first drawing the ship, then we are drawing the stars, and then we are filling the entire surface with a color. As a consequence, we can only see the color itself. Now in our case, I first want to display the background, then I want to display the stars via the for loop, and then I want to show the ship. So with that, if I run things again, now we can see the ship is on top of the stars, which looks much better. And alright, with that, we have surfaces. In this section, we are going to cover placing surfaces via rectangles. And rectangles in Pygame are incredibly important, because they allow you to do a whole bunch of useful things. Most importantly, they let you place surfaces much more elegantly. Besides that, they can also detect collisions, and they can be drawn. Those two things are really important, but for now, we are going to focus on placing surfaces. And for that, at the moment, placing a surface kind of sucks. Since we are always placing the top left, we don't really have much control over the placement itself. Or at the very least, if we wanted to place it in a certain position, we would have to do some math. For example, if this is the display surface and we want to have a regular surface in the bottom right, with padding to the right and to the bottom of 10 pixels each. Now for this part, we could place the top left, then get the entire right side, subtract the width of the surface, and then plus the padding. That would be possible, but also very annoying. Also, sometimes we just want to place the center or the right side of the surface and be really deliberate about this positioning. All of that is something that rectangles can do really well. The way they are going to work is that rectangles are just, well, rectangles with a size and a position. We could have something like this. Any width and height is totally fine, and you can place them in literally any position. Now, on these rectangles, we have a lot of points. First of all, we have a whole bunch of them with an X and a Y position. For example, we could measure where the top left is, where the top right is, where the center is, where the mid bottom is, and so on. On top of that, we also have X and Y positions. Those, for example, could be the left side of the rectangle, the top of the rectangle, the bottom. We also have center X and center Y. There's also width, height, and size of the rectangle. So we can measure how wide or tall this rectangle is. What is also really important is that you can measure and change each point. This makes it very easy to check if a rectangle has gone too far to the right or if you have crossed a certain point. And on top of that, these points always stay relative to each other, meaning if you're moving one of them, you're moving all of them. Or in other words, if you're moving the bottom left point in this direction, you would also move the mid left point, the mid top point, the top right point in this direction. Now, before we do actual coding, there are two more minor things that I want to cover. Number one, there are two kinds of rectangles. Rectangles and F-rectangles, or floating point rectangles. Those two are nearly identical. The only difference is that F-rectangles store data as floating point values, while rectangles use integers. For example, with a rectangle, or to be a bit more specific, an F-rectangle, the left side could have a value of something like 100.45, while a rectangle would truncate these values to 100. As a consequence, F rectangles are a lot more precise, and because of that, they are used much more often. In fact, rectangles are basically just there for backwards compatibility. Nowadays, for pretty much any kind of project, you want to use F rectangles. When we are coming to movement later on, this will become especially important. And truncating position values with a rectangle is actually really bad and can cause a ton of problems. So we always want to use F rectangles. But in older examples, you do see rectangles fairly often, so be aware of that. Besides that, you can create rects in basically two different ways. The first one is that you can create a rectangle entirely from scratch. This would either look like this or like this, depending if you have a rectangle or an F rectangle. In either case, you have to specify a position and a size. For that, you could either use 2 tuples or 4 values in sequence. Both would be working just fine, just check the documentation. Although this you don't actually see that often. What is much more common is that you create a rectangle from a surface, and then the rectangle would have the same size as that surface. This you do with getRect or getFrect. And then you can specify a point with a position. That way, once again, you're getting a position and a size for a rectangle. And this second approach is going to become really important later on. Because when you detect collisions, you want to have a rectangle with the size of the surface. But anyway, with that, we have all of the theory, so let's do some actual coding. Here we are back in the project, and I first of all want to stop the animation. So this x plus equals 0.1, we should get rid of, and then run all of this again. And there we can see we have the spaceship along with the rest of the game. And that works reasonably well. However, imagine you wanted to place the ship in a specific position. At the moment, we have a random top left point. I think there was 100 pixels from the left and then 150 pixels down. But what if you want to place the ship right in the middle of the window? Or you want to place it in the bottom right with padding on each side? If you always place the top left, this can get a bit tricky to calculate. And rectangles make all of this significantly easier. So, after we have imported the player surface, I want to create a player underscore rectangle, which we do first of all with the surface. In this case, player surface, and then get underscore f rectangle. And in there, we want to specify one of the points of the rectangle that we want to place, and then the actual position. For example, I want to place the center point of the rectangle at position 0 and 0. This 0 and 0 would be the position on the display surface. Or in other words, it would be in the top left. With that, we have a rectangle. And this rectangle we can use inside of the Blitten method. So in there, instead of a tuple, we can use the player rectangle. If I now run the code, the center of the ship is all the way in the top left. Alternatively, I could also place the top left point, and that way, the top left of the ship would be in the origin point of the display surface. And that example isn't terribly useful, so what I actually want to do is get the center of the rectangle and then place it right in the center of the window, which we can do by using window width and window height. Or in other words, I want to get the window width and divide it by 2, and then the window height and divide it by 2 as well. If I now run the code, the ship is right in the middle of the window. And just for one more example, imagine I want to place the ship in the bottom right with padding to the right and to the bottom. For that, I could place the bottom right of the ship. The tuple for that is going to be window width minus 10, and then window height minus 10 as well. If I now run all of this, we can see the ship is in the bottom right. Or in other words, with this system, we can place the ship super easily in a lot of positions. Although let's start by placing the ship in the center of the window. I think that's a bit better. Like so. Now what you can also do is update individual points of this rectangle. That way you would update all of them. For example, what we could do is to move this ship again, we could pick the player rectangle and then the left side. And remember what I talked about earlier. Inside of a rectangle, we have tuples and integers. Or well, for an F rectangle, those would be floating point values. But when I place the top left, or the center, or the bottom right, I always had to specify an X and a Y position. But when I'm specifying the left side or the right side, I only ever have to specify a single position, because those only represent a single value. Like we are doing inside of playerRect.left, we could, for example, set to 100. That way, our ship is now going to be much further to the left. If I change this value to 150, we're going a bit further to the right. And once again, I can make all of this dynamic and increase this value by 0.1. If I now run all of this, the ship is moving to the right. And this is also the part where floating point rectangles become incredibly important. Because if you had a normal rectangle, so at the moment, we are using getFRectangle to create a floating point rectangle. If we used getRectangle and ran all of this again, the ship isn't going to move at all. That happens because the rectangle around the ship at the moment looks something like this, and the left side has a value of, let's say, 600. And really important, this is an integer, meaning anything after the dot will simply be ignored. And well, what we are doing at the moment is adding plus 0.1 to it, which means after one frame, we are getting to 600.1. But since this rectangle always truncates the position value, this 0.1 will be removed entirely. Hence, we are not moving. That being said, if you change this value to a 1, then we should be seeing some movement, and we do. But this isn't what I actually want to do, so let's keep this at 0.1 and then use a floating point rectangle. For basically any project nowadays, I am using floating point rectangles. They are simply better. Although I guess we could make this just a bit faster. But anyway, this is basically what you need to get started with rectangles. They don't really get that much more complicated. I suppose one more thing that we could be doing is that at the moment, we have used the rectangle and its values to move a surface. What you can also do is measure these points. For example, what you could be doing is print player rectangle dot right. That way, if I run all of this again, you can see the right side of the player, which by itself isn't terribly useful. But for example, you could be using this if I cut it out inside of an if statement, that I only want to move the player to the right if playerRect.right is smaller than the window width. If I now run all of this again, we are moving to the right, but at some point we are stopping. So this is working really well. And those are the two ways you're using rectangles to move stuff in Pygame. You either measure a point or you move a point. And after you have that, you're using the blit method with a surface and a rectangle, and then you are getting some movement. Remember, in a video game, any kind of movement is simply drawing a graphic in a different position. And that you slowly update over time. That's all you ever do. Which means we just have to do an exercise, and then we are done with this part. I want you guys to do 3 things. Number 1, import a meteor and place it in the center of the window. And obviously for that, use a rectangle. Besides that, import a laser graphic and place it in the bottom left, with 20 pixels of padding to the left and to the bottom. And finally, make the player graphic bounce from the left to the right continuously. That should be quite a bit, so pause the video now and see how far you get. Number 1. I want to import a meteor graphic and place it right in the center of the window. For that, first of all, we have to import meteor.png. That we can do under importing an image, and I guess by now this should simply be called imports. In there, I want to create a meteor underscore surface, which we do with pygame.image.load, then using the join method. I want to go to images and then import meteor.png. Also really important, never forget convert alpha. After we have that, I want to create a meteor underscore rectangle, where we have the meteor surface, and then use get f rectangle, where I want to place the center. The position for this has to be a tuple with an x and a y value. X is going to be window, not height, but width divided by 2, and y is going to be window height divided by 2. That is going to give us a surface and a rectangle. So now inside of the game loop, let's do it on top of the ship. I want to call display surface.blit again with the meteor surface and the meteor rectangle. Let's run all of this, and we have a meteor right in the middle of the window. So that is looking pretty good. Although I suppose we should draw all of this before the player, I think it's better if the player is always on top of everything else. Next up, we want to place the laser in the bottom left with 20 pixels of padding. For that, we will need a laser underscore surface with pygame.image.load. Using the join method, I want to go to images and then import laser.png. And just to double check, we are importing this laser.png. And also, as always, convert alpha. After we have that, we want to create a laser rectangle with the laser surface and then get f rectangle. And since I want to place this one in the bottom left, I want to place the bottom left point. And for that, I will need an x and a y position. And now let's think about it. We have the entire window looking something like this. And we want to place the laser in this bottom left point, which means from the left side, we want to have an offset of 20 pixels. Oh, and also we are placing this point, which means for x, we only want to go 20 pixels to the right. But then for y, we want to go all the way down to the bottom of the window and subtract 20 pixels from that. That way, we are getting to this point. And if I could draw a straight line, this would be much better visually, but you get the idea. So for x, we want to have 20. And for y, we want to get the window height and subtract 20 from that. Now running all of this again, we don't see anything because we are not calling the blit method. Once again, let's do it before the player. Display surface.blit with the laser surface and the laser rectangle. Next attempt, and there we go. In the bottom left, we now have a laser. That is making some progress. And I think at this point, you might become a little bit uncomfortable because we are importing a surface 4 times, and we basically copy the same method 4 times, which really isn't efficient. Also, when we are displaying all of the graphics, we are using the same line 3 times with different arguments, which also isn't great. And don't worry, later on, we're going to make all of this much more efficient so that we can import hundreds of graphics with just one function. We wouldn't have to write every single line by hand, because that's just not a convenient way of working. Also, later on, we are going to learn about better ways of displaying multiple graphics. So with all of that, there's just one more thing to do, and that is move the player left and right. And for that, let's organize all of this a bit better. So we are moving the player with these 2 lines, move them a bit down, and then add a comment. We have the player movement. And essentially how we are going to approach this. When we are creating the player, we can add a player underscore direction, which by default is going to be 1. And then when we are moving the player, we are getting the player rectangle and then use one of the points. We could go with x here, that's simply the left side. Those 2 values are identical. And then increase this by the player direction multiplied with the speed, which in our case is going to be 0.4. And then we don't need this if statement for a bit. If I now run all of this again, the player is moving to the right. However, if I set this value to a -1 and run the entire thing again, the player is moving left. So that is working really well. Which means inside of this if statement, we want to check if the player is outside of the window, which means player.rect.right is greater than the window width, or player.rect.left is smaller than 0, or the left side of the window. If either of those conditions are met, Then we want to change player direction and multiply it with -1. If I now run all of this again, we are bouncing left and right. That is working really well. So very happy with that. And at this point, we have covered the basics of rectangles. Now, I guess there's one thing that I haven't covered, and that is you can create rectangles from scratch entirely. So for another comment, a rectangle. If you want to create a plain rectangle, you simply would call pygame.fRectangle. This could also be pygame.rectangle if you want to have a normal rectangle, which we basically never want to do. And inside of there, you have to specify two tuples, one for the position and another for the size. This would be one way. Alternatively, you could also specify the left, the top, the width, and the height. Both approaches are totally fine, and at the end, you are getting a rectangle. That being said, for our purposes at the moment, this isn't particularly useful because we have no reason to create a rectangle like this. But for now, don't worry too much about it. And for the last bit before we finish, if you look at the documentation, there you have rectangles. And this is going to give you a long list of methods that you could apply to a rectangle. If you go a bit further down, you can see all of the points that I have talked about earlier. The two that I haven't mentioned are X and Y, which are simply left and top. So if you want to know more about them, just keep on reading all of this. I will talk about it later as well. And we are going to use rectangles a lot. So this part of the documentation is going to be something you definitely want to be familiar with. For example, in there, we have all of the collision methods, which are going to be super useful for a game. Just one more minor thing before we are finishing all of this. When we are placing a surface via a rectangle, what we actually do is placing the top left of the surface in the top left of the rectangle. Or in other words, it doesn't matter if you use player rectangle or player rectangle.top left. The end result is going to be the same. Also, while we are here, the size of the rectangle does not need to match with the size of the surface. For example, what we could be doing, below the player, I can create another plain rectangle and then assign pygame.fRect with a position of, let's say, 100 and 200. And then for the width and height, I can use entirely random values. Let's say 200 and 620. If I now use this rectangle to position the player with the blend method and the rectangle, we can still place the player in a certain position, even though the rectangle is going to be much larger. So while the player would occupy this space, the rectangle would, I think, be something like this. But as far as split is concerned, this doesn't matter because we are always placing rect.top left. Although obviously this isn't what I want to do. And generally, it is a good idea to have a rectangle and a surface with the same size. Especially when it comes to collisions, this will become really important. Although you don't necessarily have to do it. But anyway, I want to get rid of the rectangle and then we are done with this part. With surfaces and rectangles covered, we can work on moving stuff in much more detail. We already have some movement, but it's fairly crude and we can refine things a lot. Although for all of that, we are going to need some theory. The general idea of how movement works in literally any video game is that you are blitting a surface in a different position on every single frame. So for example, we can slowly draw the player's ship further to the right, and if these changes are gradual enough and we have a high enough frame rate, then your brain will think this is movement. That is literally it. So in Pygame, when you are blitting a surface, you can either change the XY tuple or the rectangle position. That is literally it, although fundamentally, we are still just drawing a surface in a different position. And that I can visualize quite well. Back inside of main.py, we still have the ship moving left and right with a couple of other elements. And what I want to do is add one more thing in the general setup. I want to add a clock. And the value for this is going to be pygame.time.clock. A clock object in Pygame is incredibly useful for two reasons. Number one, it can control the frame rate. At the moment, our frame rate is simply this while loop. Or in other words, if your computer can run this while loop 10,000 times a second, then your frame rate is going to be 10,000 times a second. Depending on your computer, this might be faster or slower. And we do want to have some control over this, which we can do via the clock object. The way you would do that is inside this while loop. Doesn't really matter where you put it. I prefer to do it right in the beginning. You can call clock.pick and then enter an integer, which is going to give you the frame rate of the game. If you leave it empty, you are going to get the maximum possible frame rate. Or in other words, the speed of your computer determines the frame rate, which is generally what you want. That way you get the most amount of frames. But if you change this to a 60 and run all of this again, now our ship is moving significantly slower. And you can also see that the movement is quite a bit more choppy, although this might be difficult to see on YouTube. To make all of this more visible, let me change the frame rate to 1. That way, we're getting 1 frame per second. And also, while we're doing this, when we are moving the player, I want to increase this number by a lot. Let's say 100. If I now run all of this again, you can see how movement actually works. We have the player and we are simply drawing it in a different position. And that is literally it. If you lower the frame rate far enough, then movement is going to look very, very static. And you can already tell if I change the frame rate back to something very small, let's say 4, then we are getting something that looks a lot more like movement. And if I change it to 24, is usually the lowest frame rate that we perceive as motion. Although still not looking great. But I hope you get the idea. The fundamental thing that you have to understand from movement is that we are drawing a frame, and on every single frame, we are changing the player position a little bit. And then for some reason, the human brain doesn't see a lot of images, the human brain sees movement. That is fundamentally all we are doing. That being said, we can refine all of this in 2 important ways. Number 1, we want to use vectors to store a direction. That way we can control the movement much better. On top of that, we want to include delta time to make the movement frame rate independent. So 2 important words here that we have to cover. We are going to learn about vectors and we're going to learn about delta time. Let me talk about why those 2 are important first of all. Inside of the game, via these 3 lines of code, we are moving the player left and right, which I don't actually want to do anymore. So let me get rid of the if statement and also change this part. I only want to move the player in one direction. Let's say to the right by 100 pixels on every single frame. If I do that, the player moves a little bit too fast. Let's say I want to change this to 20 and then the frame rate, so clock.tick, should be 10. If we note all of this again, you can see the player is moving to the right. However, what if I wanted to move the player to the right and up at the same time? For that, we would need 2 lines of code. Player.rect.x plus 20 and player.rect.y minus equal, let's say 10. If I now run all of this again, we get the player is moving up and right. So that part is working, but it's also kind of annoying because for a very simple thing, we need 2 lines of code. Ideally, what I would prefer is player.rect.center plus equal 20 and negative 10. That would be much easier. And by the way, what is happening here is that we are grabbing one of the tuple points inside of the rectangle. Center has an X and a Y position, and we want to update both of them at the same time. That, however, we cannot do at the moment. If I run the code, we are getting an error message that we have an invalid rect assignment on this line. You simply cannot add a tuple or a list to a tuple position inside of a rectangle. For that, you are going to need a vector. That's the first thing we are going to work on. The second issue is going to be frame rate independence. And you have already kind of seen the issue. At the moment, our frame rate is 10. And that is going to give us one kind of speed. So our player moves at this speed. But if I change the frame rate to 100, then our player moves significantly faster, which is fine if we have a stable frame rate. But later on, we want to have a flexible frame rate, meaning the game could run faster or slower on different computers. And this we have to account for in the movement, so that a player with a faster computer doesn't get much faster movement. But anyway, let's start with the movement. I want to make sure that we can control the player direction much better. And for that, we're going to look at vectors. A vector in pygame, and well, basically anywhere else, is a list with two values. They are always going to be x and y. And you can only ever have two values, at least in a 2D vector. There are also 3D and 4D vectors, but in our case, we are only ever working in a 2D space. So our vectors will only ever have an x and a y value. Those values you can read and change. For example, what you could be doing is create a vector with x being 1 and y being 5. You could read the first part, so x, with indexing, although nobody really does that. What you rather see is that you use vector.x and vector.y. And via those, you can get the value and you can update the value. So with that, we basically have a list that is constrained to two values. So far, this isn't exactly useful. However, via vectors, we can do vector math, which is incredibly powerful. If you multiply a vector by a number, then you multiply both numbers inside of that vector. If you were to do all of that to a list, you would simply duplicate all of the values. So the difference here is quite noticeable. We're going to do this in practice in just a second. Also, you can add two vectors together, and then you get the sum of the individual numbers. And finally, what is really important to us is that you can add a vector to the tuple position of a rectangle. That way we can change both x and y at the same time. That was quite a bit, so let's write some actual code. First of all, inside of the player direction at the moment we only have -1, but I want to create a pygame.math.vector2. And notice here there's also a vector 3. This one would have 3 values, x, y, and z, but this we don't really need. So in our case, we have a vector 2 with x and y. If you leave these values empty, you're going to get a vector with 0 and 0, which means if I leave it like this and then print the player direction, we are getting an output of 0 and 0. Although in my case, I want to have 24x and -10 for y. We also don't need the print statement anymore. And now, if we go to these lines, at the moment, we are updating x and y of the player rectangle individually, but that we don't need anymore. Instead, I want to get playerRect.center plus equal the player direction. And now, this is going to work, although it's a bit fast. Let's change the frame rate back to 10 so we can see what's going on. And now, the player is moving to the top right. And later on, we can refine all of this to make it even more useful. But this is something that you see really often. That you take the tuple position of a rectangle and then add a vector to it to update it. Also, what you could be doing. So by default, the values of the vector are 20 and -10. However, we could print player direction multiplied by 2 and then run the entire thing. Now as an output, we're getting 40 and -20. The way you would be using this in an actual game is, for the player direction, we want to have fairly low values. Because that way, we can define a player underscore speed, which for now could be, let's say, 10. And then, when we are updating the movement, we are increasing the value by the player direction multiplied with the player speed. The result is going to be what we had before. Via this system, you can separate the player direction and the player speed. So for example, the player direction we can get simply via player input. Something we haven't done yet, but that's going to be the next section actually. Oh, and just for reference, if you wanted to multiply a list, let's say we have a list with 1, 2, and 3, and we are multiplying all of this with 2. If I run the code, our output is going to be a list where every single value was duplicated. Or in other words, math for vectors and math for a list is completely different. Those two just aren't comparable. But anyway, with that, we have vectors. Something that you definitely want to use in pygame. They are super useful. So the next issue that we have to work on is frame rate independence. And ultimately, the issue we have here is that depending on the computer that the game is run on, you might get wildly different frame rates. And since we update the position on every new frame of the game, the faster the game runs, the faster the movement is going to be. Which isn't ideal. You want the movement to always be the same regardless of the computer, which we have to guarantee. Imagine you have two players, one with a really fast computer and one with a really slow one. The one with the better computer might run the game 10 times as fast. If this means that all the movement in the game is 10 times as fast, it just wouldn't be controllable anymore. And let me visualize all of this a bit better using math. So, we have a table with 3 columns. The first one is going to be the movement, and we always try to move by 10 pixels. This value doesn't change. And also let me do all of this in the game right away. For our player direction, I want the player to only move to the right, so x is going to be 1 and y is going to be 0. Hence, we're not moving up or down. And then the player speed is going to be 10, the value you have just seen in the table. If we now go to this line, the player should only move to the right. Let's try, and there we go. The player is moving to the right. But depending on the frame rate, this value might change. So if we have a frame rate of 30, we're moving a bit faster. If we're getting to a value of 60, we're moving quite a bit faster. And if we get to 120, we're moving a lot faster. And those numbers we have in the table. The frames that we are setting in clock.tick is this frames per second. It could be 30, it could be 60, it could be 120. It could also be something like 1,000. Since we only make 2D games, the frame rate can actually become quite large, something you definitely want to control for. And finally, the really big issue is this final column, in which we are calculating the actual movement, which is simply the movement multiplied by the frame rate. And from that, you can tell that we are getting wildly different movement speeds. These numbers have to remain the same, because inside of the code, we are specifying the same speed. So getting from this to a very different actual speed in the game simply isn't acceptable. And to fix all of that, we will need delta time, which is the time it takes your computer to render one frame. For example, if our frame rate is 60 frames per second, then we can divide 1 second by 60, so it takes our computer 0.017 seconds to render one frame. That value we can actually get from this clock object. It's simply the return value. So in there, we can get dt, short for delta time. And after that, I can print delta time and run the code. And now you get in the bottom, we have a delta time of 8 or 9. That is because our frame rate is 120. Or in other words, the values we are getting down here are 1 divided by 120, and this number can fluctuate a bit. Hence, we're getting either 8 or 9. But if you do the actual calculation, the value would be 0.0083. And I should mention that this calculation is in seconds, but the return value from clock.tick is in milliseconds. Hence, we're getting 8 or 9 here, and 0.008 in here. If we change this value to 30 and run all of this again, then we are getting 33 or 34. And I guess from the slides, the value we have used was 60 frames per second, and if I run this, we're getting 16 or 17 milliseconds. Also, if I leave this value empty and we let the game run as fast as possible, in that case, our delta time is going to be 0 or 1, which indicates that we're getting a frame rate of about 1,000 frames per second, or even more. That's something we can actually measure. After clock.tick, we can get clock and then get FPS. And don't forget to call this one. If I now run the game, we can see our frame rate, and if we don't limit it, in my case the frame rate is somewhere between 1,000 and 1,250. Also keep in mind, in your case, these numbers might be different, and that is totally fine. What is really important to understand for now is that delta time for every computer can be different, and we are simply measuring the difference in time between the current frame and the last frame, or in other words, how long it takes your computer to render one frame. And that information is incredibly useful. To understand why, let's have a look at another table. The first three columns is what we have seen already. In there, we have a movement, we have a frame rate, and then we get the actual movement. And these numbers being different is the actual problem. So what we want is that all of these values are the same. And for that, we can use delta time, which is the time it takes to render one frame. So for example, if our frame rate is 120, our delta time would be 0.08. If it's 60, we get 17 milliseconds. If it's 30, we get 33 milliseconds. If it was 1,000, we would do 1 over 1,000. So this value would be 0.001. And that information is incredibly useful because that way we can do this calculation, where we have the actual movement, the frame rate, and then delta time. If you add all of them together, you are getting always the same movement regardless of the frame rate. And the logic here should actually make a ton of sense. All that we are doing is we are multiplying the frame rate with delta time, which essentially cancel each other out. The value of these two combined is basically always 1. Or in other words, simply look at the frame rate and delta time. For example, for 60 frames per second, we get 60, and we are multiplying it with 1 over 60, the number we are getting here. And those two numbers simply cancel each other out. The end result is going to be 1. As a consequence, the only thing that's really left is the actual movement that we care about. And with that, we can control for the frame rate. Let's implement it. Inside of the code, we are already getting delta time. But this at the moment is in milliseconds, which is a bit awkward to use. So I want to convert it to seconds, which we can do by dividing it by 1,000. And after that, all that we really have to do to move the player is we want to get the player direction, multiply it with the player speed, and then multiply it with delta time. If I run all of this, we get some kind of movement. At the moment, this is really slow. So let's change the player speed to, let's say, 100. That way, this feels a lot better. Actually, this could be 300. Let's try this again. And yeah, that feels better. Cool. So with that, we have the player speed and we get some kind of movement. What is really important now is that this is independent of the frame rate, which means if I change this value to a 10 and run all of this again, we are getting the same speed, although a lot fewer frames. But that's expected because our frame rate is much lower. Although, and this is the important part, the actual speed of the ship has not changed. We simply draw it less often. And that is it. With that, we have covered delta time. And most importantly, we have this line, which is the standard to move anything in pygame, where you have the 2-bit position of a rectangle, and to it you add the direction via a vector, multiply it with the speed, and multiply all of this with delta time. Via all of this, we can move things very easily, and we can move it independently of the frame rate. Finally then, before we are finishing this section, let's do another exercise. I want you guys to make the player ship bounce around the window like an old DVD logo. The end result should look something like this. Also, in case you don't know what the DVD is, here's a Wikipedia entry. Either way, pause the video now and see how far you get. Back in the game, I want to start with the player direction. I think by default this one should be 1 and 1. That way, if I run all of this again, the player moves to the bottom right. Also, the frame rate should be unlimited, so the movement looks a bit nicer. That feels better. So now, once the player touches this point, we want to move the player in this direction. For that, before we are doing the actual player movement, I want to check if player rectangle dot bottom is greater than the window height. If that is the case, I want to get the player direction and then change the Y part. And all I really want to do is multiply it with -1. That way, if we run the entire thing again, we are bouncing up. Besides that, we also want to check if player rectangle.right is greater than the window width. If that is the case, we want to get the player direction, although now we want to get player direction.x, and then multiply it with -1. And now we are bouncing and then disappearing at the top. So that part is looking pretty good. Next up, once the player hits the top of the window, we want to bounce down again. That we can do inside of this if statement. We simply want to add another part if player rect.top is smaller than 0. If that is the case, let's try this part. We are bouncing down. And at the bottom, we are bouncing up again. So only one more side to cover, and that is going to be the second condition for the second if statement. If player rect.left is smaller than 0. And with that, we are bouncing around quite well. So with that, we have movement that is much more robust. Next up, we can work on the input. I've made a mistake, and you might have already noticed. So sometimes we have the ship, and the ship bounces around the screen, something like this. But some of the time, the ship gets stuck on one of the walls. So for example, if we have a bottom collision, then the ship gets stuck here and wobbles back and forth. If we increase the speed of the ship to, let's say, 1000, if we now run the game, there you could already see some weird behavior. It doesn't happen all the time, but it could be an issue. So essentially what's happening here is we have a ship moving like this, and then once we hit a wall, we are bouncing off these few lines here. However, there is a potential for a bug. For example, if the right side of the ship goes too far to the right, so much further than the window width, let's say we are here. We are still trying to move in this direction. However, when we are checking all of this again, the ship is still too far to the right. And as a consequence, the direction of the ship will go this way. And this is going to continue forever then. We are basically stuck to this wall until we get lucky and the ship accidentally gets a bit further to the left. Now, one way to start working on this is to add greater than or equal to this point, or smaller than or equal to. That would do a bit, but it wouldn't fix the issue entirely. Now, for this part, since we are going to change these lines later on anyway, I am not going to worry too much about it. But what you would have to do if you're bothered by it, you would need a separate if statement for each side. For example, if player rect.bottom is greater or equal than the window height. If that is the case, we want to set the player rect.bottom to the window height, and then we also want to set the player direction.y to -1. That way we are making sure that the player never exceeds the bottom of the window. And later on, when it comes to the Pong game, we are going to implement that logic. Although for now, I'm not going to worry too much about it. Anyway, this is going to cover the movement, so let's work on the input. Although one more quick thing before we get to that. If you look at the documentation, there is no vector entry. Instead, what you would have to do is go to pygame.math, and in there, we have a vector2 and a vector3, along with a whole bunch of additional information. Essentially, when you are creating a vector in Pygame, you can either write pygame.math.vector2 or use the shorthand with pygame.vector2. Both would get you the exact same result. The last really major thing that we are going to need for a game is getting user input. And for this part, we're going to cover mouse input and keyboard input. By the end of this section, we will be able to move the player around freely on the window, either with the mouse or with the keyboard. Now, getting input in Pygame can be done via two ways. And one we have already seen, that is the event loop. We already used this one to close the game. And in there, we could also get keyboard input and mouse input. The one limitation here is that we can only ever have a single event loop. So if you have a complex game, this part is going to get really messy. The alternative to it would be pygame.key and pygame.mouse. Those can also get the keyboard and the mouse input, and they are quite a bit more flexible. They can be called anywhere in the code, which makes them super useful to use in classes. But other than that, those two are fairly similar. They both let you capture user input. But there are some minor differences, and I'll talk about them later. Now, you might be wondering, which one should you choose for input? And well, in my case, I basically always use pygame.key or pygame.mouse for a couple of reasons. Most importantly, they are much easier to integrate with classes, something that we are going to talk about in the next section. But since you can call them anywhere in the code, it makes them really easy to use. And on top of that, they can check if a button is being pressed continuously. And I'm going to demonstrate this in the code in just a second. But when you're using the event loop, you are checking the action of a button being pressed. You are not checking if a button is being pressed. So in practice, if you're holding down a button and then use the event loop to capture the input, you are only getting a single input. Whereas if you use pygame.key and you check for the button press, you would get continuous input. If you want to move something around on the screen, the second part is just better. However, it is totally valid to get input via the event loop. And sometimes that part is even necessary. For example, if you want to get touch input or the mouse wheel, then you will have to use the event loop. And generally, there's nothing wrong with using it. Just keep in mind that you would have to structure your game around it. But other than that, this part shouldn't be too difficult. Let's jump right in. Once again, here we are in the code. And the part that captures input already is this event loop. At the moment, we are checking if the event type is pygame.quit, i.e., we are closing the window. But you could check for quite a few more things, and you would always use event.type. For example, in there, we have pygame.key down. If that is the case, I can, for example, print key down. If I now run the code, I can press any button on the keyboard, and we are getting key down. So that part is working, but it's not terribly useful. To get a bit more information, we can get event.key. With that, we are getting a value associated with every single key on the keyboard. Now, this is always going to be an integer, so at the moment, this isn't particularly useful. That being said, for all of these values, Pygame has a constant to check what key we actually have. The way you would use that is you would check if the event key is equal to pygame and then k underscore whatever key you are looking for. There are quite a few options. For example, we could start with k1 or the number 1 on your keyboard. If I run the code now and I press any key, we always get false, but if I press 1, we are getting true. So I know I am pressing this key. Or in other words, what you could be doing is let me cut this part out, and then we want to check if there's a key down event and if the event key is equal to pygame.k1. If that is the case, we want to print 1. So now I can run this again. And if I press 1, we're getting 1. If I press anything else, nothing is going to happen. And that is the basics on how you can get keyboard input inside of the event loop. Let's have a look at the documentation. You want to look at event. If you click on that, you can get all of the event methods. The one that we have already used is pygame.event.get. And that is by far the most important one. If you scroll down a bit, you can see all of the main events that you could be looking for. In there, we have already used quit and we have used key down. There's also key up, there's mouse motion, mouse button up, and mouse button down. Those 5 are the ones that you are probably going to use the most. And if you then look on the right, you can see a few more parts that you could be using. For example, what key we are pressing and if there's a modifier. Or when it comes to mouse motion, we have the position and the buttons. And that's basically all that you need to know about it. But let's do all of this in code. At the moment, we only have keyboard input. I also want to get mouse input. For that, I want to check if the event.type is equal to pygame. Let's start with mouse motion. This is going to trigger as soon as we have any kind of mouse movement. So basically all the time. Let's for now print mouse is moving. For this part, let me show my mouse, and if I now run the game, I can move the mouse, and we get mouse is moving as soon as I am moving the mouse. Once again, this isn't terribly useful, but what you could be doing here is print event.position. That way, we always get the position of this event, which has to be the mouse position. Let's try, and now you can see my mouse position in real time. If we go all the way to the top left, we are getting 0 and 0. And all the way in the bottom right, we are getting nearly 1280 by 720. And that is working pretty well. And while we have that, we can also get rid of this player movement. We also don't need the comment anymore. And then do something like, as soon as we have mouse input, I want to get the player rectangle and place the center to the event position. I can now run the entire thing again, and the ship is following the mouse. That part is super easy. And that is basically it. With that, we have keyboard and mouse input via the event loop. A pretty solid start, but I wouldn't recommend using it. Hence, I'm going to comment out all of this. Instead, before we are drawing all of the game, I want to do something else, and that is going to be the input outside of the event loop. And that we can do via pygame.key or pygame.mouse. Let's start with the mouse one. This one is a bit easier to use. So this mouse is an object, and on there we can get the cursor, get focus, get position, get pressed, get relative, and so on. The one I care about right now is get the position. If you're calling this one, you are getting the mouse position wherever you are calling this method. So let's print it, run the game, and now I can once again track my mouse position. And this has worked just as before, so quite happy. Besides that, we can also get rest, which is going to give you the mouse buttons that are being pressed. If I run this one, we're getting a tuple with 3 values. And if I press the left mouse button, we're getting true, false, false. If I press the right mouse button, we get false, false, true. And if I press the middle mouse button, so the mouse wheel, we're getting false, true, false. If I press all 3 at the same time, we're getting 3 true values. And that's kind of it. We basically have continuous input, and then we are checking which buttons are being pressed. If they are being pressed, they are returning true. To get one individual value, you can simply use indexing. For example, if you want to check the left mouse button, this would be index 0. If I run this again, I can check if the mouse button is pressed or not pressed. The last mouse input that you see fairly often is get relative. This is giving you the relative mouse speed. And to explain how this one is going to work, let's run the game. Right now, once the game is running, we're getting an output of 0 and 0. And this is effectively the mouse speed. If I move the mouse around, we're getting some values in here. But if I stop moving, this value goes back to 0 and 0. So effectively, this is checking if the mouse is moving and how fast it is moving. But that's basically all you need for the mouse input. Let me comment it out so we're not printing too much. And next up, we can work with pygame.key. Get focused, get just pressed, get just released, and get pressed. Those are the really important ones. And get pressed is the one you basically always want to use. That being said, if I print the output, we're getting way too much. So in the game, you are getting a giant list with all of the potential keys being pressed. Like with the mouse buttons being pressed, we're getting a list with all of the potential keys that could be pressed. And if they're not pressed, we're getting false. If they are pressed, we're getting true. The problem for the keyboard is that we have a lot of values. So this isn't exactly feasible. Now, the way you are supposed to use this is you should be storing the return value inside of a variable. Let's call it keys. You can use indexing on this and then use the constants that you have seen inside of the event loop. For example, I could use in here pygame and k_1. If that is the case, I want to print 1. And also this should be an if statement. If I now run all of this again, I can press 1 and we're getting an output of 1. If I press anything else, nothing is going to happen. So that is basically how you would get input via the keyboard outside of the event loop. And now I can talk about one important difference between the input from the event loop and the input from the other methods. When we are getting the 1 being pressed from this part, we're getting an output of 1 continuously, as long as I'm holding down the key. To demonstrate, let me run all of this again. I can press 1, hold it down, and we get an infinite number of 1s. However, if I comment out all of this and then uncomment this if statement, I can run all of this again, and now if I press 1 and hold it down, we are only ever getting a single output. Or in other words, the event loop is checking the action of a button being pressed, whereas pygame.key.getPressed checks if a button is being pressed or not. The difference is quite minor, but really important to understand. Although if you do understand it, then it should be fairly easy to use keyboard input. So let me comment out the if statement inside of the event loop and then move the player rectangle via keyboard input. For that, we already have a player direction, which by default should be 0 and 0. And since those are the default values, I can leave this value empty entirely. Also, the speed should be, let's say, 300. Now, the way we are going to use input is by changing the player direction. Or in other words, I want to check for the keys and then check for k_. Right, for example, and once I have that, it's going to be player direction.x will be 1. And then to apply all of this, we want to get the player rectangle dot center plus equal player direction multiplied with player speed multiplied with delta time. If I now run all of this and I press right, the player is moving to the right, although he never stops moving to the right. And that should make sense. Once we are pressing right once, we always have this direction. There's no way to return to a player direction x being 0. Although for that, we could add an else statement, in which we are setting the player direction.x back to 0. That way, I can move the player to the right only if I have actual input. So that is working really well, but we have a whole bunch of lines for something that should be really simple. So this is kind of overkill. What is a much more elegant way of solving this is we can set the player direction.x to an integer of keys and pygame.write. The output would be exactly the same. So I can run all of this, and the player is still going to move to the right. Now the reason why this is working is because we have a Boolean value, which can either be true or false. And if we then use the int method, true is going to become 1 and false is going to become 0. And this is the value we actually add to player direction.x. And what you can also do is copy all of this and then subtract pygame.k_left. If I now run the game again, I can move left and right totally fine. And I hope the logic for this one makes sense. I guess it would be a good idea to do some examples. Imagine k_right is being pressed and k_left is not being pressed. As an output, we would then get a value of 1 from right and 0 from left. And 1 minus 0 is going to be 1, meaning we're moving to the right. If we have k_right not being pressed and k_left being pressed, then we're getting an output of 0 and 1. And 0 minus 1 is -1, hence we are going left. Finally, if both are being pressed, then we are getting 1 minus 1, which is going to be 0, so no movement at all. And well, with that, we have very basic player input. This line I want to duplicate, and then get player direction.y. For this, we can check pygame.k down minus pygame.k up. If I now run all of this, I can move the player around in every possible direction, so this is working really well. Perfect. We are nearly done. There's just one more thing that I really have to cover, and that is at the moment the speed of the player is inconsistent, which you might find weird because we only have a single player speed, the one that we are setting up here. However, if you run the game, and if you only move left or right and up or down, you're getting one speed. But if you move diagonally, all of a sudden you are moving quite a bit faster. And this I can actually demonstrate a bit better. I want to print the player direction multiplied with the player speed. This value is going to be a vector. And on every single vector, we can get a magnitude, which is the length of the vector, which in this case would be the distance the player is moving on every single frame. And in theory, this number should always be the same. But if we are trying this, I can move left, right, up or down, and we're getting 300. But if I move diagonally, all of a sudden, we're getting 424, or a much faster speed. And if you think about it for a second, it should make sense. If we only move in one direction, we're getting one of these inputs, i.e. we are moving 300 pixels to the right, to the left, up or down. However, if we get two inputs at the same time, then we are moving to the right by 300 pixels and we're moving up by 300 pixels, which means the actual distance being traveled is this line, which is going to be much more than 300. In our case, it's going to be 424. So this number we have to account for. And the way you would do that is by changing the player direction. This one can only have a value of 0 and 1. For example, if we are only moving to the right, then the value for this one would be 1 and 0. However, if we moved to the right and down, then this value would be 1 and 1 for x and y. And because of these two ones, we are getting a much greater movement. So what we have to figure out is that when we are moving to the right, we have a direction of 1. Or rather, the length of player direction when we are only moving to the right is going to be 1. If we're moving to the right and down, i.e. we have this and this, then the length of the vector will be greater than 1. And to fix that, we have to change the length of this line and this line so that the actual distance traveled is also going to be a 1. And that part is actually really easy because there is an inbuilt method for that. This process of converting the length of a vector to a 1 is called normalizing a vector. And basically all that's happening is you are changing these numbers so that the overall length of the vector is 1 with the number staying proportional. The way you would do that, before we are actually moving the player, I want to update player direction and set it to player direction.normalize. Now, if you're running the code at the moment, this is going to give us an error that we cannot normalize a vector of length 0. We are trying to change the length of a vector to 1 while keeping x and y proportional. But if both x and y of a vector are 0, then this isn't possible. Pygame simply doesn't know in which direction we want to go, hence it cannot normalize the length of the vector to a 1. And this is exactly the error we are getting here. Fortunately, the way around that is fairly simple. We only want to do that if player direction is different from 0. And inside of an if statement, any vector on Pygame is going to be falsy if the values are 0 and 0. If you have any other value, then it's going to be truthy. Which means else, we simply want to keep the player direction. And with that, I can run all of this again. And now, no matter in what direction I am going in, the speed of the player is always going to be 300. I guess unless I stop moving, but you get the idea. And to actually see what happened, let me only print the player direction. With that, we are getting an X and a Y value. And if I move left or right, this is going to be 1 or -1, or 1 or -1 for X and Y. However, if I move diagonally, we are getting 0.7 and 0.7. Those numbers are changed because of normalization. And with these two numbers, the length of the direction is going to be 1. So I hope that part wasn't too complicated. Basically, if you want to have very simple keyboard input, you would use these 3 lines and then actually move a rectangle via this 4th line. Now, before we continue, let's have another look at the documentation. And there we have pygame.key and pygame.mouse. Inside of key, you can get all of the methods, and there are quite a few. The one we have used so far is getPressed. There's also getJustPressed and getJustReleased. You could get a few more, but they aren't too important. And besides that, inside of mouse, we have getPressed, getPosition, getRelative. You could also set the position, you can make the mouse invisible, or get if the mouse is visible, and so on. The most important methods in here are getPosition and getPressed. And to practice all of that, let's do an exercise. I want you guys to capture the input for the spacebar. If this one is pressed, print fire laser. On top of that, use the keyboard input to trigger it only once. And for that, do not use the event loop. You should figure this one out via pygame.key, meaning you will have to read the documentation at least a little bit. Pause the video now and see how far you get. Back inside of the code, I want to check. Let's do it after the player movement. If keys and pygame.k_space. If that is the case, I want to print fire, or fire laser, I think I called it. Doesn't really matter what you do in here. If I now run the code, I can press space and we're getting fire laser. The issue is we're getting this fire laser on every single frame of the game, which at the moment is 1,000 times per second, which really isn't ideal. I want to make sure if the player is pressing this button, we are only triggering fire laser once. And for that, let's have a look at the documentation. I want to look at pygame.key, and in there, first of all, the one list you should be familiar with is this one here. It contains all of the keyboard constants. Besides that, we have getPressed and getJustPressed. The difference between these two is that getPressed checks for buttons constantly, whereas getJustPressed is only getting the most recent key presses. Other than that, they work in basically the same way, which means I can get the recent keys via pygame.key.getJustPressed. And if I then use all of those keys with the same constant, I can run this again. And if I now press space and hold it, we are only getting fire laser once. Although I can press it again, and once again, we are only getting it once on every press of the key. So that is looking pretty good. And the other input is still working just fine. So that is all working pretty well. That being said, this logic still isn't ideal, because if I run the game again and I press space really quickly, we are still getting a lot of fire laser. So in an actual game, the player would be able to shoot way too many lasers. And for that, we are going to implement a timer later on. I think for now it's not too important. The actually important part for now is that you can get keyboard input, mouse input, either via dedicated methods or via the event loop. If you can do that, you can get keyboard input in Pygame. In this part, we are going to cover sprites, which are not going to change the game. So by the end of this section, the game is still going to look like this. However, we are going to organize everything significantly better. And that is all that sprites are doing. It doesn't sound like a lot, but once the game becomes even a bit more complex, you basically cannot do it without sprites. Let's talk about it. Basically, for any project, you want to be using classes. And by the way, if you don't have that much experience with them, check out my introduction to Python. This one covers classes in a lot more detail. At this point, I will assume that you know classes at least reasonably well. Now, in our case, the code is already becoming messy. For the player, we have a surface, a rectangle, some code for the movement, and some code for firing. So quite a few lines, even though the player doesn't actually do that much. It simply moves around and then prints when we are pressing fire. If the player was able to do more and we had other objects, the code would become incredibly messy really fast. So we have to organize all of this a lot better using classes. And for that, we can use a sprite, which is the best way to use classes in Pygame. Not the only one though, but it's essentially the default. Basically, a pygame sprite is an inbuilt class that always contains a surface and a rectangle. And that is literally it. It's just a class with a surface and a rectangle, and then you can add anything else that you need. Or in other words, for a sprite, we have a pygame class called pygame.sprite.sprite. And from this class, we are going to inherit. After we are doing that, we have to override self.image, which contains the surface, and self.rectangle, which contains the rectangle. Only then is the class going to work properly. Let's try all of this in practice. Here we are back in the code, and I want to create a class all the way in the top. This one is going to be the player. And for inheritance, we need parentheses and then pygame.sprite.sprite. After that, we will need a dunder init method, which is going to run as soon as we are creating one instance of this class. And in this dunder init method, we always need self. And after we have this method, we have to do three things. The first one is, like with any other inheritance, we have to call super dunder init to initialize the parent class. After that, for a pygame sprite, we will need self.image and self.rectangle. The image is going to contain the surface that we want to display. Or in our case, we want pygame.image.load and player.png, along with convert alpha. For the rectangle, we want to do basically what we have done down here. So let me copy it. We want to get the player surface and then get f rectangle and place the player in the middle of the window. The only difference now is that we don't have a player surface inside of this method. What we have is self.image. This one actually stores the surface. And with that, we have a very simple pygame sprite that contains a surface and a rectangle. Although if I am running the code now, nothing is going to change. We can still see the player, but that happens because we get all of this stuff, which I don't want anymore. So I'm going to comment it out. And then we are doing all of this, which I also don't want anymore. And I also don't want to display the player using the blit method. If I now run the code again, we can only see the meteor, the background, and the laser. So to use the pygame sprite class, first of all, we have to create one instance of this class. Let's do it where we used to have the player. I want to create a player variable and then one instance of the player class. After we have that, at the end of the game loop, I want to call display surface.blit, and we could get player.image and player.rectangle. If I now run all of this again, you can see we have a player ship. Although at the moment it doesn't do anything because we do not capture any kind of input, which we are going to reintroduce in just a second. First of all though, this is not the proper way to display a sprite. Let me remove it right away. Instead, let's talk about it in a bit more detail. To display a sprite, you could use surface.blit with sprite.image and sprite.rectangle, although that is not a good approach. What is much better is to use a pygame group. And for that, we are going to need a bit of theory. So, for a sprite group, we have the basic issue that in a proper game, we want to display dozens, if not hundreds of sprites. And pygame sprite groups are designed around that. They can do three things. They can draw all of the sprites, they can update all of the sprites, and they can organize the sprites. For drawing, we simply get the group and then draw on a surface. and this is going to draw all of the sprites on that surface. This would work with hundreds, if not thousands of sprites, which is much easier to use than calling surface.blit 1,000 times. Besides that, we have group.update, and we could pass in any amount of arguments in there. This would call an update method on every sprite inside of that group with those arguments. And finally, you can also loop over sprites to use them in other methods. So for example, in just a bit, when we are creating the meteors, we are going to place each meteor sprite into two groups, one to display them and one to organize them. That way we always know when we have a meteor sprite. Although first of all, let's create a single one for the player. Before we are creating any sprite, I want to create a sprite group that I call all sprites, because we're going to place every single sprite in there. To create a group, we need pygame.sprite.group. And then, when we are actually running the game, so in the while loop, we want to get that group, all sprites, and then we have a draw method and an update method that can accept any amount of arguments. For now, let's simply work with the draw method. And we want to draw on the display surface. That is a start, but if I run the game, we still cannot see the player. That is because when we are creating the player, we are not attaching it to the sprite group. And to fix that, we can go in one of two ways. Number one, after we have created one instance of the player class, we can get all sprites and then use the add method and add the player to it. If I now run all of this, we can see the player. However, this isn't usually what you see because it's, well, an unnecessary line. What is much more common, when you are creating a sprite, you are passing in the groups that you want this sprite to be attached to. After that, when you're calling super dunder init, you can pass the groups in there. That way, this sprite will be added to this group automatically when we are creating the sprite. As a consequence, we don't need this add method anymore, but we do have to add all sprites to the player class when we are creating one instance of it. With that, I can run all of this again, and we can still see the player. Besides that, what we can do before we are calling the draw method, in fact, before we are drawing anything inside of the game, I want to call all sprites dot update. For now, without any arguments. And also, this recent keys should be commented out. By the way, I am fully aware that the code is starting to get a bit messy. We will clean this one up in just a bit. First of all though, before you're drawing anything, call allsprites.update. This is going to call an update method on all of the sprites inside of this group. Now in our case, the player doesn't have an update method, which means if we are running the code, nothing is going to happen. However, if I am adding an update method to the player, for now only with self, then I can print ship is being updated. And if I now run all of this again, we are getting ship is being updated, which means this update method is running just fine. And in turn, that means we can recreate all of this logic. That part is actually going to be your exercise. I want you guys to recreate the player movement logic inside of the player class. And for all of this, the code shouldn't really change all that much. You just have to adapt it to use it inside of object-oriented programming. Pause the video now and see how far you get. I suppose we should start by cleaning things up just a bit. First of all, we don't need this comment down here anymore, and also we don't need the input inside of the event loop. And after that, I want to cut out all of the stuff we have commented out and then paste it below the player class. With that, inside of the update method, we first of all want to get all of the keys. After we are getting that, we want to update the player direction. Although at the moment, player direction doesn't exist inside of this class. To fix that, I want to create another attribute self.direction, which by default is simply going to be a pygame.vector2 without any values. After we have that, I can copy those 2 lines, paste them in there, and clean all of this up. The only change that we have to make is that this should now be self.direction.x and self.direction.y instead of player direction. Also, at this point, we have to make sure that we are normalizing the vector. That is going to happen in just the same way. Instead of player direction, we want to have self.direction.normalize. If we have a self.direction, if that is not the case, we want to keep self.direction. And then finally, I want to get the actual movement for the player, which is player.rect.center plus equal direction, speed, and delta time. Most of this doesn't exist anymore, but let's go through it step by step. The player rectangle now is self.rectangle.center. Then we are getting self.direction, and that we want to multiply with self.speed. This self.speed doesn't exist at the moment, so we can create it inside of the dunder init method. Self.speed is going to be, I believe it was 300. Yeah, 300. That's a really good start. And also at this point, we do have delta time, because delta time is in the global scope, so we can use it inside of the class. Which means at this point, if I run the game, we can move the player around, and this is looking really good. Now, that being said, you shouldn't have stuff in the global scope. It's just not good practice. So what is a much better way of handling all of this is when we are calling the update method, we are passing delta time in there. And then inside of the update method, we have to add 1 parameter to capture it, which we can also call delta time. The end result, though, is going to look exactly the same. Besides that, we also have to recreate this logic. I think at this point, this shouldn't be too hard anymore. We simply want to get all of the recent keys and then check if recent keys pygame.kspace is pressed. And if that is the case, we want to print fire laser. With that, we don't need the comments anymore and run the game. If I press space, we're getting fire laser. So that is working just fine. And with that, we have a player sprite that is getting quite a bit more complex. If I now minimize it, and we don't need this stuff for the player anymore, if you now look at the actual game loop, to display and update the player, we simply have to call allsprites.update with delta time, and then allsprites.draw on the target surface. Later on, we are also going to create meteors and lasers dynamically, which means at this point, we can remove those 2 lines, which is cleaning up things quite a bit more. And finally, when we are creating the stars, at the moment, we are importing a star surface, and then we are getting 20 random positions. After that, we are using another for loop to displaying all of them in the actual game. That we can also simplify by using a sprite. Which means I want to create another class, let's call this one star, which also needs to inherit from pygame.sprite.sprite. And by the way, this part could be your exercise as well. I want you guys to create 20 star sprites and display them on the screen in random positions. So the end result will be the same, but the code should be much more organized. Pause the video now and see how far you get with this one. First of all, we want to call a dunder init method, where we have self and we have the groups, like we have done for the player. So in there, we also had dunder init with self and groups. After that, what you should always remember is to call super dunder init with the groups. Besides that, we will need self.image and self.rectangle. For the image, I want to have the star surface. Let me cut it out actually. And then we will need a rectangle. And this is going to be a bit different compared to what we have done in the original. When we created the star positions, we used list comprehensions to create 20 x and y tuples using rand_int. That was necessary because we had to create all of the positions before we are running the game. If we created all of the random values inside of the game, they would update on every frame of the game, which wasn't ideal. But now we don't have to do that anymore because we are going to create all of the stars before the game is running anyway. So for self.rectangle, we can simply get self.image.getFrectangle and then set the center to an XY tuple. And those values we can copy. For X, I want to have random integer from 0 to the window width, and for Y, I want to have a random integer that goes from 0 to the window height. After that, we don't need these two lines anymore. Also, that's basically it for the class. Now we have an image and a rectangle. And now to actually create the stars, I want to use another for loop for I in range 20. And then create one instance of the star class with the groups. In our case, we only have a single one, all sprites. Once we have that, we don't need the for loop inside of the game anymore. And that's basically it. The stars are still going to be drawn via the draw method of the group. So I can run the game, and we are still getting stars and the ship is moving, although there are two things we have to refine. The first one is that now the ship is below all of the stars. That is happening because we are creating all of the stars after the player. And inside of a group, all of the sprites are being sorted by the time of their creation. The later a sprite is being created, the later it will be drawn. Or in other words, if we are creating the player after the stars, I can run the game again, and now the player is on top of the stars, which looks a bit better. On top of that, we can optimize the entire thing, because when we are creating one star, we are always importing a surface. And since we are creating 20 stars, we are doing 20 imports. But well, we are importing the same surface 20 times, which is not efficient at all. So what would be much better here is to import the surface before we are creating the star. Let's call it star_surface. And then we are only importing it once. After that, when we are creating the star, I want to pass this surface in there. This should be the star surface. After that, when we are creating the star, inside of dunder init, I want to have a surface, and this surface will be assigned to self.image. That way, we are only doing a single import and then using the same surface 20 times, which is significantly more efficient. Generally, importing anything is quite hardware intensive, so you ideally want to do all of that in the beginning of the game and then reuse the surfaces. Although now, if I run the game, we're getting the same output. So in practice, since our game is really small, this isn't going to make a difference. And with that, we have a player class and a star class, and inside of the actual game, you can see this is becoming significantly more organized. We have one part where we are updating all of the game, and then another part where we are drawing everything. Besides that, we have delta time and the event loop, but that's basically it. Via a sprite, you can organize your game significantly better. And as soon as you have even slightly more complex projects, this will become a necessity. And going forward, I will be using a lot more sprites. So if you struggle with classes more generally, definitely check out some kind of introduction to them. It's going to be really important. The next important part is going to be working with time. Via those, we can create meteors and control the laser spawn time. Let's talk about it. In our case, we want to use time in two ways. Number one, we want to create a timer that triggers every X amount of seconds. And number two, we want to have a cooldown timer for the laser. Ultimately, those need two different approaches. For the first timer, we want it to run continuously and then trigger within a certain interval. Although for the laser, we want to have a timer that starts whenever we want and then runs for a certain amount of time. To create these two timers, first of all, the interval timer, or a timer that triggers every X amount of seconds. This we can create with an inbuilt pygame tool. We basically create a custom event and then set a timer for that event. Once we have that, we can capture that event in the event loop like any other user input. For the custom timer, we would have to rely on a pygame method that captures the time, or more specifically, the time since the game has started. And that we can use to create a custom timer. Basically, all that we are going to do is we are capturing a starting point and then measure the time that has passed since that starting point. If the difference between these two numbers is large enough, then we want to run some code. And then we have a custom timer. None of this should be terribly difficult, so let's jump right in. I want to start by creating another section. We can do this one all the way at the bottom before the while running loop. And there, I want to create custom events. Or to be a bit more specific, I want to create a meteor event. So a timer that triggers twice a second, and every time it triggers, it creates a meteor. For that, first of all, we will need a custom event that I want to store in a variable called meteor event. And to create this one, we want pygame.event and then custom type. This is going to create a custom event. And once we have that, we can use pygame.time.setTimer. For this one, we will need two arguments. Number one is an event that we want to trigger, which in my case is going to be the meteor event. After that, we will need a duration in milliseconds. If you add 500 in here, you would have a duration of half a second. And with that, we have created a timer. The way we are going to use that is inside of the event loop. We have to check for if event.type is equal to a meteor event. If that is the case, I want to print create meteor. Let's run all of this, and in the bottom of the window, we can see create meteor every half second. And that runs continuously, so it's looking pretty good. Perfect. And well, that's basically all you need to know to create an interval timer. It doesn't get any more complex. So that would be the first kind of timer. Besides that, inside of the player. At the moment, we are printing fire laser every time the player presses a button. Or in other words, if I comment out this line and run the game, every time I press space, we are printing fire laser. And this happens as fast as I can press the button, which shouldn't be the case. There should be some kind of delay between different laser shots. So we have to create a timer inside of the player class. And essentially what we want to check, if this is the time of the entire game, where we start on this point, and this is basically infinity. We want to check if the player has shot at this point in time, let's say after 1 second, then we want to wait for, let's say, 0.4 seconds. Only after that point has passed can we shoot again. To implement that logic, we will need a couple of attributes. So let me create a timer, or rather a cooldown section. We want to have, first of all, self.can_shoot, which by default is going to be true. Besides that, I want to have a self.laser_shoot_time, which by default is going to be 0. And finally, self.cooldown duration, which is the length of the cooldown, in my case, 400 milliseconds. And the way we are going to use that, first of all, if the player presses the space button, we want to add a second condition, and self.canShoot. By default, canShoot is true, so this one is not going to make a difference. However, once we are running this if statement, I want to set self.canShoot to false. With that, if I run all of this again, I can press space and we can only ever shoot a single laser. For the obvious reason, once we have shot a laser, canShoot is false, so this if statement is never going to trigger. To account for that, I want to create another method. Let's call it the laser timer. No need for custom parameters, and in there, we basically want to check, first of all, if not self.canShoot. We only want to run any code in here if the player currently cannot shoot. And then we want to get the current time, which we can get via pygame.time.getTicks. This will get you the amount of time that has passed since the start of the game in milliseconds. Or to be a bit more specific, the time since we have called pygame.init. Just to demonstrate, if I print that current time, and then also we have to make sure that we are calling self.laser timer. If I now run all of this, I can press space and we're getting the time and it's increasing. So that is working pretty well. So with that, we can get the time continuously. Besides that, we will have to know when the player shot the laser, which happens inside of this if statement. And to get that, we want to get self.laserShootTime and use pygame.time.get ticks again. Now at this point, you really have to understand that this if statement is only triggered once, whenever the player shoots a laser. However, this define laser timer, or more specifically this current time, is being run continuously. Because of that, we can check one point in time, and after that check how much time has passed. Combined, all that we really want to do is if current time minus self.laser shoot time is greater or equal to self.cooldown duration. If that is the case, we want to set self.canShoot back to true. And that should be all. If I now run the game, I can press space, and even if I press it really fast, we only get it every 400 milliseconds. To test all of this a bit better, let's change the cooldown duration to 2000 or 2 seconds. I can now press space as fast as I want, but we only get fire laser every 2 seconds. And let me go over the logic really quickly. This is the timeline of the game, where we start with pygame.init, this would be point 0, and then the game could run as long as we need it to run. If the player presses space, then this if statement is going to trigger, and we are capturing one point in time. Let's say in here, and this could be 1200 milliseconds since the start of the game. At this point, we are only capturing once. After that, we are calling define laser time continuously, which means this current time increases. It would first be here, then it would be here, 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 and so on. This number keeps on growing. After we have that, we are checking this line, where the current time minus the laser shoot time is greater than the cooldown duration. Or in other words, our cooldown duration would be 2 seconds. We would be roughly at this line. And via this if statement, we simply check if we are exceeding this point or not, which at some point is going to be the case. And that is it. With that, you can create a custom timer. And also this covers the two approaches to time in Pygame. If you understand them, you can create basically any kind of timer. And later on in this video, we're going to use this kind of logic to create a much more powerful timer. But that's going to be a topic for later. For now, I want to use the timers. Meaning I want to create a laser and then a meteor. And let's start with the laser, although both of these classes are going to be fairly similar. I want to create a class laser, which has to be a pygame.sprite.sprite. In there, as always, we want to have a dunder init method with self. We want to have a surface, a position, and then the groups. We will need groups to assign it to a sprite group, the position to place the laser in the right position, which is going to be in front of the player, and then the surface we want to import first of all and then reuse every time we are creating a laser. You do not want to import every time the player shoots. Fortunately, we already imported a laser surface, so that part is quite easy. Although we don't need the laser rectangle anymore. After we have that, inside of the dunder init method, I want to call super.init and pass the groups in there. After that, we will need self.image, which is going to get the surface. And finally, self.rectangle will be self.image and get f_rectangle, where we want to place the mid-bottom. This one is going to get the position. The way you want to think about this one is that this will be our player, and we want to create a laser right in front of it. which means from the point of view of the player, the laser should be in the mid top. But from the laser's perspective, we should be placing the mid bottom. Anyway, with that, we have a laser class. So now, every time the player presses space, we don't want to print laser anymore. Instead, we want to create one instance of a laser, for which we will need a surface. That would be the laser surface. Then we will need a position, which is going to be self.rect.midTop. And finally, for the groups, we only have a single one, all sprites. I can now run the game, and every time I press space, we can create a laser. Now at the moment, the cooldown for the laser is really, really large, so we are only creating a laser every 2 seconds. Let's change that part right away. This should be 400. If I now run all of this again, we can create a laser at a much more reasonable pace. Cool. That covers creating the laser. Besides that though, we also want to make sure that the laser is moving, for which we will need an update method with self and delta time. Basically all that we want to do is self.rect.center minus equal some kind of speed. For now, let's say 400. And this we want to multiply with delta time. Also, this should be center Y. We only want to move 1 point. I can now run all of this, and we have a laser that is moving. So that is looking really good. With that, we basically have a laser. Wasn't actually that difficult. Now at this point though, you do want to be careful. If the game runs long enough, we will have a huge amount of laser sprites. They are not going to be visible, but they will still exist. Hence, they take up some processing time, which could become very inefficient. For this game, it's not going to make a difference because the game is, well, really simple. But for a more complex game, this could actually be an issue. So what we want to do, if this is the window of the game and we have the player somewhere in there, if the player is shooting a laser and the laser passes the top of the window, i.e. we are exceeding this point, then we want to destroy the laser sprite. That we can do with if self.rect.bottom is smaller than 0. Then we know the laser is above the window, so it's not visible anymore. If that is the case, we can destroy the sprite using the kill method. Now, in the game, this is not going to be visible. Although I guess I could demonstrate this, we want to check if self.rect.bottom is smaller than 200. If that is the case, the laser is simply going to disappear at this position. So you can tell it is working. In my case though, this one should be 0. And with that, we have a proper laser class. Next up, we want to create a meteor, which is also going to be pygame.sprite.sprite. And this part is going to be your exercise. I want you guys to create a meteor on every meteor event. On top of that, I want you guys to destroy the meteor sprite after 2 seconds. Or in other words, create a timer inside of the meteor and start a timer once the meteor has been created. First of all, we will need a dunder init method, where we have self, a surface, a position, along with the groups. Next up, super, don't forget to call this one, and then dunder init, where we pass the groups to the parent class, and then we will need self.image and self.rectangle. The image we're going to get from the surface, i.e. the parameter. And then the rectangle is going to be self.image.getFrectangle, where we are placing the center in the position that we are getting from the parameters. And just as a reminder, we are already importing a meteor surface, although at this point we don't need the meteor rectangle anymore. And looking at all of this, I think we can organize things just a bit better. We are not using the plane surface anymore. This one can go entirely. Instead of that, I want to have an import section where we are importing the star surface, the meteor surface, and the laser surface. After that, we are creating a whole bunch of sprites, and then we have the custom event. And before that, we are doing the general setup, which I think overall feels much cleaner. All right, now we have a meteor. But this is not going to be visible in the game, so we have to make a few more changes. Most importantly, every time the meteor event triggers, I want to uncomment all of that. Then we want to create one instance of the meteor class, which means meteor, and we have to pass in a surface, which is going to be the meteor surface. Then we will need a position, and for now, let's simply say 400 and 500, two entirely random numbers. We will change them in just a second. Besides that, for the groups, all sprites. If I now run the game, we are getting a meteor, and since this one is always in the same position, we are not going to see much of a change. But at the very least, it's working. So we need to customize these numbers. Or in other words, we want to have an X and a Y number. Both of those should be random. For X, I want to have a random integer between 0 and the window width. For Y, for now, I want to have a random integer that goes from 0 to the window height. Or in other words, at the moment, we are spawning a meteor somewhere on the window. Let's try that. And there we are getting meteors all over the window. That part is working really well. At this point, we can also make the meteors move, which we are doing via an update method, define update with self and delta time. All that we want to do in there is self.rect.center y. And to this, we want to add some kind of speed, let's say 400 multiplied with delta time. I can now run all of this, and we're getting meteors that are moving down. So that's a pretty good start. The reason why this is looking weird is because we are creating the meteor right in the middle of the window. So the player can see when the meteor is being created. To avoid that, when we are setting the Y position, we want to be on top of the window. Or in other words, we want to be in a position randomly between negative 200 and negative 100. Let's try off this again. And now this is looking quite a bit nicer. The game is definitely coming together. Although, that being said, we can customize the meteor class just a bit more. There are two things I want to do in there actually. Number one, and this was part of the exercise, so let's start with it. We want to destroy every meteor sprite after 2 seconds. Or in other words, we want to have self.start_time, which is going to be pygame.time.get ticks. That way, we know when the timer is supposed to start. We can also set a self.lifetime, which is going to be 2000 milliseconds or 2 seconds. After that, inside of the update method, we want to check if pygame.time.get ticks minus self.startTime is greater or equal to self.lifetime, and if that is the case, we want to kill the sprite. Let's try all of that, and I think the meteors shouldn't reach the bottom. And there you can see they disappear slightly before, which was intentional, so you can see it's working. For the actual game, we probably want to go with 3000, so the player cannot see a meteor disappearing. And that part is looking pretty good, so I am quite happy with that. Now, you might be wondering, why aren't we using the laser logic, where we are simply checking if a laser is above or below a certain position, and then we destroy it. For example, for the meteors, we can check if a meteor is below the bottom of the window. And well, you could do that, it would actually be more efficient. I simply wanted you guys to practice timers a bit more. This approach is actually better, although you should be familiar with both of them. Anyway, with that, we are destroying a sprite after a certain amount of time. Besides that, at the moment, the meteors are always going in a straight line, which isn't ideal. I want to give each meteor a direction, which is going to be a pygame and vector2, for which we will need x and y. Now y is always going to be 1, we always want to go down at the same speed. However, for x, I want to have a random value, and that should be a floating point value, because we want to stay below 1. For which we are going to need another part from random. This one is called uniform. And uniform works quite easily. We want to specify 2 floating point values. We want to start at negative 0.5 and then go to 0.5. After we have that, when we are updating the position of the meteor, we want to get a tuple position, center is totally fine, and then get self.direction multiplied with self.speed multiplied with delta time. Now self.speed doesn't exist. Let's create it, self.speed, and this could also be a random integer. Let's say between 400 and 500. With that, the game is going to feel much more organic, and this is looking pretty good. So very happy with that. Later on, we are also going to rotate the meteors, which is going to make things look even better. But for now, I think we have made some pretty solid progress. To actually create a game, we will need collisions. So by the end of this section, we can check if a meteor hits the player, or if the player hits a meteor via a laser. Once we have all of that, we basically have a game. Now, collisions in Pygame you can do broadly in 2 ways. Number 1, you can use rectangle collisions. A rectangle can check for collisions via a single point, another rectangle, or a list of rectangles. Besides that, we also have sprite collisions. Mostly what you're doing in there is you are checking the collisions between a single sprite and sprites inside of a group. Although there are quite a few variations. For all of that, you want to look at the documentation. Here we are, and to get started, you want to look at rectangles. If you scroll down just a bit, you can see all of the collision methods. I guess we can start up here. The first one would be contain. This one checks if a rectangle is inside of another rectangle. Then there's collide point, and this one checks if a point is inside of a rectangle. After that, we have collide rect, a really common method. This one checks if there's an overlap between 2 rectangles. And just in case you're wondering, contains means that a rectangle has to be entirely inside of another rectangle for this to trigger, whereas collide rectangle simply needs a simple overlap. And well, then we have a few more methods, but I think they're all fairly straightforward. So if you click on one of them, let's say collide rect, you can see what Pygame is expecting. We need a rectangle, and then we are calling collide rect, and pass in another rectangle. The return value is going to be Boolean, so either true or false. And they basically all work in more or less the same way. Anyway, besides that, we can look at the sprites, which I haven't shown yet, but they live in this section, under sprite. And there you can create a pygame.sprite.sprite. And if you go just a bit further down, we can see all of the collide methods. By far the most common one is sprite collide. Besides that though, we have collide rect ratio, collide circle, and a few more. Later on, we are also going to use collide mask, but this one we haven't covered yet. For now, I only care about sprite collide. This one, at the minimum, wants to have 3 arguments. A single sprite, a group of sprites, and then do kill. We basically check all of the sprites inside of a group, and if any of those sprites collide with the single sprite, then we are storing those inside of a sprite list. That's the return value. And do kill means that we are going to run the kill method on a sprite that is colliding with the single sprite. And well, that is basically it. Here we are, and I want to start by creating some rectangle collisions. Although for a real game, you want to use sprite collisions, simply because you are going to work a lot with sprites. But you should be able to handle both. Anyway, at the moment, we have a player, and in there, we have a rectangle. That is what I'm going to use for now. Which means, inside of while running, I can check, and let's add another section here, test collision. I want to get player.rectangle, and then use collide, any of those methods, and for now, collide point. This one is checking if the rectangle is colliding with any point meaning we have to specify an x and a y point. For example, in there, we could add 100 and 200. And that I want to print. Let's try all of that. And by default, we are getting false. But if I move to one point up here, we are getting true. So this part is working quite well. Although I suppose it's very hard to see. Something that you could also do is use pygame.mouse.getPosition. That way I can show my mouse, and by default we are getting false because the mouse is not colliding with the spaceship. However, if I hover over it, we are getting true. So this is also working just fine. Another method that you do see very often is collide rectangle. For this one though, we are going to need another rectangle. Let's create one before we are running the game. I want to have a test rectangle, which we are going to create via pygame.frect. And by the way, frect or normal rectangle doesn't matter for rectangle collisions. They all work in the same way. For this one, we want to have a left, top, width, and height. Let's say the left could be 0, the top could also be 0, and then the width will be 300, and the height will be 600. That means if this is our window, the test rectangle is going to be roughly capturing this size. And that we can check for inside of the game. I want to check for playerrect.collideRect with the test rectangle. If I now run the game, we get false by default, but if I go to the top right, we're getting true. And then I can go outside of this area and we're getting false again. So that is working pretty well. And that is basically all you have to do for rectangle collisions. They don't really get that much more complex. Although there's one important thing you should keep in mind. When we're talking about collisions in Pygame, we don't really talk about collisions. Instead, Pygame only really checks overlaps, i.e. if one rectangle overlaps with another rectangle. But that is never going to change the position of either of those rectangles. Meaning, if you want to have a game and the player is constrained by a wall or a house, this would require extra logic on your part, something we are going to work on in the next game. It's not terribly hard to do, but you do have to make it yourself. Just keep that in mind. Anyway, with that, we have rectangle collisions, meaning we don't need this test collisions anymore, and we can also get rid of this test rectangle. Next up, we can work on sprite collisions, which are going to be much more useful. And for now, I want to check if a meteor is colliding with the player. For that though, we have a problem, because at the moment, all of our sprites are in a single sprite group, which makes it really hard to separate all of them. For that, I want to create another sprite group. Let's call it meteor_sprites, which is going to be pygame.sprite.group. The same thing we have done before. And then, when we are creating a single meteor, instead of adding a single group, we want to have two groups, all sprites and meteor sprites. And this is totally fine to do. We are going to have all sprites for the update and the display part. And then the meteor sprites are going to be used to classify all of the meteors. Or in other words, when we are working with a sprite, we know what we are working with. Besides that, we also have the player inside of a separate variable. That way we can always identify the player. And by the way, so far I haven't really talked about it. But when you are creating a sprite, you are getting a return value of that sprite. So you can reference it via a variable. But you don't really have to do that. For example, when we are creating a meteor, we're not storing it inside of a variable. We are simply attaching it to a group and then call it a day. Both approaches are totally fine to do. Now, attaching a sprite to a variable is something you only really want to do when you want to reuse that sprite a lot. Or rather, when you want to get very easy access to it, which we do want to do for the player, but for the meteor, we don't really need it. Anyway, after we have that, before we are drawing the game, still inside of update, we want to check for collisions, which we can do with pygame.sprite.spriteCollide. This is the most important sprite collision method, and in there, we have to specify 3 arguments at a minimum. The first one is a single sprite, which in my case is going to be the player. Besides that, we want to check a group of sprites, which is going to be our meteor sprites. And finally, we have do kill. Or in other words, if any of the sprites inside of meteor sprites is colliding with the player, do we want to destroy that sprite that has collided? For now, let's say this one should be false. And after we have that, I can print the return value. If I now try all of this, by default, we have an empty list. But once there's an overlap, we get a value inside of that list. So that part is working pretty well. Now, so far, we only ever get a single value. But if I manage to overlap with two meteors, we would have two values. I suppose what we could be doing for the meteor event, I want to change this to 50. That way, we're getting a whole bunch more meteors. And now you can see this list can contain many more values, as many sprites as we are colliding with. Or if you look at this, if the game isn't running, we're getting a collision with one meteor here, and if I scroll up a bit, at some point we should have multiple collisions. There, for example, we have a collision with two sprites. And if we set do kill to true, then we are getting rid of any meteor that is colliding with the player. So that is also working quite well. And keep in mind, what can sometimes be a bit confusing. If you set do kill to true, you are destroying the sprite. However, the return value is still going to give you access to that sprite for one frame. Or if I scroll up a bit, sometimes we do get a value. And this sort of logic can be really helpful. So after you have destroyed a sprite, you might want to do something else. For example, what you do see very often is that you don't want to print all of the collisions. Instead, you want to use an if statement to check if you have any kind of collision. If that is the case, let's say print collision. And this is still going to work even if we are killing the meteor on collision. And this can only work if you have access to the collision sprite. Or in other words, the return value of this cannot be an empty list once we have a collision. In fact, what you see even more often is that you assign the return value to a variable. Let's call it collision sprites. You are checking if collision sprites is truthy. And once you have that, you can get collision sprites and get the first item to get the collided sprite. So if I try all of that, we are getting the sprite that we are colliding with. So that part is working reasonably well. That is basically it for sprite collisions. The really important thing that you have to understand is that you can get access to a couple of methods via pygame.sprite and then the name of the method. Check the documentation for more details. And after that, you have to make sure that you have access to all of the sprites, which usually happens via either a group or by assigning a sprite to a variable. Collisions, or rather overlaps in pygame, aren't really that hard to get. Which means we can do an exercise. I want you guys to check for collisions between the lasers and the meteors, and then destroy both once there is a collision. For that, you would have to do a bit of creative thinking, see how far you get. And don't worry too much about it if you can't do it. This one is getting slightly more advanced. Either way, pause the video now and see how far you get. To check for the collision between the lasers and the meteors, we first of all need to get access to all of the lasers. And for that, when we are creating a laser, that happens on this line. We want to assign a laser to all sprites to display and draw it, and then we also want to have another group called laser sprites. This one doesn't exist at the moment, but we can create it quite easily. Below the meteor sprites, I want to have a laser sprites group, which is going to be pygame.sprite.group. With that, we have access to all of the lasers. So that's the first step. Next up, we want to check if any sprite inside of the lasers collides with any sprites inside of the meteors. And there we kind of have a problem. If you look at the documentation for sprites, you don't really have a method for that. I suppose we do have group collides, but this one simply checks if we have group 1 and group 2. We want to have a bit more detail. We want to check for every single laser. We don't want to check for the entire laser group, so we can't really use this method. However, what we can do is to loop over every single sprite inside of this group and then call sprite collide. Or in other words, inside of the game loop. We are currently checking if the player collides with a meteor. Besides that, I want to do for laser in laser sprites. That way I get access to every individual laser sprite. And once I have that, I can call pygame.sprite.sprite collide with the individual laser, then the meteor sprites, and do kill should be true. If I now run all of this and I press space, the laser is going to destroy all of the meteors. That part is working well, but it's not ideal yet. The laser simply destroys all of the meteor sprites, but that shouldn't happen. Once there's a collision, the laser should also be destroyed. For that, I want to get the collided sprites as a list and store all of the collisions. If that exists, i.e. if collided sprites, then I also want to get the laser and kill it. If I now run all of this again, I can shoot a laser and both the meteor and the laser disappear. Although that's a bit hard to see. Let's change the meteor spawn timer back to 500, and that way I can shoot at individual meteors and they disappear. So that part is working quite well. That being said, we should keep this game loop a bit more organized. So what I think would be a bit more elegant is to put all of this into a separate function. Which means below the classes, I want to define collisions. No need for custom parameters. And we basically want to cut out all of this and then call collisions. After that, inside of collisions, we have all of the code, although we would need to organize things a bit better. If I now run all of this, everything should still work just fine. And that is looking pretty good. And yeah, I get an overlap, I can destroy the meteors, quite happy. The last thing that I want to cover is that once a player is being hit by a meteor, we want to end the game, which in practice means we want to set running to false. Unfortunately, this we cannot do right away, so we couldn't simply set running to false because we would simply create a local variable inside of this function. Or in other case, if I run the game, the meteors do disappear, but the game doesn't end. As far as Python is concerned, we have a running variable inside of this function and then a global running variable. And those have nothing to do with each other. To fix that, we want to set global running. That way, those two connect. And then, if the player collides with a meteor, the game is simply over. Although, that being said, this approach isn't ideal because you want to avoid having global variables. For now, I think it's fine because we are just getting started, but for the next game, we are going to approach this slightly differently. But anyway, with that, we have collisions. At this point, we basically have a game. That being said, we can make all of this look significantly nicer. And for that, we are going to display a few more things. And also, we're going to work on the color. So by the end of this section, we have a much nicer looking game. There are two major things that I want to cover in this bit. Number one is displaying text, which is actually fairly straightforward. You first of all have to create a font object, which means you have to define a font style and a size for the font. After you have that, you can simply use this font to render some text, and then you get a surface. And that surface you can use like literally any other surface. The only difference is that this surface has some text instead of an image. But that's literally it. Besides that, we can draw things. And for that, Pygame has a draw module, which lets you, for example, draw rectangles, circles, lines, and pretty much any kind of shape. So those are going to be the two major topics that we are going to cover. Let's start with some text. Back inside of the game, we have to, first of all, let's do it under import, create a font. And this we do with pygame.font.font. Make sure that you are spelling the second font with a capital F. We will need a font and a font size. For the font size, we could go with 20, and by default, a font can also be none. Then we are using a default font that looks pretty bad, but it gets the job done. So with that, we have a font. After that, we can use font.render to create a surface. And this will need 3 arguments. The first one is some kind of string with a bit of text, whatever you want to render. Then we have anti-alias, for which we will need a Boolean value. Anti-aliasing means that we are smoothing out the edges of a surface. Most of the time, you want this value to be true. Or in other words, you want to smooth out the edges of any kind of surface just a bit to make them look better. The only exception is pixel art fonts. If you anti-alias those, they are going to look really weird. Finally, we will need a color, and we will talk about colors in just a bit as well. For now though, I simply want to have a red. And this is going to give us a text surface, or just a surface that happens to have some text. And well, that is basically it. Once we have that, inside of the game loop, we could run display surface.blit with the text surface and a position, let's say 0 and 0. And then in the top left, you can see some text. That part is working pretty well. That is literally all you need for this part. Although, if you want to have a custom font, which you basically always want to have, you would have to import a font file. That fortunately we do have, because if you look under images, there's a file called oxaniumbold.ttf. TTF is a font file, and that we want to import, which we are going to do via the join method. I want to go to images and then import oxanium-bold.ttf. If I now run all of this again and you look at the text, it is looking quite a bit nicer, which is a good start, but the color doesn't really fit. Now you could go with white here, for example, and that would help, but ideally we want to have more control over our colors. And that we can do in Pygame, although I haven't covered it yet. So let's do it now. To create colors in Pygame, you can basically follow 3 approaches. The first one are the inbuilt color names, like a string green, red, blue, yellow, so on. You do have quite a few inbuilt ones. But those are still fairly crude. If you want to have more detail, you want to have either an RGB tuple or a hexadecimal value. To start with RGB tuples, those are simply a tuple with 3 values. The first one for red, the second one for green, and the final one for blue. And all of these values have to be between 0 and 255, with 0 being the absence of the color and 255 being the full amount of that color. For example, if we have 255, 0 and 0, then we are getting a pure red because we have no green or blue. If you have 0, 255 and 255, you're getting a light blue. Or in other words, you are mixing a full amount of green and a full amount of blue. Finally, if you have 200 for each, you're getting a grayish color. And that's basically it. Besides that, you have hexadecimal values, which always starts with the hashtag symbol. Then you have 2 characters for red, 2 characters for green, and 2 characters for blue. Now, the slightly confusing thing about those is that for each value, we can specify a value from 0 to F. Or in other words, we go from 0 to 9, and then we continue with A, B, C, D, E, and F. So for example, we could have values that look like this, where to get the full amount of red, we would have F and F. This might look weird, but in practice it means with a single value you can express a much greater range, and that's why we are using this. And well, that's basically it. All you have to understand about hex values is that we are using 2 values for each color, and we always go with red, green, and blue. Although in practice, you wouldn't do this by hand anyway. You would use some kind of computer system to give you the values that you need, and you simply select the color that you like. All you have to do for that is go to Google and then look for a color picker. Google even has an inbuilt one, and there you can select any color that you like, and then you're getting a hexadecimal value and an RGB value. Now there are a few more ways to express a color, but we don't really care about those. Hex values and RGB values is all we really need. Which means inside of the code, instead of white, I could specify a tuple with red, green, and blue. For example, a value here could be 200, 50, and 100, and we would get a purple-ish color. Not ideal yet, but we can work on it. Alternatively, what you could be doing Instead of a tuple, you can specify a string that starts with a hashtag symbol. Then specify 2 values for red, 2 values for green, and then 2 values for blue. Let's say 5, 5. That way, you would be getting another color that looks somewhat similar. Those are the 3 ways to express color in Pygame, or at least the ways you would be using most of the time. Besides that, if you look at the documentation, there is a whole color module, and this one gives you a lot more control over the color. Now, this could be incredibly useful, but in practice, I basically never use it. You simply don't need that much control over the color. But in some very specific projects, this might be useful. Now, in our case, I want to change the background color, which we are setting here. At the moment, this is dark gray, and this really doesn't feel right. Instead, the color that I want to go for is a hexadecimal value with 3A for red, 2E for green, and 3F for blue. If I run all of this now, we get something much better looking. And everything else still works just fine. And for the text, I guess instead of this random color, we could go with 255, 255, and 255, which arguably is a pure white color, so not that much gained. I suppose just to have something a bit more customized, we can set this to 240. So we're not getting a perfect white, which usually feels a bit too strong. But anyway, play around with this. At this point, you have all the tools to create your own colors. What I want to do instead is to display a score via text. Or in other words, this text surface shouldn't display a static word text, it should display the time since the start of the game. Meaning all of this needs to be dynamic. And this I want to have in a separate function. Let's call it define display underscore score. No need for custom arguments. And in there, first of all, we want to create a text surface. I can cut it out from where we used it earlier and then paste it in there. And the alias and the color can stay the same. But for the actual text information, we want to have a separate value. Let's call this one the current time. And we have already seen how to create this one. We simply want pygame.time.getX. Now this is going to return a number, but font.render always wants to have a string. And if you pass anything else in there, you are going to get an error. Which means in our case, we want to use str to create a string and then pass the current time in there. And well, that's basically it. Now we have a surface. So next up, we can create a text rectangle via text surface and get f rectangle. We want to place the mid bottom. For that, we will need x and y. X is going to be the window width divided by 2, and y is going to be the window height minus 50 pixels. That way, we are in the bottom center of the window. Finally, I want to get the display surface and then split the text surface along with the text rectangle. And with that, we have the entire score logic inside of a single function, which feels nice and clean. So after we have that, in the bottom of the game, after we are drawing everything else, I don't want to display the text surface. Instead, I want to call display score without any arguments. If I now run all of this, you can see we have a score in the bottom. Now I guess the text is a bit small, so what we can do about that is increase the font size. Instead of 20, let's go with 40, and that feels much nicer. Also, what you can do, you can display the score before or after all of the sprites. If you do it before, the player can be on top of the score, which I guess is a decent effect. I don't know, it's fairly subjective, just choose whatever you like. And if you feel like that the score is increasing too fast, you could floor divide this, for example, by 100, then it doesn't feel that strong anymore. Once again, this is fairly subjective, just choose what you think looks good. There isn't a universal answer for any of this. Anyway, with that, we have a score. Next up then, we can work on drawing things. And for that, we have to look at pygame.draw. If you look at the documentation, there we have draw. And there you can, for example, pygame.draw.rectangle, polygon, circle, ellipse, arc, line, lines, AA lines, and that's basically it. In case you're wondering, the difference between line and AA line is that we are anti-aliasing the line, which means an AA line is going to look a little bit less pixelated than a regular line. And to use all of that, let's do a couple of experiments. So after we are drawing everything else, I want to have a draw test. For that, we can use pygame.draw, and for now, let's start with line, for which we will need a couple of arguments. The first one is the surface to draw on. In my case, this will be the display surface. Then we will need a color. Since this part doesn't matter too much, let's go with red. Then we will need a start position and an end position. For the start position for now, let's go with 0 and 0, and the end position could be 500 and 600. After that, you can also set the line width. Let's go with 10. And now, if I run all of this, we have a random line on top of the game. That's kind of all we have to do in here. And you can see this thing is quite pixelated. Might be hard to see on YouTube, but if you run this on your own, you can definitely see it. If you don't like that look, you can change this to AA line. That way, you would be getting rid of the pixels, although AA line doesn't have a line width. So this we would have to get rid of. If I now run this again, you get a line that is looking a bit less pixelated, but since you cannot define the width, it's not terribly useful. Anyway, what is much more interesting, and let's go with line, so we can set a line width of 10. Instead of having a static point, you could also use pygame.mouse.get, and this should be get pos actually. If I now run this again and I can show my mouse, you can see that we can move both the ship and this line. It works just fine. I suppose what we could also do is layer.rect.center, and now we get a line to the center of the ship. That's kind of all you need for the draw method. Besides line, two things that you see all the time are pygame.draw.rectangle and pygame.draw.ellipse. Both work basically in the same way, actually. Let's start with the rectangle. For this one, we will always need a target surface, which in our case will always be the display surface. Then we need a color. Let's keep on going with red. And then we need a rectangle. In this case, we can use player.rectangle. If you simply run it like this, you are drawing a rectangle on top of the player. So this part is working fairly well. And if you change rectangle to ellipse, then pygame is going to draw an ellipse in this rectangular area. So those two methods are basically working in the same way. Although for now, I do want to work with a rectangle just a bit more, because you can specify a few more arguments, actually quite a few. The first one is the width. By default, it's 0, but if you set it to anything higher, let's say 10, then you are only drawing the border and you don't fill it anymore. Also, if you specify another argument, you would set a border radius. Let's go with 10 for this one as well. And then you have rounded corners. I think you get the idea. Drawing in Pygame really isn't that complicated, which means we don't need this draw test anymore. And instead, we can do an exercise. I want you guys to draw a box around the scored text. Also make sure that you are adding rounded corners. And for an extra challenge, add padding between the text and the rectangle. For that, you would have to look at the documentation. This one is a bit beyond what we have done so far, so don't worry if you can't do this extra part. But anyway, pause the video now and see how far you get. Back in the code, I want to work inside of display score. In there, we already have a text rectangle. This is what we want to draw via pygame.draw.rectangle. We want to draw on the display surface. For the color, we want to go with the same color as the text. So 240, 240, and 240. After that, we will need a rectangle, which is going to be our text rectangle. Then we will need some kind of border width. Let's go with 5 for now. And we will need a border radius. I guess 10 could be going okay. Let's try all of that. And we are getting, well, we're getting something. This doesn't look ideal, but at the very least, we have a border around the score. But this we have to refine. So how can we add padding between the text and the border? And unfortunately, this we cannot do inside of the draw method. However, what we can do is mess with the rectangle. For that, I want to look at the documentation and then the rectangle. In there, you have a move method and you have an inflate method. Inflate simply grows or shrinks a rectangle. And you can specify an x and a y value, although a better name here would be horizontal and vertical size changes. Or in other words, if this is our rectangle, the inflate method would keep the same center point, but then expand it in the horizontal or the vertical axis. And if you add negative numbers, you are shrinking the rectangle. That's all you really do. Which means when we are drawing the rectangle, we don't want to have the text rectangle itself. We want to have text rectangle dot inflate. And for the numbers, let's say 20 and 30. If I now run this is already looking quite a bit nicer. So definitely an improvement. The issue is though, we have some text that has a bounding box like this, with the actual text being roughly here. The reason why we have this bottom stuff is because some letters go quite a bit further down, like a P for example. But for numbers, this isn't really going to be an issue. Which means in our case, we want to move the entire rectangle up by just a bit. And that we can also do. So essentially what's happening at this point, we have a text rectangle, and then we are calling inflate. And this is going to return another rectangle, on which we can call another method, which is the move method, which is going to return another rectangle that has been moved by an x and a y amount. Now x in our case is going to be 0. We only want to move up by a little bit. Let's say negative 10. If I run this again, and that is definitely looking better. I think this value should be a bit lower, and the inflate for y should also only be 20. And that is looking much nicer. I think the vertical inflate could still be smaller, let's say 16. Let's try it again, and well, we are heading in the right direction, but this is something you have to play around with. I think 10 is actually best. Yeah, that looks like a pretty reasonable amount. Once again, the numbers here are fairly subjective. So play around with this and choose whatever you think looks best. With that, we can draw text, we can choose custom colors, and we can draw random shapes. Things that are really important to make our game look better. Alright, in this part, we are going to finish up the space shooter. And there are a couple of things I want to work on. The easiest one is going to be sound. I don't think I have to explain this one. Besides that, we also want to transform the meteor surfaces and make them rotate. After that, we're going to add better collisions by using a mask, which is a slightly more advanced topic in pygame. And finally, we're going to add an explosion animation. If you add all of these things, you are making the game look quite a bit nicer. And let's go through the topics one by one. The first one that I want to start with is using a mask. First question here is, what is a mask? And well, it's basically an object that checks which pixels of a surface are visible. Invisible pixels will be black and visible pixels will become white. Or in other words, our player surface would become something like this. Which in itself doesn't seem terribly impressive. But via this system, you can do two things. Number one, you can get pixel perfect collisions because now we know which pixels have actual content. And besides that, you can create silhouettes, which is super useful to make the player flash, for example, or you could add an outline to a surface. And for more detail on all of this, you want to look at the documentation under mask. In there, you can get all of the methods and quite a bit more detail. And the most important method that you have to be aware of in the beginning is pygame.mask.fromSurface. That way, you are creating a mask from a surface. This is what you're using most of the time to create a mask, although it's not the only way. To experiment with all of this, let's have a look at our player class. At the moment, we have a single surface in here, and that is self.image, which is something that we can use. And let me add a section at the bottom for the mask. I want to create a mask, which I can do via pygame.mask.from_surface. And in there, we have to add a surface, which in this case will be self.image. And that by itself doesn't do anything. If I run the game, nothing is going to change. However, I can visualize this mask by turning it back into a surface. Let's call this one the mask surface. And this we get with mask and then dot to surface. That way we have turned the mask back into a surface, and that we can use to override self.image. I want to set this to the mask surface. And if I now run all of this, you can see what's going on. We have turned all visible pixels white and all invisible ones black. And that is what a mask does. And the way you are using this system most of the time is with collisions. Because right now, our collision object is a rectangle. Meaning if this is the outline of the ship, very roughly, then the actual collision shape would look like this. That is the rectangle that we have created. And on top of that, if we have a meteor, while the meteor itself is round, the collision shape of the meteor is also a rectangle. Which means if you have a meteor in this position, we still get a collision, even though visually to the player there was no collision whatsoever. Which for a game can be very frustrating, so this is something we want to avoid. To avoid that, we want to know which pixels of a surface are visible, and that we do via a mask. That is the most common way of using a mask. Besides that, what you could also do on this mask surface, if you were to hide the black pixels, then you would have a flash effect. And you can hide pixels of one color on a surface quite easily. For that, you want to get the surface, in this case mask surface, and then set a color key. Setting a color key means that you're making all of the pixels of one color invisible. In our case, this should be the black pixels. And if I now run all of this again, we have the ship in perfect white. This could be useful if you want to make an object flash after it got hit, which is something I am going to cover later, but for now, we don't really care about it. Instead, what we want to do is to get rid of all of the surfaces and then turn the mask into an attribute, meaning this should be self.mask. And this self.mask is another part of a sprite class. But if you add it, you can implement mask collision fairly easily. Although for that to work, we have to add a mask for all of the sprites, which ultimately is fairly easy. You will always need the same line. Let me copy it. Actually, for the star, we don't need that because they're not supposed to collide with anything. But for the laser, we will need self.mask. And for the meteors, we will need another self.mask. And that way, all of the collidable objects have a mask. So how can we use it inside of the collisions? For that, let's have a look at the documentation. We want to look at the sprites. If you scroll down there a bit, we have once again all of the collision methods. The one that we are already using is called sprite collide. And if you look a bit further down, we also have collide mask. And you could use both of them, although I would recommend sprite collide. If you click on that, so far we have used sprite, group, and do kill. But there is a fourth argument, collided. It basically means that we can specify in a bit more detail what kind of collision we want. And in there, we can look for a collide mask. You could also look, for example, for a circle or some kind of ratio, but those aren't too common. Besides that, if you go a bit further down, we have collide mask. And in there, we are calling pygame.sprite.collideMask and then add in two sprites. The return value is going to be an X and a Y position, which you can read more about here. Although this method we don't actually need, because back in the code, we can simply expand sprite collide by just a bit. For that, I want to add a fourth argument, pygame.sprite.collideMask. And that is literally it. If I now run the code, and this is going to be quite hard to demonstrate, but for example there, you can see I can dodge the meteors much better. And if we collide with them, it is a pixel perfect collision. And the same thing you could also do for the lasers, although for them I don't think it's very necessary, because lasers are essentially rectangular. So not much point adding a mask. And one thing that you generally want to keep in mind is that using a mask is very, very hardware intensive. If you do it for every collision, you are going to tank your performance pretty hard. And actually, while I'm recording this, I realized that when we are calling pygame.sprite.collideMask, we don't actually have to create a mask attribute inside of the class. Because if you read the documentation, then you can see that if a sprite has a mask attribute, we are going to use that one. Otherwise, we are going to create a mask from the image automatically. And since we want to use the image anyway, we don't need this line for any of the sprite classes. Sorry about that. Fairly minor mistake. Although I'm going to leave it in there for the player just so that you can copy it. Anyway, with that, we have a mask. Something slightly more advanced in Pygame, and if you want to know more about it, check out this dedicated video. In there, I cover masks in a lot more detail. Next up, I want to transform surfaces. Or in other words, I want to use pygame.transform to change surfaces. This is just another module in Pygame, and this one can, for example, scale, flip, rotate, blur, grayscale, invert, and quite a few more things to a surface. Once again, in the documentation, if you look at transform, you can find all of the options. A really simple one would be rotate. In there, we have to call pygame.transform.rotate, pass in a surface and an angle. And then the return value is going to be another surface. And the same logic applies to basically all of them. You pretty much always call pygame.transform and then a method and pass in a surface with a couple of extra arguments. For that, for example, when we are creating the player, we can once again mess with the image. And let me add another section, transform test. We could simply override self.image via pygame.transform and then one of these methods. The one I've already talked about is rotate. And in there, we first of all need a surface, which in this case is going to be self.image. And then we need an angle. Let's go with 90 degrees. And now if I run all of this, the ship is rotated 90 degrees. Besides that, another common method would be scale or scale to x. Scale to x is the simpler one. And there we simply want to have a surface, self.image. And with that, we have the player being twice as large. If you read up on the other methods, you can do basically anything. I guess what you can also do is use grayscale. That way, our ship is going to be black and white. Pygame.transform doesn't fundamentally get that complicated. There's just one thing that you really want to keep in mind. Transforming a surface can reduce the quality. This doesn't apply to all of the transform methods. For example, if you use grayscale, this doesn't really have an effect. But if you rotate something too often, then you are going to notice a loss in quality. But let's go through it step by step. If you rotate a surface once, you are going to lose a very minor amount of quality. This is so minor that it's never going to be visible. However, if you rotate a surface 1,000 times per second, then the quality is going to decay very fast and very noticeably. And let's do an example for that. Let's say I want to rotate the player's surface continuously. Or in other words, inside of the update method, I want to add another section, continuous rotation. I want to get self.image and then assign pygame.transform.rotate, then get self.image and then a rotation number. For that, under transform test, I want to have self.rotation, which by default is going to be 0. But before we are applying the rotation, I want to increase self.rotation by a small amount. Let's say 10, and don't forget to multiply it with delta time. If I now insert self.rotation into pygame.rotate and run the game, you can see that the game gets really weird. And in fact, the frame rate crashes as well. So this isn't ideal. If I change the rotation speed to 1, you can see a bit better what's going on. So there you can see the ship simply disappeared. And the basic issue is, for all of this, if this is the full rotation, where we start at 0 and then go in 360 degrees. At the moment, we are always jumping by a very small amount, and then use the new surface to jump again for another rotation. And we keep on doing that forever until the game crashes, which admittedly isn't too long. That is because every time we are doing this kind of rotation, we are lowering the quality and we are changing the surface a bit. And if you're doing this too often, you are getting some really weird behavior, which you absolutely want to avoid. And the way to avoid this is to only rotate a surface once, which kind of sounds weird, but basically what we are going to do. We are going to always keep the original surface, and from there, jump by a certain amount, and then display this new surface. However, on the next frame, we are once again starting on the original surface, and then simply rotate a little bit further, and then use the new surface. Since we always start from the original surface, we only ever have a single rotation, which is not going to affect the quality, or at least not in a noticeable way. To achieve something like that, we want to store self.image in some other attribute. Let's call it self.originalSurface. This is going to be pygame.image.load, the thing we have already done, and then for the image, I want to have self.originalSurface. After we have that, when we are assigning a new image, we are not using the image itself. Instead, we are using self.originalSurface. On top of that, let me change the rotation speed to something like 20. If I now run the code, you can see that we have a rotation and we are getting some loss in quality. So it is definitely visible, especially on this surface. Now, depending on what kind of art you have, this will be more or less visible. This also depends on the speed. If I change this to 100, then it's already looking quite a bit better. Although this still isn't amazing. You can see way too many pixels. And to fix all of that, we have to look at the documentation. In there, I want to look at transform and then have a look at the rotation methods. There are two that we can use. pygame.transform.rotate is what we have already used. This one rotates an image. Besides that, we have pygame.transform.rotozoom. This one does two things. It scales and rotates an image at the same time. On top of that, it applies a filter when it's doing that, which effectively means it smooths out the entire thing and gets rid of pixels, which for most graphics is what you want to do. It looks much better most of the time. Which means, back inside of Pygame, I want to pygame.transform.rotozoom, still use the original surface and the rotation, but then for the scale, we have to add a 1 in here to keep this value constant. If I now run all of this, the ship is looking significantly better. So this is what you would want to use most of the time, but it's not a universal thing. Very often rotate is what you actually want. This depends very much on your game, and you should experiment to see what works best. There simply isn't a universal answer. But for the ship, I don't actually want a rotation. So let me get rid of all of this stuff. We don't want to have any transform. And also we want to keep the original image with the surface. That way, that is looking pretty good. What we actually want to do is to rotate the meteors. That part is going to be your exercise. I want you to make the meteors rotate and also give them a random rotation speed. Pause the video now and see how far you get. When we are adding this surface, we want to store it under self.originalSurface. And this can get the surface, and you don't even have to change self.image, since we are getting the same surface for both of them. Other than that, I want to have self.rotation_speed, which can be a random integer, let's say for now between 20 and 50. After that, when we are updating all of this, I want to override self.image with pygame.transform.rotate or rotozoom. And for this one, I want to use a rotozoom to have a bit better quality. For the surface, we want to have self.originalSurface. And then we're going to need an angle, which at the moment we don't have. For that, I want to have self.rotation, which by default is going to be 0. And then before we are updating self.image, self.rotation plus equal self.rotation speed multiplied with delta time. Then we can pass self.rotation in there. For the scale, we want to keep 1. If I now run all of this, we have the meteors rotating, so that's not looking terrible. I guess what we could be doing is increase the speed. This could maybe be 40 to 80. Let's try it again. And yeah, that is looking a bit better, but we're getting some weird wobbly behavior. If you keep on looking at the meteors, they do move a bit weird. That is because we are changing the image, but the rectangle always stays the same. Which shouldn't be the case, because for this image, we now have new dimensions. We want to also override self.rectangle and assign it to self.image.getFrectangle and set the center to self.rect.center. Or in other words, we are creating a new rectangle with the same center position as the last rectangle. That way, I can run all of this again. The meteors are moving much more naturally, which feels quite a bit nicer. Perfect. With that, we have the meteor rotation. And that we can improve even more with an animated explosion. For that, we have to go through a couple of steps. First of all, we need to import a whole bunch of explosion images. After that, we have to create an explosion class. And whenever a laser hits a meteor, we want to create one instance of that class. This is then going to play an animation, and after the animation is done, the class disappears. Or rather, the instance of the class disappears. If you want to try this on your own, it could also be a really good exercise, although it's getting a bit more advanced. What I want to do is to create a new class animated explosion, which is also going to be a pygame.sprite.sprite. For that, we are going to need a dunder init method. And for that, we want to have a list of surfaces. I usually call that frames. I think that name makes the most sense, but it's basically a list of surfaces. Besides that, we want to have a position, and we will need the groups. Super.dunder init with the groups, and then we will need self.image and self.rectangle. Now the rectangle is going to be fairly simple. Self.image.getFrectangle, and we want to place the center at the position. But then we have to assign a surface to self.image. And for that, basically, we want to get frames and pick the first item. And I think I am jumping ahead just a bit. So let's have a look at the project folder. There we have images, and in there we have explosion, which is simply a folder full of images. We want to import all of them and then play them in sequence. After the sequence is done, we are going to destroy the animated explosion class. For that, though, we have to import all of these frames, and that is going to happen in our import section. I want to store all of the explosion underscore frames in a single list. And that we can do via list comprehension. Or in other words, when you're looking at the folder, we know the file name starts at 0 and then goes all the way to 20. And we're always working with a PNG file. Meaning we can do for I in range 21. That way we're going up to 21, but not including it. And this should be I for I in range 20. If I do this so far and print the explosion frames, then we're getting a list with the integers from 0 to 20. That is a good start, but not exactly what I want. Because what I actually want is to use the join method. We're going to images, then we're going to explosion, and in there, we want to have all of the file names. Or in other words, images, explosion, and then an f string, where we are using i.png. If I now run all of this again, we are getting a list with a whole bunch of paths. And that we can use inside of pygame.image.load. And also, don't forget to call .convert_alpha. The line is getting a bit longer, but I think it's still manageable. Fundamentally, we are not really doing anything complicated. We are simply running this pygame.image.load inside of a for loop. Let's try all of this again, and we are getting a list of surfaces. That is perfect. So with that, we can get one image, which is going to be the first item inside of frames. Next up, when we have a collision between the lasers and the meteors, besides killing the laser, I also want to create one instance of the animated explosion, for which we are going to need the explosion frames. The position is going to be the top of the laser, i.e. laser.rect.mid-top. And then groups is simply going to be all sprites. If I now run all of this and I can shoot at a meteor, we're getting the first frame of the explosion. Doesn't do anything at the moment, but we are getting there. So to create an animation, we basically want to change self.image and always assign a different index from self.frames. And that needs to run inside of the update method. And there we will need self and data time, just as before. We basically want to do something like self.image is going to be the frames and then some kind of index. And this index has to increase over time. For that, first of all, we have to store all of the frames inside of an attribute. That way we can access them in the update method. Besides that, I also want to have self.frame_index, which by default is going to be 0. When we are assigning self.image, I want to get self.frames, although you could also just use frames in there, and then self.frame_index. This we want to do when we are creating one instance of the class and in the update method. But then before we are doing that inside of update, we want to increase self.frame_index by a certain amount. Let's say 5, and also this needs to be multiplied with delta time. Now this is not going to work for 2 reasons. Number 1 is that when we are using indexing, we always need an integer, which by default is going to be the case. But remember, delta time is something like 0.0 something. If we multiply that with the speed, we are going to get a floating point value, which is not going to work with indexing. Which means when we are assigning the frame index, we want to convert this number to an integer. And that should actually work already, at least for a bit. If I now shoot at a meteor, you are getting an explosion, but then the game should crash. The issue we have is that the list index is out of range. Or in other words, this frame index continues indefinitely. But we only have a finite number of surfaces inside of self.frames. To fix that, you want to use the modulus operator along with the length of self.frames. Also, I want to increase the animation speed to make this look a bit better. If I now shoot at a meteor, you can see we have the animation playing forever. Now, in case you don't know what modulus does, it basically gives you the remainder of any division operation. If you had 10 modulus 3, you would get a 1, because the next clean division that you could be doing is 9 divided by 3. This one would get you a 3, but then we have a remainder of 1. Now in our case, the length of self.frames is 20, and self.frame_index can grow indefinitely. And if you did 10 modulus 20, you would get 10. However, if you did something like 25 modulus 20, you would have a remainder of 5. And that is exactly what we want, because we have gotten to 25, and this would not be in the original frames anymore. Instead, what we want is the 5th frame, or more specifically, we simply want to get rid of the 20 in the beginning and keep the 5. Understanding modulus in Python is incredibly important, so if you don't understand the logic here, definitely do some research. That being said, we don't actually want to use it, because if I run the game again, having the animation playing forever would look a bit weird. Instead, I want to check if self.frame_index is smaller than the length of self.frames. Only if that is the case, do I want to assign a new self.image. And for that, we don't need modulus anymore. If that is not the case, else meaning frame index is greater than the length of the frames, or in other words, the animation is finished, then we want to discard the sprite. With that, I can shoot at a meteor. Let's hope there's going to be one nearby. And we get one animation. And then the explosion disappears. Perfect. And with that, you have a basic animation logic. That's all there is to it. All you need for basic animation is that you are going to override self.image. You could either play it once or continuously, and that's really all there is to animations in Pygame. With that, we can cover the final part, playing sounds. This is actually fairly simple. We have to first of all create a sound object. That we do with pygame.mixer.sound along with a file path. After we have that, we can play, stop, rewind, set volume, and so on. Anything that you would want to do with a music file. And by the way, if you look at the Pygame documentation, there we have music and we have mixer. Although this is a bit deceptive. If you click on music, you are also getting to a subpart of mixer. So ultimately, just go to mixer right away. Then you have the main module. And in there, if you go down just a bit, we should be getting to pygame.mixer.sound. That is the main module that you are using for sound, and you can create it in a whole bunch of different ways, but basically, you always either insert a file name or some kind of data to get a sound file. And then you can use sound.play, sound.stop, fade out, set volume, and so on. Which means, back inside of the code, we first of all have to import a couple of files. And for that, if you look at the folder, we have 4 files that we want to import. Let's start with the laser sound that we want to store in a variable. For that, I need pygame.mixer.sound. Then use the join method to go to audio, and then I want to import laser.wav. And that is it. We now have a laser sound. To play it, we want to go to the place where we are creating one instance of a laser. That happens in here. I want to get the laser sound and then play it. If I now play the game, I can shoot the laser and we're getting a laser sound. If you find this laser sound too loud, when you are importing it, you can get the laser sound and then the method set volume, where we have to add a floating point value, which goes from 0 to 1, with 1 being the full amount. If you add a 0.5 in there and run this again, the laser is now 50% as loud. And that is basically it for sounds. So to finish the game, we simply have to import a few more sound files. For that, I want to copy the laser sound and get, first of all, the explosion sound, which we are getting from explosion.wav. Then I can duplicate this line one more time, and we want to have a damage sound, which is going to be damage.ogg. Finally, we have a game_music, for which we will need pygame.mixer.sound one more time. The file is called game_music.wav. With that, we have all of the sound files. We just have to figure out when to play them. The explosion sound I want to play when we have a collision between a laser and a meteor in here. Explosion sound.play. Let's try, and there we go. This is working pretty well. Now, alternatively, you could also run explosion sound when we are creating an animated explosion inside of the dunder init method. In there, we would get the same result. Just choose whatever you think is better. It doesn't really matter. Both work just fine. Besides that, we have the damage sound that we want to play whenever the player gets hit, which happens in here. Although for this game, once the player is hit, the game is over anyway. So we don't actually need a damage sound. Let's remove it. Finally, we have game music. This is the background music, which we want to play right away. I guess we can do it right after game music.play. Although before we are doing that, I think for the game music, we want to set the volume to something lower. Let's say 0.4. Let's try. Cool. That is working reasonably well. Now, before we are finishing, the one last thing that I do want to cover is when you are playing a music file, you can specify the amount of loops. If you add a 5 in here, you're playing the music file 5 times. And if you add a -1 in there, you are playing it indefinitely, which is what we want for the game music. We have finished our first game, and at this point, you are aware of all of the main concepts of pygame. Although there are quite a few more specific concepts that we are going to cover. For example, for the next game, we're going to add a camera and actual collisions, along with a few more extra things that actually make a game. Alrighty, the second game in the series is going to be a Vampire Survivor style top-down shooter. This project is going to be much closer to an actual game, and there are a couple of key concepts that I want to cover. Most importantly, we have collisions and a camera. Those are essential parts that you basically always need. Besides that, we will also cover creating levels in an editor, in which we can move things around super easily. That is going to make it much easier to build actual games. Finally, we are going to work on proper animation control. Or in other words, we are going to take the basic animation logic and make it more sophisticated. That way, for example, we can animate the player moving in different directions. You will see later what I am talking about. First of all though, we have to set up the basics. For that, let's start with the project folder. Here we go. There are 4 subfolders inside of the project folder. Audio is super simple. This one is just a couple of audio files. Then we have the code folder, and in there we have main.py and settings.py. They don't do very much, and we will have a look at them in just a second. Besides that, we have data and images, and those 2 folders are quite a bit more extensive. Inside of images, for example, we have the gun, we have the enemies, and those are always animations, meaning we have multiple images that we have to import. And also inside of the player, we have the different states, and then inside of each state, we have an animation of the player walking in that direction. Besides that, we have a data folder. And this one you don't really have to understand at the moment. But in there, we have graphics, maps, and a tile set. The map, or world.tmx, is what actually contains the level. I will talk about that in much more detail later. For now, we have to create a basic game. And what I want to have is a very basic setup in which the player can move around. Or in other words, I want to have a sprite class with 1 image for the player. This one can be static for now. And then the ability to move around, which we're doing via input and a move method. And at this point, this shouldn't be impossible, meaning this could be an exercise right away. I want you guys to set up the basic game, which means I want you guys to create a player class with an imported player image that can walk around. And this should be a sprite. Also, for the overall logic of the game, contain all of this inside of a game class. That way we can avoid global variables. Also, all of this should be inside of main.py. I should actually demonstrate. Here we are in the code, and there is main.py. Doesn't do anything at the moment. And inside of settings.py, we are importing pygame, and we have a window width and a window height. Use all of that inside of main.py to create the basic game setup. Pause the video now and see how far you get. I want to start by creating a class called game. No need for inheritance, but we will need a dunder init method, although without any parameters. In there, we want to run pygame.init to initialize the entire thing, and then create self.display_surface, which is going to be pygame.display.set_mode. That way we are creating the display surface inside of a class. For the dimensions, I want to have window width and window height from settings.py. I suppose while we are here, we can also change the window title with pygame.display.setCaption. I am going to call it survivor, but choose whatever you like. Besides that, we also want to have self.clock for the frame rate, which we get with pygame.time.clock. And that is all we need to get started. Besides that, I want to have a run method. In there, we are going to have a while true loop. Or rather, I want to have while self.running. And this is what I forgot inside of the dunder init method. Self.running should by default be true. And once we have that, we will need delta time. We want to have the event loop. We want to update the game. And finally, we want to draw stuff. First of all, delta time, we're getting with self.clock.tick without any argument and divided by 1000. That way, we get delta time in milliseconds. For the event loop, I want for event in pygame.event.get. At the moment, I only want to check if the event.type is equal to pygame.quit, all in uppercase letters. If that is the case, self.running should be false. That way, we can close down the game. And what is really important, after we are finishing the while loop, we also want to run pygame.quit, or the opposite of pygame.init, just to have a clean exit. That was fairly easy, and update for now we can simply ignore because we don't have anything to update. Inside of draw though, we want to call pygame.display.update or .flip. Both would be acceptable. Since we used update in the last game, I'm going to keep on using that, but you could use either. That is it. Now we have a game class, and this we have to call. I want to create one instance of the game class and then game.run. If I now run everything, we are getting a basic pygame window. So that is working really well. There's just one more thing that I do want to do. Over the course of this game, we are going to create multiple files, and I want to make sure that I only ever run this main.py file. For that, we can check if dunder name is equal to the string dunder main. That way we are checking if the file is the current main file, and only if that is the case do we want to run the code. If I run all of this again, this is not going to make a change. And if you forget it, it probably also won't be the end of the world. But it's a neat safeguard to avoid some potential problems. We now have a basic game class. After that, we want to create the player. And this I want to do in a separate Python file. Which means inside of the code folder, I want to create a new Python file. Let's call it player.py. In there, I'm going to create the player class. Although first of all, we will need from settings and import everything. Then class player. This has to be a sprite. This needs to be a sprite, or in other words, we want to inherit from pygame.sprite.sprite. After that, we will need a dunder init method with self. I want to have a position and I want to have the groups. Next up, we have to call super.dunder init along with the groups. Once we have that, self.image and self.rectangle. For the image, for now, we can simply call pygame.image.load along with the join method for the path. We want to go to images, then we want to go to the player, and I guess we can start with down 0.png. So once again, we want to go to images, then we want to go to the player, then we want to go to the down state, and finally 0.png. Also, do not forget to convert alpha all of this. That way, we have our player surface. For the rectangle, I want to get self.image.getFrectangle and place this center. The position for this is what we're getting from the parameter. Also, I realized there is a typo. This should be pygame.sprite.sprite. So, with that, we have a player class. This I want to use inside of main.py. For that, we first of all have to import it. From player, import the player class. Next up, I want to create one instance of this player class and store it inside of self.player. For that, we will need player along with a position and a groups. To start with the position, I simply go with 400 and 300. Entirely random positions. This we're going to change later on anyway. After that, we will need a group, which we don't have at the moment, but I'm going to create one in just a second and call it all sprites. Let's do it right away actually. I want to have a bunch of groups later on, although for now I simply want to have self.all_sprites with pygame.sprite.group. And just to keep things a bit more organized, I want to have groups, sprites, and I also want to have, let's call it setup. With that, we have a couple of basic things. After that, before we are calling pygame.display.update, I want to get self.allSprites and draw on self.displaySurface. And I suppose while we are here, we can also call self.allSprites.update with delta time. I can now run the code and we can see the player. It doesn't do anything at the moment, but we have something. So next up, we have to work on two important things. We want to get the input. For now, let me add pass in here. And we want to have a move method with self and delta time. Both of which are going to be called inside of the update method. In there, we're also getting delta time. I want to call self.input and self.move. I'm going to start with the move method, just so we have something to look at. I want to get self.rect.center plus equals self.direction multiplied with self.speed multiplied with delta time. We do have delta time, but we don't have direction or speed. Those we have to create under a movement section. Self.direction is going to be pygame.vector2. For now, with a direction of 1 and 0. That way we are going to the right. Self.speed is going to be 500. If I run main.py, we have some movement, although we can't see the last frame. To fix that, before we are drawing all of the sprites, I want to get self.displaySurface.fill with a black color. Let's try all of this again, and we get proper movement. After we have that, for the direction, we should have 0 and 0 by default, which are the default values. So I'm going to leave it empty. And then I want to check for the input, which is going to be a local variable. pygame.key.getPressed. Don't forget to call this one. And then we want to update self.direction.x and self.direction.y. For x, I want to get the integer value of keys and pygame.k_right. From that, I want to subtract the integer value of pygame.k_left. Let's start by trying this one. So self.direction.y is going to be commented out. Inside of main.py, I can now move left and right. So that part is working pretty well. Just as a reminder at this point, pygame.kright and pygame.kleft are Boolean values. They can either be true or false. And in our case, via integer, we are turning true into a 1 and false into a 0. If we then subtract one from the other, we can check for both at the same time. This is the exact same logic that we had inside of the space shooter. And for self.direction.y, we want to do basically the same thing. So let me copy all of this and check for pygame.k down minus pygame.k_up. With that, I can run main.py and move in all 4 directions. That's a really good start. However, if I move left and right, we have 1 speed, the same with up and down. But if I go diagonally, all of a sudden, we are moving quite a bit faster. That happens because we are not normalizing self.direction, which we can do fairly easily. Self.direction is going to be self.direction.normalize. But this we can only do if the vector has a direction, i.e., we want to check if self.direction has any value that's not 0 and 0. If that is not the case, else we simply want to keep self.direction. And with that, inside of main.py, the movement is now constant, or rather, the movement speed is constant. And that covers the exercise. So by the end of it, I have written 40 and 20 lines. So in about 60 lines, we have created a reasonable starting point for our game. And I hope you could follow along. I did speed things up quite a bit. But fundamentally, all of this is very similar compared to what we have done in the space shooter. So if you get stuck on any of these topics, definitely play around with them in your own time. In this section, we are going to cover collisions, which means by the end of it, you can stop the player movement using some kind of object. We are not really going to use proper graphics, just to keep it simple. Later on, we can add all of that fairly easily. First of all, though, we have to cover some basic theory about collisions. And the most fundamental issue is that rectangles can only check overlaps. Meaning, we know if there's a collision, but we don't know what to do with it. Instead, what we want for an actual collision is that if there's an overlap, i.e. a collision, then we also want to update the position of the player. Or in other words, if we have the player overlapping with an obstacle, then we want to move the player a bit further to the left, so we are stopping at that obstacle. Since we can move all the sides of a rectangle, this shouldn't be too difficult. However, there is a bit of a complication. The problem is that we do not know on which side the collision happened. For example, if we have something like this, we could have a collision on the right side of the player. That seems to be the most obvious case. However, we could also have a collision on the bottom of the player, on the top of the player, or on the left side of the player. All of those are equally possible. For example, for the left side case, it could be that this player is moving really fast to the left. And then within a single frame, we are moving all the way over there. Which is entirely possible, and simply looking at a single frame with a collision can be really deceptive. Which means, first of all, we have to get the collision side. That process is going to involve two steps. First of all, we're going to separate the dimensions. We are moving and checking the collisions only on the horizontal axis and then on the vertical one. You could also do this the other way around. The order here doesn't matter too much. What matters is that we are only checking a single axis. That way, we only have to figure out if the player is to the left or to the right of the obstacle. So if we have something like this, at the moment, we only want to know if the collision happened on the left side or on the right side of the obstacle. And the easiest way to figure this one out is to look at the direction of the player. For example, if the player moves to the right, then we know the collision must have happened on the left side of the obstacle. Or in other words, if there's an overlap and the player is moving to the right, then the collision must have happened on the left side of the obstacle. At least as long as the obstacle itself is not moving, which we are going to assume for now. And that's the basic logic. We are simply checking if there's an overlap between two objects, and on the moving object, we're going to check the direction. Which is a very easy thing to implement, but it's not without its problems. The most important issue is that this approach only works if a single object is moving. For example, in this game, the player can only collide with trees, rocks, and the hills, all of which are static. The player cannot collide with any of the enemies. Since those are moving, the collision logic would break. For collisions between two moving objects, we would need some more logic, which we are going to implement in the next game. That is going to be a Pong game, and in there we have a player paddle and a ball, both of which can move, meaning in there we have to check collisions between two moving objects, which isn't that much more difficult to implement, but you do want to have some groundwork first. Anyway, with that, we have all of the theory out of the way. Let's do some coding. Although, first of all, back inside of the code, we have a problem. We only have the player, and the player cannot collide with anything. To fix that, Inside of the code folder, I want to create another Python file, sprites.py. I want from settings and import everything, and then create a class. Let's call it collision sprite. This also needs to be a pygame.sprite.sprite, for which, once again, we will need a dunder init method, for which we are going to need a position, size, and groups. Super.dunderInit with the groups, and then we will need self.image and self.rectangle. The image is going to be pygame.surface, and then we pass the size right through. To make sure that we can see self.image, I want to fill it with a blue color. After that, for the rectangle, self.image.getFrectangle, in which we are placing the center with the position. That would be a very basic collision sprite that we are going to use inside of main.py. First of all, from sprites, I want to import everything. Later on, we're going to add a few more classes in there. After that, inside of dunder init, I want to create a random amount of instances of this class, which we can do with a for I in range loop. Let's say I want to create 6 collision objects. And then I want to have a collision sprite, for which I'm going to need a random position and a random size. Let's call it position, size, and for groups, we want to have self.allSprites. Now to get random values, I want from random import randint. For the position, I want to have an x and a y local variable, which we both get via randint. For x, it's going to be 0 all the way to the window width. And for y, it's going to be a randint from 0 to the window height. Those numbers we can then pass into the position. I want to have a tuple with x and y. After that, I want to have a width and a height for the surface, which I'm also going to create via random integer. I guess the numbers here could go from 60 to 100 for width, and for the height, also random integer. Let's say those from 50 to 100. Entirely random numbers, and later on, when we actually import objects, those are not going to be relevant anyway. For the size, I want to have width and height. If I now run all of this, we get a bunch of random objects somewhere on the window. So that's a really good start. Although, before we continue, we have to make sure that we have easy access to all of these sprites. For that, I want to create another group, self.collision_sprites, which is simply going to be pygame.sprite.group. Every time I am creating a collision sprite, I want this sprite to be in all sprites and self.collision_sprites. On top of that, the player needs to know where all of these collision sprites are, which means I'm going to pass self.collision_sprites in there as an argument. But now you have to be careful because those two lines do something fundamentally different. Inside of the collision sprite, we are adding the sprite to two groups, all sprites and collision sprites. However, for the player, we are only adding the sprite to self.allSprites. But on top of that, we are giving player one more argument, self.collision_sprites. But the player itself is not in this group. It only has access to it. And that should make sense. We don't want the player to collide with itself. That would just give us some weird behavior. So, next up, inside of the player, we are going to need one more parameter, collision_sprites. That we also want to store under movement as an attribute, self.collision_sprites is going to be collision sprites. With that setup, we can keep the collision logic inside of the player. Or in other words, inside of the player, I can create another method. Let's call it collision, for which we will need self, and we will need the direction or the axis that we want to work in. This could either be horizontal or vertical. Although for now, we are simply going to add pass in there. Because before we are going to write anything inside of collision, we have to work inside of the move method. At the moment, we are updating both of the axes at the same time, simply because we are updating the center via a direction. But this I want to split into horizontal and vertical movement, which fortunately is very easily done. I want to duplicate this line and then increase self.rect.x and self.rect.y. Self.rect.x is simply the left side of the rectangle and self.rect.y is the top side of it. To that, I want to add self.direction.x for the horizontal movement and for the vertical one, self.direction.y. If I now run all of this, we are still getting the same kind of movement. So at the very least, we didn't break anything. Once we have that, after we have done all of the horizontal movement, I want to call self.collision on the horizontal axis. Next up then, we are going to do all of the vertical movement and then we are checking the vertical collision. That means we are first going to move on the horizontal axis the player either left or right. After which we are going to check for a collision. For example, if this is our player, we might have a collision here. We now have to figure out if the player is to the left of the obstacle or to the right. If the player was on the left side of the obstacle and we have an overlap, something like this, then we want to resolve this collision by moving the player a bit further to the left side of the obstacle. But first of all, for that, we have to get all of the obstacles, which we can do via a for loop. For sprite in self.collision sprites. In there, first of all, we want to check if sprite.rect.collide rect along with self.rectangle. If that is the case, for now, let's simply print overlap. If I now run main.py and I overlap with any of the obstacles, we are getting overlap. So that part is working pretty well. But this is something we have already seen a couple of times, so this isn't particularly special. However, what we can do, instead of printing overlap, I want to check if direction is equal to, let's start with horizontal, meaning we only want to check left or right collisions. And in there, I can check if the player is to the left or the right of an obstacle via self.direction.x. And if that one is greater than 0, then I know the player is moving to the right, which means for the collision, I want to get self.rect.right and set it to sprite.rect.left. I can now run main.py, and if I am only moving to the right and do nothing else and I hit an obstacle, the player stops. So that part is indeed working. The issue is if I do anything else or any other side, nothing is going to work. And if we are overlapping and moving to the right, we are teleporting. On top of that, you might be wondering, why is there such a big gap between the player and an obstacle? So all of this. That happens because the player image is quite large. If you look at the project folder, under images, the player, and we have down, you can see there's a ton of white space to the left and to the right of the player. That is necessary because when the player is moving left, we are using some of that space for the legs. And don't worry, we are going to account for that in just a bit. First of all though, I want to finish up the collision logic. And also, you don't have to write this if statement on one line. It could also be something like this. Although since we are only doing a single thing, I prefer to keep the if statement on a single line. Besides that, we also want to check if self.direction.x is smaller than 0, i.e. we are moving to the left. If that is the case, self.rect.left should be sprite.rect.right. Let's try that one. I can now move to the left, and if I collide with an obstacle, the player stops. The right side collision also works just fine, so I am quite happy with that. Definitely making progress. And just to go over the entire logic one more time. At the moment, we are moving the player only left and right. If this is our player, at the moment, we are only moving to the right. After that, we are checking for collisions, meaning we are looping through all of the sprites and then we're using a rect collision. If that one triggers, we could have something like this. If that is the case, we are checking one of two if statements, one of those two. In our case, we know that self.direction.x is greater than 0 because the player is moving to the right. If that is the case, we are setting the right side of the player to the left side of the obstacle. Or in other words, we are getting this side and setting it to this position, i.e., we are moving the player a bit to the left. And that is literally all we do. With this system, we have basic collisions. And, well, the same thing we can do in an else statement for the vertical movement. I simply need to check if self.direction.y is smaller than 0. If that is the case, we are moving up. And if there's a collision, self.rect.top should be sprite.rect.bottom. Then we can duplicate all of this because next up, I want to check if self.direction.y is greater than 0. In other words, we are moving down. And if there's a collision, I want to set self.rect.bottom to sprite.rect.top. And that is all we need for the collisions on all four sides. If I now run main.py, we're getting a collision on all of the sides, and this works super reliably. So, very happy with that. This would also work with two collisions at the same time. Let me try this again. So there you can see we have two obstacles at the same time. I cannot move to the right and I cannot move up. So this part is working perfectly fine. Great. With that, we have basic collisions. However, we are not done yet because at the moment our player has a shape that's roughly like this. Or in other words, those are the visible pixels, but the entire surface is this large. As a consequence, we do have a bit too much white space to the left and to the right of the player. This I don't like and want to remove, which we can actually do fairly easily. At the moment, our collisions are done via the rectangle, which is going to have the same size as the image, which is not what I want. I want to create self.hitbox_rectangle, which is going to be self.rect.inflate. At the moment, we only want to change the width. Let's say by -40 for now. The height we can keep, so this one is going to get a 0. With that, we have a hitbox rectangle. This is what I actually want to use for the collisions. And to use it, we have to update the move method and the collision method. Or in other words, we first of all want to move the hitbox rectangle, both on the horizontal and on the vertical axis. After that, we want to set the center of the rectangle to the center of the hitbox. Those two always have to keep the same center positions. Besides that, for the collisions, we want to check with the hitbox of the player instead of the rectangle of the player. And all of this is going to be your exercise. So what I want you guys to do is to implement the hitbox logic for the collisions. Pause the video now and see how far you get. Back in the code, first of all, we have to update the movement because we only want to move self.hitbox_rectangle on the horizontal and on the vertical axes. Now this code wouldn't crash, but now we do not get movement anymore. Simply because the sprite is drawing the image wherever the rectangle is, and we are not moving the rectangle anymore. To fix that, I want to set self.rect.center to self.hitbox_rectangle.center. Since we are not checking for collisions with the hitbox rectangle inside of main.py, the player can simply walk through all of the obstacles. To account for that, inside of collision, we want to check if sprite.rect.collideRect and self.hitbox_rectangle. On top of that, if there is a collision, so for example on this line, we don't want to update self.rectangle. Instead, we want to update self.hitbox_rectangle. That we want to do for all of the rectangles. If I now run main.py again, I get proper collision logic again, and now the player gets much closer to these obstacles. Especially when we are comparing this to the original, it looks much better. Although there's still a little bit of a gap that we can now fix with this inflate method. Let's go with -50, and we are getting closer, but there's still a bit of space between them. Maybe -60 is the right number. And there you can see. Now we have a pixel perfect collision. Or well, not exactly pixel perfect because we're not using a mask, but it looks good to the player, and that's really all we need. So with that, we have basic collision logic, something really important for any kind of game. And fundamentally, we are really not doing anything too complicated. So the entire collision logic took maybe 10-ish lines to write. We are simply getting the player rectangle and then setting it to one of the sides of the obstacle. And to know which side we are working with, we are checking the direction the player is moving in. And that is literally it. It is time to import the level data. By the end of this section, we have some actual stuff in the game that is nice to look at. Although for the full effect, we are also going to need a camera, which we don't have yet. That is going to be the next section. Anyway, to create a proper level, we are going to need an editor. That way we can place images and see the result right away. And there are quite a few different level editors, but one of the really popular ones is called Tiled, that you can get at mapeditor.org. I have used this one for a whole bunch of projects. It's entirely free and really nice to use. And the files you create in Tiled can also be imported into Pygame super easily. That being said, for this video, I will only cover how to import tile maps. I will not cover how to create them. If you are interested in that, check out my dedicated video. In there, I cover all of the details of Tiled, including how to create a map. Anyway, if you go to mapeditor.org, you can see Tiled. If you go down a bit, you can also see a couple of games that have been using it. I guess the really famous one is Shovel Knight, there's also Axiom Verge and Carrion. All really good games. In our case though, we simply want to download on itch.io. There, you can click on download now, and you could set a price, but you don't have to. You can simply go to no thanks, take me to downloads, and then you can download the version that works for your operating system. In my case, I'm working on Windows, but if you have Mac or Linux, go with the other ones. Then you have a download. After that part is done, you want to open the file, and simply click on next and agree to everything, and then you should be done. Afterwards, you can launch Tiled. If I click on finish, then we are getting to something like this. This is the Tiled editor. In there, you could create a new map or a new tile set. What those words mean, you are going to see in just a second. In fact, I think the best way to approach this is to look at the project folder. So in there, we have a data folder, which contains graphics, maps, and tile sets. The main thing that you want to work on is a map. And there you can see we have a tiled symbol. That should also work for you. If you click on that one, you can see a tiled map. So the main thing you see on the window is the map that we have created, and this is going to be our actual level. On the right side, this bottom area, this contains the tile sets. And at the moment I have two. A world tile set, and on there, if you hold Control and use the scroll wheel, you can zoom in and out. One tile set is going to be all of the graphics. The other tile set, objects, simply contains a whole bunch of objects, like trees and pillars and rocks. And besides that, we have a whole bunch of layers. The bottom one is ground, then we have entities, collisions, and objects. So how does all of this work? For that, let's have a look at the project folder. We have three main components: graphics, maps, and tile sets. The way those are going to work is that we are importing all of the graphics into Tiled. If you open this one, you can, for example, see under tile sets, we have the world tile set, the one you have just seen under world tile set. On top of that, what Tiled is doing, it is separating this graphic into individual tiles. One would be this one, the next one would be this one, then we have another one here, and so on. We are simply separating the graphic into smaller bits. And these smaller bits are effectively a tile set. Or in other words, if I go back to data, we are importing the graphics and storing them as a tile set. That way, we can pick one part of the graphic. And then this tile set is going to be used inside of a map to create a new kind of graphic. Or in other words, if I head back to tiled and I have the ground layer selected, if I now select one of these tiles, I can go to the map and zoom in and simply place them as I like. I can also select multiple and place them in there. And that is how you create the entire map. For this entire thing, I spent about half an hour laying out all of these parts. And that way, we have created a tile map, which is what we actually want to import into pygame. And in the most basic sense, that's all you have to understand about tiled. Although, I guess there's one more thing that you want to keep in mind. There are two kinds of layers that you could be working with inside of tiled. What I have covered so far is a tile layer. And this you can see via this grid symbol. That means we have a tile layer. Besides that, we can also have an object layer. Those have these pink, speech bubbly kind of looking things. Those work in a very similar way, but there are some key differences. For example, if we are looking at the objects, those would be all of the trees, the pillars, and the rocks. The main way those differ from the tile set is that they can be placed freely anywhere on the map. While a tile set always has to conform to a grid, so I can only ever select one of these grid positions. I cannot go outside of it. Also, when we're importing all of them into pygame, they do work just a little bit differently. Ultimately, for all of these objects, the way you want to approach them is that if I go to the top left, we have a whole bunch of ground tiles, all of those, they're all grass. Then we have an object, that one is simply a tree, or rather a couple of trees. And those for now we want to import, which means inside of pygame, we want to get the ground layer and the objects layer. Collisions and entities we are going to ignore for now. And for all of these objects, if you look on the left, there we have properties. For example, if I am clicking on the tree, we have an X and a Y position. So if I'm moving this tree, you can see this position is updating. We're also getting a width and a height, and all of these numbers we can use inside of pygame. And for the ground, let me hide all of the other stuff. For all of the tiles, for example, for this top tile, we have three major attributes that we care about. We have an X position, a Y position, and a surface. The surface for basically all of those would be a plain grass tile, but for example, for this one here, we have mostly grass, but then also a corner for the stone. Besides that, we have a position, but the position is on a grid, meaning for this top tile, the position would be 0 and 0. And if you go one tile further to the right, the position would be 1 and 0. Really important to understand here is that we are not working with pixel positions. Or in other words, when we are importing all of this into pygame, we have to convert a grid position into a pixel position, which arguably is fairly simple. Alrighty, but with that, we have another question. How can we import all of this into pygame? That topic you could approach in two ways. Number one, you could export all of this as a CSV file. There's also JSON or Godot scene, and via that, you could import them into other programs. While that's possible, it's also quite a hassle, so not something I would recommend. What is a much better way is to use a Python module that does all the work for us. For that, you want to open the terminal and then type pip install pytmx. Then Python is going to load something for a second, and then you have pytmx, a module that can import TMX files super easily. And with that, finally, we can start working inside of pygame. First of all, we have to import the pytmx module. Although we don't want all of it, we simply want from pytmx.util_pygame and then import load pygame. Via this method, we can import a TMX map and then use it inside of the code. And I suppose for all of that, we can create a separate setup method. without any custom parameters. And first of all, I want to import the map, which we are doing via load pygame. After that, for the path, we want to go to data, then to maps, and then to world.tmx. Or in other words, we want to use the join method, then go to data. After that, we have maps, and finally, we have world.tmx. Once we have that, let's print the map. And after we have covered all of the groups, I want to call self.setup. If I now run all of this, we're getting the game, although we don't care about that at the moment, and then we are getting a tiled map. If you get anything else, something has gone wrong. So double check your steps. Now on this map, we want to access all of the individual layers. For example, we want to get the ground layer or the objects layer, and later on also the collisions and the entities layers. For that, we want to get the map and then get layer by name. That is the most common way to access one of the layers. After that, we're going to need a name. And for now, I want to look at the objects layer. The layer inside of tiled that contains all of the trees, all of the rocks and the pillars and stuff like that. Inside of this layer, we have a whole bunch of individual objects, all of which we can access via a for loop. For obj in map.getLayer by object name. And inside of this thing, you can now print obj.x, obj.y, and obj.image to get the x position, the y position, and the surface. Which means if I run all of this now, we are getting a whole bunch of data. And that is looking pretty good. All we have to figure out now is how to turn this data into a sprite, which we can do easily, because under sprites, we already have a collision object. This we simply have to modify a bit. We want to keep a position, but instead of a size, we want to have a surface. And then, when we are creating self.image, we want to use that surface. We don't want to fill the image anymore, but we want to keep self.image.getFrectangle. After that, we don't need this for I in range 6 for loop anymore. Let me get rid of it entirely. Instead, inside of the for loop for getLayer by name, I want to create a collision sprite. For the position, we will need obj.x and obj.y. Both of those have to be inside of a tuple. After that, we are going to need a surface, which is obj.image. Finally, for the groups, self.allSprites and self.collisionSprites. And with that, if I run all of this, you can see we have a whole bunch of trees. And since the player collided on a collision object, we get some weird behavior, but that's totally fine. That we can fix by changing the starting position of the player to 500. If I now run all of this again, we can see that the player can move around and we have a whole bunch of trees. So that is working really well. We are also not needing the print statements anymore, and that covers the first part. Besides that, I also want to import the ground layers. Or in other words, I want to only look at the ground layer at the moment. And this is working a bit different because remember, now we are working with a tiled layer, whereas objects was an object layer. Now to use a tiled layer, we are still going to use map.getLayer by name. And the layer we now want to get is called ground. But after this one, we want to add .tiles. That way, we are returning the tiles and make them a bit more accessible. Or in other words, when we are using the for loop, we can use for x, y, and let's call it image in map.getLayer by name. And after that, I can print x, I can print y, and finally, I can print the image. If I now run all of this, we are getting a huge amount of data. We're getting, for example, 51 and 49. This is the x and y position on the grid. It is not a pixel position. And then we're getting a surface, and that's really all we need. That being said, for the ground, we want to have another kind of sprite, because those sprites should not be collidable. Or in other words, inside of sprites.py, I want to create another class called sprite. This one is also going to be pygame.sprite.sprite, and then define dunder init, for which we are going to need self, a position, a surface, and the groups. And well, for now, this sprite class is going to be basically identical compared to the collision sprites. So I can simply copy paste the lines and then we are good to go. Then inside of main.py, we want to create one sprite for now with the X and Y position. After that, for the surface, we want to use the image, and for the groups, we want to use self.allSprites. That should be all we need to get something. And well, if you now look in the top left, there we do have some weird thing. That is because we use the X and Y position from the grid, meaning all of the numbers are way too small. To fix that, we have to multiply all of these numbers with the tile size. The top left tile, for example, would have a grid position of 0 and a 0. And we know that the width of this tile and also the height is both 64. But then for the next tile, this one here, we have a grid position of 1 and 0. The top position is simply going to be 0. However, for the left side, this one here, we want to have 1 times 64. That way, we are getting all the way to this point. And by the way, the tile size you can set when you are creating a map. But this you want to plan out. So when I got the graphics, I checked what kind of tile size we had. This is really important to know before you are starting. Although in our case, under settings, we have a tile size. This we can simply use. Or in other words, when we are getting the position for the sprites, I want to get X and Y and then multiply it with the tile size. If I now run all of this, we can see that we have the proper level. Although all of the objects disappeared, but we still have collisions. So what happened? Well, this is an issue we had earlier. When we are drawing all of the sprites, we are sorting these sprites by the time of their creation. And since we are creating all of the sprites after the collision objects, they are being drawn on top. That is a very easy thing to fix. We simply want to create all of these objects after the sprites. If I now run all of this again, you can see that we have something much better looking. And the collisions also work reasonably well, so I am mostly happy with that. That being said, if you compare this image at the moment with what we have inside of tiled, the objects don't line up exactly. I guess a really good way to illustrate is if you look at this tree, how it relates to these rocks. The top of the tree is basically right around this corner. But inside of the game, this is looking different. So what happened? The answer to that is fairly simple. When we are placing a collision sprite, the position that we are placing is the top left. If I now run main.py again, this is looking much better. Although it's not perfect yet. If we are comparing all of this to tiled, and pay close attention to the top of the tree and the corners of the stones. If I run the game again, you can see quite well that this isn't what we are getting. That is because when we are placing all of the background sprites, we are placing the center. But when we are placing the objects, or in other words the collision sprite, we are placing the top left position. Or in other words, we are placing a different position. Now generally, when you're getting anything from tiled, you want to place the top left position. If you do that and run all of this again, now this is looking exactly like what we have in tiled. But anyway, at this point, you should be confident to import tiled layers or object layers from tiled. Let's do an exercise. I want you guys to import the collision layer from tiled and then create invisible collision objects from the rectangles on that layer. Or in other words, here we are back in tiled and I want to look at the collision layer. If I make this one visible, you can see that we have a whole bunch of rectangles. Those basically define the environment, or the collision with the environment. I want you guys to import all of those and then create a collision object that the player cannot see. Simply because we already have the graphics from the tiled layer. And a minor tip for this one, when you're importing objects in pygame, you can get the width and the height quite easily. You also get with .width and .height. And also in the code, you can reuse the collision sprite for all of that. Pause the video now and see how far you get. I want to have for obj in map.get layer by name. And I want to look at the collisions layer. Since this one isn't visible, it doesn't really matter where you put it. It could be before or after the other for loops, it's entirely up to you. In there, we want to create a collision sprite, for which we are going to need a position, a surface, and the groups. The position is super easy. We simply want to have obj.x and obj.y. For the surface, we kind of have a problem, because when we imported all of the objects, we got obj.image. But this we cannot use for this for loop, simply because we are importing rectangles. Or in other words, if I comment out this line for now, and then print obj.image and run the code, we are simply getting a whole bunch of none, which means obj.image isn't a good way to approach this. However, what we can do is create pygame.surface and then create a surface with the size of these rectangles. That is possible because we can get the width and the height of all of them via obj.width and obj.height. Finally then, we want to create the groups. And in my case, I only want to get self.collision_sprites. That way the player can collide with them, but they are not visible. If I run all of this now, I can try to go down, but I am not able to go to the cliff. Also, if I go to this stony hill thing, like so, the player has a collision. And this is working really well. Although for this part, I was a bit lazy, because when you look at these collision layers, you can see they don't really line up with the cliff graphic. That is because later on, we will spawn the player inside of this center area. And then the area around it is sealed off, meaning this area around here is never going to be reachable by the player. So it doesn't really matter how large these rectangles are on the left side of the cliff, at least on this side. Unfortunately, we cannot place the player in there yet because we don't have a camera, so there wouldn't be any point to it. That we can work on next, but for now, we have made some pretty solid progress, and now we are able to import stuff from tiled. Now that we have a level, we can work on a camera. By the end of this part, we have a proper level that the player can explore. Makes the entire game feel significantly better. For that though, we have kind of a problem at the moment. That is that we can only see things that are on the display surface. Or in other words, if this is our display surface, and so far our window, at least in my case, was always 1280 by 720. On there we have a player and we have a bunch of objects. However, what happens when we have an object outside of it? What do we do then? Or in other words, at the moment we can only see things that are between the positions 0 and 0, so the origin point, and the bottom right, or the window width and window height. For example, in our case, the top left position of this object might be 1400 and 100 for X and Y. This at the moment would not be visible. How can we change that? And first of all, for that, we have one major limitation, and that is that the display surface cannot be changed. It always starts at 0 and 0 and then continues to the display dimensions. I suppose you could resize the window, but ultimately that doesn't help you very much. Instead, to create a camera, we have to change where all of the elements are drawn. And to understand how this is working, let's look at the display surface again. And one more time, we have a whole bunch of objects and one object outside of it. Now what we cannot do is move the entire display surface to the right to make it visible. That is simply not possible. But what we can do is the opposite. We can move all of the other objects in the opposite direction. And when I say move, I am a bit incorrect here, because we are not moving anything. What is really important to understand is that the position of the sprite, or rather the rect inside of it, does not change. The only thing that changes is that we are drawing things in a different position. If we change the position of the rectangles, our collision logic would stop working. So this is not something that we can do. So the question then is, how can we draw stuff in a different position? And for that, we can customize a sprite group, or more specifically, the drawing logic of a sprite group, which actually is quite simple, because all that is happening inside of group.draw is a for loop that blits all of the sprites on a surface. Or in other words, we are looking at all of the sprites inside of the group, and then we are doing surface.blit with sprite.image and sprite.rectangle. That's all that's happening in there. So let's play around with that. Once again, here we are in the code, and at the moment, we are drawing all of the sprites via self.allSprites. Or in other words, inside of the run method, we are calling self.allSprites.draw with a target surface, which in our case is the display surface. This we want to change, and for that, I want to create a new Python file, which means inside of the code folder, I want to create, let's call it groups.py. First of all, we're going to need from settings and import everything. After that, I want to create a class called allSprites, which has to inherit from pygame.sprite.group. And for now, all that we are going to do in here is define dunder init with self and nothing else, and then call super.dunder init. That way, we have a copy of a sprite group, which we can use inside of main.py. I want from groups import all sprites. And that I can use to replace this pygame.sprite.group. If I add all sprites in here and run the code, we are getting the very same outcome, which should make sense. We are basically just wrapping the basic pygame group inside of another class. Although with this setup, we can customize things. But first of all, let's recreate the original functionality of this group. For that, we will need define draw with self and some kind of surface that we want to draw on. If I add pass in here for now, we are not going to see anything because we are now overwriting this draw method. And since we are not doing anything, we cannot see any surfaces. To get that functionality back, we want for sprite in self. That way we can access all of the sprites inside of this group. And then we want to get a surface and call the blit method with sprite.image and sprite.rectangle. After we are doing that, we can see the game again, and it works just as before. That part was actually fairly simple. I suppose one thing that we could be doing to simplify this code just a bit is that we always want to draw on the display surface. So adding this argument here doesn't really make sense. Instead, inside of dunder init of all sprites, I want to get self.display underscore surface and then get the display surface, which we can get via pygame.display.get underscore surface. That way, you're getting the display surface from anywhere inside of the code. And that we can use inside of the for loop self.displaySurface.blit. Because of that, the parameter surface is not needed anymore. And inside of main.py, we don't need the argument, but we can run the game and everything works just as before. We have now created a customized drawing method. And this we can push much further, because what you have to understand is that when we are calling the blit method, we are placing this surface in the position of this rectangle. And as a reminder, we are basically always placing the top left position of the rectangle. So if I run main.py again, once again, the same result. But what we can do now, to the top left position of the rectangle, we can add an offset via a vector 2. For example, in there, I could add 500 and 100. Inside of the game now, we are drawing every single element at an offset. Or in other words, from the top left, we are 500 pixels to the right and 100 pixels down. And really important, this is just where elements are drawn. The actual position of the rectangles has not changed. which means if I move around, the collisions work just as before. And let me get to a better position. There you can see I have a collision with a tree, and this works perfectly fine. So the main thing you have to understand is that inside of this logic, when we are drawing the rectangle, we are simply adding a vector 2. And to create a camera, we simply have to customize these numbers. For that, I want to turn the vector into an attribute, self.offset, which is going to be pygame.vector2, by default with 0 and 0. And this offset I want to use inside of the blit method, self.offset. On top of that, when we are drawing everything, I want to have a target underscore position, which we are getting inside of draw from self.player.rect.center. This is the position we want to follow, or in other words, the camera should follow the player. Once we have that, we want to get self.offset.x and later self.offset.y as well. But for now, let's only do one dimension. I suppose for now, let's simply start with target position and 0. If I now run the code, you can see that we get some movement. And the issue here is that, well, the camera movement and the player movement go in the opposite directions. If the player moves to the right, the entire thing is drawn further to the left. To flip that around, we simply want to have a negative number. If I now run main.py, we are getting something. So now the player is always on the left side of the window. So essentially what is happening now is that we are getting the origin point from the offset of the player. And then from that, we are adding the top left of the rectangle. That way, if the player gets further to the right, we are drawing everything at that offset. But we don't want the player to be constantly on the left border. And for that, we want to add another value, which is going to be window width divided by 2. To get that, we want to subtract window width divided by 2. Oh, and also, we want to apply the negative value to the entire thing. If I now run main.py, we have the player in the center, and we have a camera. So that is working really well. Although we are not covering the vertical axes, which fortunately is fairly simple. We simply have to duplicate this line and then change self.offset.y to target position 1, and then minus window underscore height. With that, we have a camera. And I can explore the level, although the collision is a bit wonky, but we're going to fix that later on as well. Other than that though, the player can explore the level, and we are nearly there. We're going to cover the starting position of the player in just a second, but for now, this is all you need for a basic player camera, where you place the top left of the rectangle, and then you add an offset. The offset you are getting from the position of some kind of target. This is almost always going to be the player. So next up, we have to work on the starting position. For that, inside of tiled, we have another layer called entities. On there, we have a whole bunch of markers. And let me hide all the other stuff. There you can see on entities, we simply have a whole bunch of markers. That's all we do in here. And if you look at one of those, this one for example, we have an X and a Y position, and that is about it. However, if we look at this marker, we have a name, and that is player, which means that this marker is supposed to be the starting position of the player. And all of the other positions are going to be starting positions for the opponents. That we cover later. First of all though, back inside of main.py in the setup method, I want to add one more for loop, and I think generally a bit more white space in here would be quite nice. I want for obj, and this could also be marker. Markers are just other objects. The name here doesn't really matter so much, and I want to keep it consistent, so for obj in map.getLayerByName. We want to look at the entities layer, and for now, let's simply print the object that we are getting. If I run the game, we are getting a whole bunch of tiled objects. Some of those are called none, others are called enemy, and then we have a player all the way in the beginning. Or in other words, if you look at tiled, This one was the starting position for the player. Then we had a none value here, and none just means we have no value for the name. But if I click on this one, we have enemy. And the issue why we have some none values is because I forgot to add a name. But that is quite easily fixable. If you go to objects, there you can see all of the objects on that layer. And I simply forgot a couple of those, and that you can fix quite easily by selecting all of them and then change the name to enemy. After that, we have a much better system where we have a marker with enemy or a marker with player. And that name we can access. I want to get obj.name. I can run this again, and now we are getting lots of enemies and one player. At the moment, we only care about the player, because that we can use via if obj.name is equal to player. And if that is the case, we want to create one instance of the player that we have so far done inside of dunder init, and then create that one in there. Because of that, we can use obj.x and obj.y for the position. Once we have that, we are getting an error. That game object has no attribute player. The reason for that is that this if statement never triggers, because the name of this object is player with a capital P. If I now run this again, we have the player in the proper starting position, and now we can actually move around properly, and we have something that looks much, much nicer. This is getting very close to an actual game, so quite happy with that. However, there is another issue, and that issue is called wise sorting. You might have already spotted that in the game. Basically, if there are overlaps between sprites, you want to make sure that the right one is on top. For example, what we could be having is the player being behind a tree, which does look right. But you could also have something like this, where the player is below a tree, and this doesn't look right anymore. Instead, we want to have something like this. And in our game, it needs to be possible for the player to be behind a tree and in front of a tree. And more generally, if I run the game and you look for overlaps, for example, there you can already see one, where we have the pillar thing being on top of the tree. That just doesn't look good. Also, we have another tree here that has the shadow on the other tree. The reason why all of this is happening at the moment is because we are sorting all of these sprites by the time of their creation. This does work for the background sprites, because those are always supposed to be in the background. But for the actual objects, like the trees and the rocks and the pillars, we can't rely on that logic anymore. Or in other words, in our case, the player, since we are creating this one last, is always going to be on top of everything else. But sometimes we want the player to be behind other things. And to make all of this a bit more visible, when we are creating the player, at the moment, the hitbox covers the entire width of the surface. This is not what we actually want. We do want to have some vertical overlaps. To get those, let's change the inflate method for the height to -30. If I now run main.py, I can, let's try this one, I can move on top of a tree. Or I can do something like this, where the player is slightly in front of that palm tree. This is still not that much of an effect, so let's go with -60 here as well. If I now run this again, and let's get the proper effect that we want. If I'm in front of a pillar, you can see that the player is overlapping, so it looks like the player is actually in front of it, which is the effect that we want. However, if we are behind it, then the effect breaks really, really fast. So how can we get that effect? And basically, you want to sort all of the sprites by their center white position. Which means, for the tree, we always have one center position, roughly here. And then if a sprite has a lower center Y position, for example, for this player, let's put some values on it. This could be a center Y of 100, while the tree has a center Y position of 150. Since 100 is the smaller value, the player should be drawn behind. However, then for these other sprites, we're getting a center Y value of 200. And since that value is greater than 150, the player should be drawn on top. With that system, we are avoiding this situation. And implementing all of this is actually really simple. You are simply going to need a sort method. and I think you could figure this one out on your own. So I want you guys to implement the Y sort system. Or in other words, use the sort method to sort all of the sprites when they are drawn by their center Y position. Pause the video now and see how far you get. And don't worry if you can't figure this one out on your own. It does get a bit more advanced. Back in the code, I want to look at the groups because we are drawing all of the sprites inside of this for sprite in self loop. And we want to sort all of the sprites, which means this self needs to be inside of sorted. But this at the moment is not going to run because we cannot compare different sprites. They are simply too complex. To get around that, we have to set a custom key. And for that key, we will need a lambda function with one parameter, which I usually call sprite. After that, we simply need sprite.rect.centerY. If I now run main.py, we are getting something really strange. The issue now is that we are sorting all of the sprites via the center Y position. And don't worry, I'm going to explain this line in just a second. First of all though, let me hide the background sprites. I can simply comment them out. And now this is working a bit better. And if I look at this pillar now, the player is in front of it. And if the player is behind it, the player is actually behind it. And all that is happening now is that we are always comparing the center position of the player with the center position of the sprite. Whichever is greater will be drawn later. And this is dynamic. At the moment, the center Y position of the player is below the sprite and now it's on top. Hence, the player will be drawn on top. This system works for all of the sprites. So if we're going to this pillar, you can see it is now behind the tree, which does look a lot better. If we add all of the sprites, they mess this thing up quite a bit because they are also included in the system. Or in other words, we have to make sure that we are excluding the ground sprites from the sorting logic. First of all though, let's talk about the sorted method. Basically what it does is it looks at some kind of list. In our case, that is self, or a list of all of the sprites inside of this group. And then it goes through every single one individually. And it wants to sort all of these values from the lowest to the highest value. But that's not possible at the moment, because if you have 5 different sprites, it doesn't know how to sort them. And for that, we have the key. Essentially sorted puts every single sprite inside of this lambda function, and then via this lambda function, we are extracting one value from the sprites, which is returned automatically. And that way, we are getting a value that can be sorted, the center Y position of all of the sprites. If you worked a little bit with a sorted method, it should be fairly straightforward. Although if you haven't, this might be a bit confusing, so definitely experiment with this just a bit. Anyway, to make the system work properly, we have to exclude all of these sprites. For that, I'm going to give them another attribute, self.ground, and this one is going to be true. After that, when we are drawing everything, I want to get the ground sprites, and then let's call it the object underscore sprites. To get the ground sprites, I want to use list comprehension with sprite for sprite in self. But I only want to get a sprite if they have the grounds attribute, which means if has attribute, I want to look at the sprite and the attribute ground. For the object sprites, I simply want to get all of the other sprites, which means if not has attribute, and then sprite and ground. After that, we want to go through both of these lists, which we can do with another for loop for layer in the list, ground sprites, and object sprites. And the order here is really important. Inside of a for loop, you always start with the first item, then you go to the second one, and so on. And in our case, we always want to start with the ground sprites. After we have that, I want to do the for loop for the actual sprite drawing. And then instead of self, I want to get the layer. If I now run main.py again, we have the background always in the background. And the logic for the sorting still works just fine. So the player can be behind a tree and in front of a tree. This would also work on a pillar, so there we have both sides, and everything else still works just fine. So I am very happy with that. Although I feel like inside of the player, we could subtract an even larger number. Let's say -90. If I now run this again, we should be getting a much greater overlap. And we do. This is actually much nicer. So quite happy with that. Now the game is feeling much more three-dimensional. And on top of that, we have a proper camera. So with that, we have another really important part of the game. Next up, we have to work on the proper animations of the player. With that, it looks like the player is actually walking around. Now, we have already seen basic animations, and we are going to keep the basic logic. Or in other words, we're going to import images and then update self.image inside of a sprite. However, we need to add state management. For example, if the player is moving to the right, then we want to play the right animation frames. On top of that, if the player stops moving, then we want to stop the animation. And I think looking at the project folder is going to help a bit here. If we go to images and the player, there we have the 4 different states. For example, if I click on right, we have 4 frames with the player walking to the right. And in practice, for self.frames, we are going to have a dictionary where we have a state and then the value is a list of surfaces. The states could be left, right, up, and down. After we have that, inside of animate, we have to get the state first, and then we're updating self.image with the surfaces. First of all, for that though, we have to do a couple of imports. And for that, we have an issue, because for the player, we have to import quite a few things. So for each folder, we have 4 different surfaces, and that we want to import all at once. And I want to avoid importing all of this manually. Back in the code, I want to work inside of player.py, and let me minimize everything. There we go. To get started, we want to import all of the surfaces for the player, and that I want to do in a separate method. Let's call it load images. No need for custom parameters, and in there, we want to create self.frames, which is going to be a dictionary with 4 key value pairs. We have the left state, and the associated value for now is going to be an empty list. This we want to duplicate 3 times, because the other states are right, then we have up, and we have down. Really important at this point, the names of these keys have to match the folders inside of the player, because in just a second, we are going to use them for the path. Essentially, we want to look at the player folder and then go over all of the subfolders. For that, we will need another Python method that so far we haven't seen yet, or rather, you have seen it, but I didn't talk about it. If you go to settings, there we have from OS import walk. And walk is allowing you to, well, walk through a folder. The way you're using walk is you call walk, and then you have to insert a file path, which we are also going to do via the join method. I want to go to images and then to the player. After we have that, I want to print the result. Although for that to work, we have to call the load images method, which we need to do before we are creating an image. Self.load images, and now let's run main.py, and we are getting a generator object. Not particularly useful, but what we can do is to wrap all of this inside of a list function. That way we can see the content. Let's try it again, and there you get a list with a whole bunch of information. I think to see all of this a bit better, inside of player, let's put all of this into a for loop. Or in other words, I want to cut out the walk method and then do for info in walk. Inside of that, we are going to print info. If I now run main.py, we are getting something much more readable. We are getting 5 tuples returned. And the first value that we are getting returned is just a little bit different compared to the other values. Although generally, you're always getting 3 values returned. The first one is the folder path you are currently in. The second value is all of the subfolders, and the final value are the file names. So basically what is happening here is the first entry that we are getting is the parent folder, or images and player. In there, we have the subfolders down, left, right, and up, and no other actual files, like PNGs, for example. After we have that, we are going through all of the subfolders, which means we have down, left, right, and up. In all of those folders, we don't have any subfolder, which means the second value is an empty list. However, the third value is going to be all of the PNG files in this folder. Although I should be specific here, we are not getting an actual file. We are simply getting the name of one. So how can we use that to actually import all of the data? And first of all, we know that we are always getting three values returned. We are getting the folder path, we are getting the subfolders, and finally, we're getting the file underscore names. And in our case, we only want to look at the folders with actual file names, which means if file names. That way we are ignoring the parent folder. Or in other words, we are looking at down, left, right, and up. If that is the case, I want to look at all of the individual file names for file underscore name in file names. If I print that file name and run main.py, you can see that we are getting 0 PNG, 1 PNG, and so on. Those are all of the file names. And if you combine that with the file path, you can get the full underscore path, for which we can use the join method once again. I want to combine the folder path with the file name. The return value, if we are printing full path inside of main.py, is going to be the proper path to all of these files. And that we can use to import a surface. All we need is pygame.image.load along with the full path, and then convert underscore alpha. That would be giving us a surface, but so far this isn't useful because we have to get the surface into the appropriate list. So how can we combine this dictionary with this for loop? And well, we simply need another for loop for state in self.frames.keys. And as a reminder, the keys of the dictionary are going to be the states of the player. Left, for example, is the left running animation. After we have that, I can indent the inner for loop and then update the join method. We want to go to images, player, and then get this state, the one that we are getting from the dictionary. Once we have that, we can get self.frames along with the state and then append the surface to the list. At the end of all of this, I can print self.frames, and if I run the game, we are getting a dictionary where we have a state, for example, left, and then the associated value is a list with a whole bunch of surfaces. That is all we need for the import. Although sometimes you do want to be a bit careful here. When you're going through the file names, you are not guaranteed to have them sorted, which is really important for an animation. Or in other words, when you're looking at these animations, let's say for right again, we always want to start on 0, then go to 1, then 2, then 3, and then so on. You really want to make sure that these are sorted from the lowest to the highest value. If that isn't the case, you're going to get some really weird behavior. Fortunately, in our case, we know how to sort things. So when we're getting these file names, we want to sort them, for which, once again, we are going to need a key. Because remember, inside of file name, we are getting something like the string 0.png. And we want to extract the 0 from that. Which means, for the key, we want to have a lambda function with a name. And on this name, we want to split it wherever we have a dot. That way we are separating the actual file name from the file ending. And we only care about the name, so index 0. All of this we want to convert to an integer. That way the string 1 or string 2 would become an actual number that can be sorted. Now the result in my case is not going to be visible, but it is a good safeguard, so I would always recommend to include it. Anyway, with that, we have covered the import. Next up then, we can actually create an image. For that though, we will need self.state and we will need self.frame_index. The state for now can simply be down and the frame index is going to be 0. Finally then, we can create, let's do it right before the update method, define animate with self and delta time. There are two things we have to do in here. Number one, we have to get this state. Number two is the actual animation. And let's start with the basic animation. I want self.frame_index plus equal some kind of animation speed. Let's say 5 multiplied with delta time. After that, self.image is going to be self.frames. Then we will need self.state. And on that, we can call integer self.frame_index with modulus of length and self.frames with the same self.state. That should give us a very basic animation, although we have to make sure that we are actually calling self.animate with delta time. If I now run main.py, we're getting a down walking animation. All we have to do now is update self.state to get a different kind of animation. For example, if I set the starting state to right and run this again, now the player is walking to the right. For that, we have to cover this state. The way you want to think about it is, how do we know if the player is walking to the right? And in my case, I know that from the direction. So if self.direction.x is greater than 0, we know the player is walking to the right. Or rather, the way I am approaching this is if self.direction.x is different from 0. Then I want to get self.state and set it to right if self.direction.x is greater than 0. If that is not the case, else it should be left. With that, I can go right, I can go left, and we get the proper animation. That is looking pretty good. The same thing we can also do for the vertical movement. I simply want to duplicate those lines and then check for self.direction.y, and self.state is going to be down if self.direction.y is greater than 0. If that is not the case, we are going up. Let's try this again, and now I can go in all 4 directions. That being said, there's one limitation at the moment. That is that the player never stops walking. So even without any keyboard input, the player is walking to the right. And if I go around and stop moving, the player keeps on walking. And fixing that is going to be your exercise. I want you guys to only display the first animation frame if the player doesn't move. Really important here, keep the current direction. So if the player has been moving to the right and then stops, the player should still face to the right, but not animate anymore. Pause the video now and see if you can figure this one out on your own. Alrighty, let's try it together now. And the way I started is that we know we only want to update the animation if the player is moving. Or in other words, frame index should only change if we have a direction. Which means instead of adding some animation speed and delta time, I want to get self.frame_index plus 5 times delta time. So far, no change. But then we can add an if statement that we only want to do all of that if self.direction is the case. If that is not the case, else frame index should always be 0. That is actually all we needed. I can now walk around, and if I stop moving, the player doesn't animate anymore. And this works pretty well. And by now, our player is actually becoming a fairly complex class. So we have 65 lines of code, and we are doing quite a few different things. But fundamentally, for example, for animate, there isn't really anything too complex in here. We are simply checking if the player is walking left or right, Then we are looking at the frame index and updating it if the player is moving, or setting it to 0 if he is not. Finally, we are updating the image with the frames, the state, and then the frame index. I hope none of this is too complicated. I suppose the one slightly challenging part is going to be the import. So I hope it still made sense. If you're massively confused, let me know in the comments. Next up, we have to add the gun. And fundamentally, this isn't going to be too difficult. We simply have to float a sprite around the player and then rotate it. That's kind of the basic idea. But the details can get a bit more difficult. Let's go through it one by one. In the most basic sense, the gun is just another sprite that rotates around the player. The only really difficult part is to get the angle. Or in other words, we want to get the angle between the player and the mouse. However, the mouse position is always going to be on the display surface. So in our case, between 0 and 0, and the display width and height. The player, on the other hand, isn't linked to those dimensions anymore because of the camera. As a consequence, we would need to do one of two things. We could either get the offset of the camera and include that in the calculations, which would be possible, but kind of a headache. Instead, what is much easier is to use the fact that the player will always be in the center of the window. Because of that, if this is our display surface, we know that the player is always right in the center. So all we need to know is what is the relationship to the mouse to this point. Are we up here? Are we here? Are we here? Are we here? And we always want to know what's the angle to the center of the window. That is actually all we need to know. For all of that, I want to work inside of the sprites, minimize the other classes, and then create another class called gun, which also needs to be a pygame.sprite.sprite. We will also need a dunder init method with self, the player, and the groups. I suppose to get started, we want to have the player connection. For that, we want to store self.player, which is going to get the player. Then we will need a distance to the player, which I have set to 140. Next, I want to have another attribute called player_direction, which is going to be a vector 2 with a default direction of 1 and 0. This value we are going to update later. It's basically going to be the direction from the gun to the player. This will be super important to rotate the gun. But first of all, we have to set up the sprite. So sprite setup, and in there, super dunder init with the groups. Besides that, we want to have self.image and self.rectangle. Although, truth be told, since we want to rotate this image later on, we also want to store a let's call it gun_surface. This we get with pygame.image.load. I want to use the join method and then go to images. There we have the gun. And in that folder, we have gun.png. Or in other words, if I go to images, there we have gun, and there we have gun.png. In the same folder, we also have the bullet. That one we are going to use later. Also, as always, do not forget convert alpha. Then for self.image, we simply want to get self.gun_surface. Finally, for the rectangle, I want self.image.getFrectangle, in which we want to place the center of the gun. For the position, imagine that this is the player and the player center is here. From this point, we want to go in the player direction by the distance, and then place the center of the gun. Or in other words, at the moment, we want to go to the right by 140 pixels, and then place the center of the gun. The math for that is actually fairly simple. We first of all want to get self.player.rect.center plus self.player.direction multiplied with self.distance. With that, we have the gun right next to the player. That means inside of main.py, I am already importing the gun from the sprites, so that we don't have to do any more. Besides that, in the setup method, after we have the player, I also want to create one instance of the gun and store it in an attribute. Self.gun is going to be gun with two arguments, self.player, and for the groups self.allsprites. If I now run the game, we have a gun right next to the player. That being said, if the player runs around, the gun doesn't update with it. That we can fix quite easily, because inside of the gun, I want to have an update method with self and delta time. That being said though, for this class, we don't need delta time. To indicate that, I'm going to add an underscore. For now, all that we want to do in here is self.rect.center is equal to self.player.rect.center plus self.player.direction multiplied with self.distance. The very same thing that we have done just a second ago. And I hope the logic here makes sense. Initially, when we are getting the position for the gun, we are placing it right next to the player. But then we also have to check if the player position updates. And then we are always placing the gun relative to the player. That way later on, we simply have to change the player direction, and then we get a different position. Although first of all, let's try all of this. If I now run around, the gun follows the player. On top of that, what I can do inside of the gun, for the direction, let's go with 0 and 1. With that, the gun should be below the player. So that is working pretty well. That means, next up, I want to self get underscore direction. That is going to be just another method, get direction, without any custom parameters. Most importantly in there, we will need the mouse position and we will need the player position. Both of those are going to be vector 2s. That will make the math a lot easier. The mouse position we can get very easily. pygame.mouse.get position. Don't forget to call this one, and this will return a tuple with an x and a y position, which we can pass right into a pygame vector 2, and then we have a vector. For the player position, you might be tempted to go with something like pygame.vector2 and then self.player.rect.center. The same thing we have done earlier. This would not work, simply because inside of the display surface, we have a top left position of 0 and 0, and we can only go as far as the window width and window height. And the mouse position cannot leave this area. The smallest mouse position is going to be 0 and 0, and the largest one in my case is going to be 1279 and 719. Or 1 pixel short of the display width or height. That is because we start counting from 0. But the same logic does not apply to the player. Since we have a camera, the player could actually be somewhere down here, with an x and a y position of, let's say, 600 and 4000, way below the display surface. And we can only see the player because we are offsetting all of the graphics. And this does work for the game, but it would not work to get the angle between the mouse position and the actual player position. And that we have to account for, which in our case is fairly simple, because we know that the player is always in the center of the window. Or in other words, we have window width divided by 2 and window height divided by 2. That is all we need to get the player position relative to the mouse. And after we have that, we simply want to get self.player.direction and set it to the mouse position minus the player position. And this vector we want to normalize. And that is actually all we need. I am not going to talk too much about vector math, but essentially what we are doing here, if this is the display surface, we have the origin point in the top left, then we have the player in the center, and let's say our mouse could be here. What we want to get with the player direction is this new vector that goes from the player to the mouse position. And to get that, you want to get the endpoint and subtract the start point. This is a common operation and very basic vector math. Anyway though, for now, let's simply print self.player.direction. With that inside of the game, I can move my mouse around, and this is working pretty well. Also, you can see in the bottom left, if I move the window just a bit to the side, If my mouse is all the way on top of the player, like this, the mouse is perfectly on top of the player, and then we get 0 and -1. If I go a bit to the right, eventually we would get 1 and 0. Below, we would get 0 and 1, and then -1 and 0, at least roughly. It's a bit hard to get the exact point, but you get the idea. That being said, we also want to rotate the gun surface. For that, I want to have another method, rotate_gun. No need for custom arguments, we simply want to create rotate gun. Ultimately, what we want to do in here is self.image and then get pygame.transform.rotoZoom. With self.gun surface, really important at this point, do not use self.image. We always want to start the rotation from the original surface. After that, we will need some kind of angle, and for the scale, we want to stick to 1. So then, how can we get the angle? That is going to be a local variable, and for that, we want to use atan2, which we have to import. All the way at the top, I want from math import atan2, also degrees. Alright, so question, what is atan2? And well, imagine you have a right-angled triangle. And what atan2 wants is a width and a height. Once it has those, it is going to give you the angle of the triangle, which is exactly what we want. Although it's going to return all of that in radians that we have to convert to degrees, and for that we are importing degrees from the math module. And by the way, all of this is trigonometry, which is another really important part in game development. You at the very least want to know what sine, cosine, and tangents do. This topic isn't too difficult, and I guess let me know if you want a separate tutorial on that. Anyway, what we want is to call atan2, and then we have to insert the two sides with self.playerDirection.x and self.playerDirection.y. All of this is going to return an angle, but this angle is in radians, while we need degrees. For that, we can use degrees, the thing we have just imported, to convert all of this. And with that, I can run main.py, and we are getting something. Let me show my mouse actually. You can see that the gun is rotating, but it's not rotating in the right way. To fix that, we have to subtract 90 from the angle. If I run that, we have the gun rotating properly. That is much better. The issue here is that the starting point of these angles is simply different, which we can account for very easily. Although there's one more issue. Let me actually show main.py. If my mouse is on the right side of the player, this is working perfectly fine. But if we are on the left side, then the gun should be flipped around. Otherwise, it's going to look a bit funny. We simply want to check if self.playerDirection.x is greater than 0. That means we are on the right side of the player. If that is the case, self.image should do this. However, if that is not the case, else, meaning the mouse is on the left side of the player, then I still want to get a rotated image. But on top of that, self.image should also be pygame.transform, and we want to flip the entire thing. For that, we want to get self.image and rotate it not on the horizontal axis, but on the vertical one. So false and true. I can now try all of this again, and it's not going to work just yet. The right side is working, and on the left side, we are getting some funky behavior. To understand this issue, let's print the angle that we are getting and run main.py again. If we now go to the left side, you can now see that we are getting a negative value from -90 all the way to -270. And those values being negative is the entire issue. Because of that, the gun is rotating in the wrong way, which we can fix very easily. We simply need the absolute value. Let's try all of this again, and now the gun is behaving just in the right way. So this is looking really good. That means we don't need the print statement anymore, And we have the gun rotation. Although for the proper gun, we are going to need a bullet. That part is going to be your exercise. What I want you guys to do is when the player presses the left mouse button, then launch a bullet in the direction of the gun. On top of that, the bullet should start at the end of the gun. So it looks like the gun is actually firing all of the bullets. Should be reasonably straightforward. Pause the video now and see how far you get. First of all, we have to figure out where to capture the input for the mouse button. And that we can do either in the game class or inside of the player. I'm going to go with the game class because in here we also want to create the bullets in just a bit. That means I want to create define input with self and then check if pygame.mouse.get_pressed. Don't forget to call this one, and via this method we are going to get all of the mouse buttons. Although we only care about the left one, which is the index 0. If that is the case, I want to print shoot for now. After we have that, inside of the run method, before we are updating everything else, I want to get self.input. Let's try, and this is working reasonably well. The issue is that we are checking this input on every single frame of the game, which would give us way too many bullets. So we have to moderate things quite a bit, which we have already seen. I want to add another condition and self.can_shoot. If the if statement then triggers, self.can_shoot should be false, and we want to get self.shoot_time, which we get via pygame.time and get ticks. Now for that to work inside of dunder init, we don't need the sprites anymore, but I do want to have a gun timer, for which we have can shoot. This one should be true by default, and self.shoot time. The default value for this one will be 0. Besides that, I want to have a self.gun cooldown, which I have set to 100 milliseconds. Or in other words, in the game, we can shoot 10 bullets per second. Perfect. Once we have that, we will also need another method with the gun_timer, for which we want to check if not self.can_shoot. If that is the case, we basically want to get the current time via pygame.time.getTicks, and then check if the current time minus self.shootTime greater or equal to self.gun cooldown. If that is the case, self.canShoot is going to be true. And finally, inside of the run method, we can do that before we are capturing the input self.gun timer. With that, inside of the game, if I hold down the mouse button, we are still getting a lot of input, but a lot less than before. And if I change the gun cooldown to something like 600, it should be much more visible. There you can see we get one shoot printing every 600 milliseconds. So that was the first part. Next up, we have to figure out, whenever we are getting this input, we want to create a bullet. Or in other words, I want to create an instance of a bullet class, for which I'm going to need a surface of a bullet, a starting position, a direction, and then the groups. For all of that, I want to go to sprites and then create, all the way at the end, another class called bullet. Once again, we are creating a pygame.sprite.sprite. Then we will need a dunder init method with self, the surface, the position, a direction, and the groups. Next up, we will need to call super dunder init, has the groups in there, and then we have to create self.image and self.rectangle. Those two are actually fairly simple because we already get a surface via the parameters, and self.rectangle is simply going to be self.image dot get f rectangle, in which we are placing this center. And once again, we are getting the value via the parameters. So now we have to figure out all of the arguments. The surface is the easier part because if you look at images, there we have gun and the bullet. This is what we want to import. For that, I want to create another method called load images. For now, in there, we are only going to create a self.bullet surface, which we can get via pygame.image.load. And then via the join method, we go to images, gun, and bullet.png. Also, we want to convert alpha, all of this once again. And that's all we need inside of this method for now. Although in the next section, we're going to reuse this to import all of the enemy images as well. But for now, that's not really an issue. That being said though, we do have to call it inside of the setup method. I want self.load images. With that, we have a surface, self.bullet surface. Next up, we will need a position. And for that, I want to create a separate local variable. Now for the starting position, we obviously want to start on the bullet itself, which means self.gun.rect.center. And then add a bit of an offset in the direction that we are currently facing, which means plus self.gun.player direction multiplied with some value, depending on how much distance you want. In my case, I went with 50. On top of that, for the direction of the bullet, we simply want to reuse the gun direction, or rather the gun player direction. Finally, for the groups, I want to have a tuple with self.allSprites and self.bulletSprites, a group that does not exist at the moment. But inside of dunder init, I can duplicate the collision sprites and then create bullet_sprites. That should actually be it for the bullet. If I now run all of this, and let me show my mouse, if I press a button, we are getting a bullet. We can also walk around, and this is working pretty well. That being said, while testing this game, I realized that the input is a bit clunky because we are using the mouse input, and then inside of the player for the input, we are checking for the arrow keys, which makes it kind of awkward on the keyboard. To fix that, what we can do is check either keys pygame.kwrite or the keys along with pygame.k_d. That would be the D key on the keyboard. The same thing we have to do for the other side. So on there, we want to check for the A key. Then for self.direction.y, when we are checking down, I want to check for k_s if we're going down, or k_w if we are going up. And that should be it. If I now run main.py, I can walk around with WASD or with the arrow keys. We are getting the same result. Besides that, the bullets also work perfectly fine. I can even hold down the mouse button and we keep on creating bullets. They do not move, but that we can fix right now actually. All we have to do inside of the bullet, we first of all need a few more attributes. I want to have self.direction, which we are getting from the direction parameter. Then self.speed, I set this one to 1200. And then we can create an update method with self and delta time. All that we really want to do in here is self.rect.center plus equal self.direction multiplied with self.speed multiplied with delta time. With that, if I shoot a bullet, the bullet actually moves in the right direction. So this is looking pretty good. However, at this point, we do have to be careful because these bullets never disappear. And if we can create 10 bullets per second, we very quickly end up with way too many bullets. So there should be some way to get rid of these bullets. You could either delete them when they collide with an obstacle, or you could add a timer. I'm going to go with a timer, which means I want to get self dot, let's call it spawn time, which is going to be pygame.time.get ticks. On top of that, I want to have self.live time. I want these bullets to live for 1 second. After that, inside of the update method, if pygame.time.get ticks minus self.spawntime is greater or equal to self.lifetime, then we want to kill the sprite. To make sure that this is working, inside of the run method, we can do this one all the way at the end. I want to print self.bullet sprites. If you simply print a group, you get the number of sprites inside of it. Or if I run all of this, I can press space and we're getting the number of sprites. And there you can see the bullets work just as before, but we at the most get 2 sprites. So that part is actually working pretty well. Although I realized the reason why we are getting so few bullets is because the gun cooldown is 600. This should only be 100. Let's race again, and now we're getting a whole bunch more bullets, but only 10 at the most, which is a really good thing for performance. But anyway, with that, we have the bullet mechanic, which gets us very close to a complete game. The only major thing that we now have to add are the enemies. That's going to be the next section. We are nearly done with the game. The last major part that we have to cover is how to add the enemies. For that, we have to go through a couple of steps. First of all, we will need a timer that triggers twice per second. And every time it triggers, we want to create one instance of the enemy. And that enemy needs to do a couple of things. It always needs to walk towards the player, and it needs to be able to collide with objects. On top of that, it should always play a walking animation. And for that, we will also need to import the animation frames. I think at this point, all of this is reasonably straightforward. As a consequence, all of this could be an exercise. So try to figure this one out on your own and see how far you get. Back inside of the game, I want to work inside of sprites and create another class called enemy, which, as before, is going to be pygame.sprite.sprite. Then for the dunder init method, I want to get a starting position, a bunch of frames, the groups, the player, and the collision underscore sprites. After we have that, super dunder init with the groups. Also, I want to store the player as an attribute, i.e. self.player is the player. That player, by the way, we need to get the proper direction of this enemy. Also, I can see an issue right away. I have a typo inside of pygame. After we have that, we want to create the image. For that, at the moment, we have an issue because we don't have a single surface, or rather later on, we are not going to have a single surface. Instead, we have a whole bunch of frames. The walking animations we are importing. If you look at the images folder, there we have enemies. And for example, for the bat, we have 0, 1, 2, and 3.png, which are all one part of the walking animation. Or I guess for the bat, the flying animation. To account for that, I want to create self.frames and self.frame underscore index, which is going to get frames and 0. After that, we can create self.images, which is going to be self.frames, and then we use self.frame index for the indexing. Also, what we could be setting in here is self.animation underscore speed. I went with 6 for this one. Next up, we have to figure out the rectangle, which ultimately is going to be self.rectangle, self.image.get underscore f rectangle. We want to place the center, and the value will be the position from the parameters. On top of that, I want to create self.hitbox underscore rectangle, which we get via self.rect.inflate, and I want to reduce the size of this by -20 and -40. Besides that, I also want to store all of the collision sprites as an attribute. meaning self.collision_sprites is collision sprites. Nearly done. Besides that, we also want to have self.direction, which is simply a pygame.vector2 without any values, and I want to have self.speed, for which I want to go with 350. That is quite a bit. Next up, inside of the game class, I want to create a timer, which we can do right below the gun timer. We also want to have an enemy timer. For this timer, I want to use the event loop, which means I want to have an enemy event and then create pygame.event.custom_type. After that, pygame.time.set_timer with self.enemy_event and 300. Also, I want to create one more attribute, which is going to be the spawn_positions. By default, this will be an empty list. The reason why we are going to need this one, if you look at tiled, we have on the entities layer all of the markers. And at the moment, we are only using the player one, this one here. But we also want to use all of these other enemy markers for a random starting position, which basically means we want to place the position of all of these markers inside of this list. That way we can very easily pick one of them. To get that, we want to look at the setup method, because in there we are already getting all of the markers, although at the moment we only look at the player. If that is not the case, else I want to get self.spawnPositions and then append obj.x and obj.y. After we have that, we can work inside of the event loop, because now we can check if event.type is equal to self.enemy_event. If that is the case, I want to print spawn enemy. If I now run all of this, we are getting an attribute error. That game object has no attribute spawn positions. And I think I know what the issue here is. Inside of the init method, we are running the setup method here, but only afterwards we are creating the spawn positions, which means when we are trying to append a value to the spawn positions, this attribute doesn't exist at the moment. Fixing that is super easy. We simply have to move the setup method all the way to the bottom. And I guess while we are here, I think it's also going to be a good idea to move load images right before. With that, we can create a more general setup section, which feels a bit cleaner. Also, before we are trying all of this, I realized that I am printing the bullet sprites inside of the game loop. If I now try all of this, we're getting spawn enemy every few milliseconds. Every 300 milliseconds to be a bit more specific. Now that we have that, whenever this event occurs, we want to create an enemy, for which we are going to need first of all a position. That part is quite easy. We want to get choice and self.spawnPositions. Now choice we have to import all the way at the top from random import randint and choice. Next up, we have to get a whole bunch of frames, which we can't really do at the moment. Let's leave this one empty for now. For the groups, I want to have a tuple with self.allSprites and self.enemy_sprites. This one does not exist at the moment, so I want to duplicate the bullet sprites and rename this to self.enemy_sprites. Next up, we need a player. That is simply self.player. And for the collision sprites, we want to have self.collision sprites. Nearly done. We are just going to need all of the frames. And for that, I want to work inside of load images, because in there, we want to do all of the imports. This is going to be quite similar compared to what we have done inside of the player. There we have load images, and we have used the walk method to walk through this folder. Something similar I do want to do, although first of all, I want to get all of the available folders, which for the player I have kind of done in a janky way. I simply created a dictionary with all of the folder names. But this isn't particularly elegant, because ideally I want to get these values dynamically generated, which we can get via the walk method. I can simply get join, then go to images and the enemies, and then turn all of this into a list. On this list, I want to get index 0, or the first item. If I print that folders and run all of this, we are getting name frames not defined. That's okay for now, but we are also getting this value here, where we have the name of the folder and then a list of all of the subfolders. This is what I actually want, which means I want to have index 1. That way I'm getting all of the folder names. After we have that, I want to create self.enemy_frames, which is going to be an empty dictionary. And then for folder in folders. In there, I'm going to get a folder path. I would be getting the subfolders next, but those I don't care about, so an underscore, and then the file underscore names. For all of this, in walk, join, we want to go to images, then we want to go to the enemies, and then we want to get the folder. Once we have that, we can create self.enemy_frames and create a key value pair. The key should be the name of the folder, and the associated value is simply an empty list. After that, for file underscore name, in file names. First of all, we will need a full underscore path that we can create via the join method. We simply want to combine the folder path with the file name. And then we can create a surface, or rather, we can import a surface via pygame.image.load with the full path and convert alpha. Finally, I want to get self.enemy_frames with the folder key and then append the surface. Nearly done. The last thing that I want to do is to sort the file names. So sorted method, and then we want to use a key which is going to be a lambda value with a name parameter. This name at the moment is something like 0.png. And we want to extract the 0 and convert it to an integer, for which we need name.split. We want to split this thing wherever we have a dot, and then pick index 0. After that, we want to turn all of this into an integer. And with that, we're getting all of the frames. After this method, I want to print self.enemy_frames and run all of this. Now we are going to get a name error again, because we are not using frames inside of the enemies. But before that, we have a larger dictionary where the key would be an enemy. And then we have the walking animation. That is actually all we need. So we don't want the print statement anymore. Instead, when we are creating one enemy, I want to use the choice method to pick one of the enemy animation frames, which I can do via self.enemy_frames and then get the values. Although this wouldn't work immediately because choice cannot work with values directly. What we need to do instead is to turn all of this into a list. If I now run all of this, we are getting an attribute error that non-type object has no attribute getF_rectangle. Let's have a look for that inside of the player. I simply have a typo. This should be self.image, not self.images. With that, let's try all of this again, and the game doesn't crash anymore, and we can see a whole bunch of enemies in random positions. So that is working pretty well. For these enemies now, we have to do two things, both of which are going to happen inside of the update method. I want every single enemy to move along with delta time and to self.animate, also with delta time. Move we can do later because this one is getting a bit more complex, but for animate, we simply have to call self.animate with delta time once again. Then we want to increase self.frameIndex, or in other words, plus equal self.animationSpeed multiplied with delta time. After that, self.image is going to be self.frames with integer of self.frameIndex modulus length of self.frames. That should give us an animation. Let's try, and there we go. This is looking pretty good. If I find a skeleton, those also work fine. Perfect. That looks pretty good. Next up then, we have to work on the move method. For that, we need to do two things. Define move with self and delta time. In there, we need to do broadly two things. We first of all want to get a direction. And after that, update the rect position. Really important for the rect position, we also want to include the collision logic. But step by step. First of all, we want to get the direction, for which we are going to need the player position and the enemy position, or the position of this class. I am using enemy position here to keep things a bit more understandable. Also, both of these values should be vector 2s, i.e. pygame vector 2. And for the player position, we simply want self.player.rect.center. For the position of the enemy, we also want to have a pygame vector 2 with self.rect.center. And for self.direction, we simply want to get the target position, i.e. the player position, minus the enemy position. The same thing we have done for the gun. And all of this we want to normalize, which means I want to add normalize at the end of all of this. That way, when we are doing the movement, we can simply multiply the direction with the speed, and we always get a consistent result. Speaking of which, for the basic movement, all we want to do is self.rect.center plus equals self.direction multiplied with self.speed multiplied with delta time. With that, if I run main.py, all of the enemies are moving towards the player. That is working pretty well. But without collisions, this is going to look just a bit silly. Which means we also want to add a define collisions with self and then the direction. Now for that, I am going to go to the player and then simply copy the collision method. And then we can update the movement. Although I do have to mention, this is not elegant. Ideally, you would use inheritance to create a parent class for the enemies and the player that has the collision method. That way both of them can inherit the same method. So we don't have to copy paste things. We are going to do something like that later on, although for now I want to keep things simple. Anyway, I first of all want to split the movement into horizontal and vertical parts, which means we want to update self.rect.centerx by self.direction.x multiplied with self.speed and delta time. Then for the vertical movement, self.centery plus self.direction.y multiplied with speed and delta time. Now you could also go, and this is what we have done for the player, you could go with x and y. I suppose we could actually do that, self.direct.x and self.direct.y. That just feels a bit cleaner. Also, we are not using the hitbox yet, but that's going to come in a second. Now, after we are doing the horizontal movement, I want to call self.collision with the horizontal collisions. This I can then duplicate, because after we're doing the vertical movement, we want to check the vertical collisions. If I now try to run main.py, this is not working. And I think I know why. Inside of collisions, we are using the hitbox rectangle, but when we are doing the movement, we are using the rectangle, which isn't ideal, so instead of the rectangle, I want to use the hitbox rectangle. Although for that to work then, at the end of the movement, we have to set self.rect.center to self.hitboxrect.center. With that, we should get the hitboxes and the proper collisions. Let's go up here, and we should be able to see that the monsters are also constrained by the environment. So that is working really well. And with that, we have the enemies. We are nearly done with the second game. We just have to add some minor bits to finish up the entire project. There are two major things that I want to work on. Number one are the collisions, so that if an enemy gets hit, it disappears, and if the player gets hit, the game ends. On top of that, we need to add some audio, which should be fairly straightforward. In fact, this could be an exercise right away. I want you guys to add the collisions between the bullets and the monsters. If a bullet hits a monster, then kill that monster sprite. On top of that, add all of the sounds. I want to add another method. Let's do it right before the run method. Define bullet underscore collision. No need for custom parameters. And in there, we need to check if we have bullets in the first place. For that, inside of dunder init, we know that we have a bullet sprites group. That we can use simply by checking if self.bullet sprites. If we don't have bullets, there's no reason to check any of these collisions. If, however, we do have some, then we want to check for bullet in self.bullet sprites. Next up, we want to check the collision underscore sprites, which we get via pygame.sprite.sprite collide, in which we need a single sprite, a group of sprites, and then do kill. For now, the single sprite is going to be the bullet. The group is going to be self.enemy sprites. And do kill is going to be true, although this we are going to change later on. After that, inside of the run method, when we are updating the game, I want to call self.bullet collision. I can now run all of this, and if a bullet hits an enemy, the enemy disappears. So that is looking pretty good. That is looking quite nice. So now we can refine all of this. First of all, what we can do is use a mask for the collision via pygame.sprite.collide mask. That way we are using a mask for the collisions, meaning we have a lot more precision. That being said, most of the objects that we are working with, for example the bullet or the bats, are fairly rectangular, so this isn't going to make a massive change. What is going to be much more noticeable is that I want to have a delay between the bullet hit and the sprite death. For that, I want to set do kill to false. And after that, check if we have collision sprites. If that is the case, I want to go through all of them, i.e. for sprite in collision sprites. And then call a method sprite.destroy. This destroy method does not exist at the moment, but we can create it inside of sprites, the enemy class. I want to have a method called destroy. Inside of this method, there are fundamentally two things that I want to do. Number one, I want to start a timer. Once this timer runs out, we are actually destroying the sprite. Besides that, I want to change the image. Once a sprite has been hit, we want to change the entire thing to a white surface. That's the part we can work on right away actually. For that, I want to create a new surface via pygame.mask.fromSurface and then use self.frames and 0. Or in other words, the first frame of the walking animation, this I want to turn right away back to a surface. That way, if we are overwriting self.image with the surface, we can see the mask, or in other words, we can see a silhouette that is black and white. At the moment, this is only going to run for a single frame, so it wouldn't be particularly visible. But what we can also do is set self.def_time to pygame.time.getFix. And to use this attribute, I want to work inside of the dunder init method and add a timer section with self.deftime. This one can be 0 by default, and then self.def_duration. I set this one to 400 milliseconds. Once we have that, inside of the update method, I only want the enemy to move and animate if self.deftime is equal to 0. That can only be the case if the enemy has not been hit by a bullet. Once it has been hit, however, we are overwriting this surface. That way, if I run main.py and we hit an enemy, the enemy stops moving and we get this silhouette. So that part is working pretty well. That being said though, I only want to get the white part, which we can get via surface and set underscore color key that we are going to use to remove all of the black pixels. Via that, I can shoot the enemies and we only get the white outline. That works pretty well. Next up then, I want to create a def underscore timer. That is going to check if pygame.time.getTicks, or in other words, the current time. From that, we want to subtract self.defTime, and if the resulting value is greater or equal to self.defDuration, then we want to kill the sprite. And to call this def timer, we want to check if the def time is different from 0. Or in other words, else self.defTimer. Inside of the game, I can now hit the enemies and they do disappear after a short amount of time. So that looks pretty good. On top of that, the last thing that we need for this collision is once a bullet hits an enemy, the bullet should also disappear, which we can do very easily. If there are collision sprites, I want to kill the bullet. Let's try this one, and if I hit a bat or any of the enemies, the bullet also disappears. A bit hard to see, but you get the idea. Anyway, with that, we have the bullet collision. Besides that, I want to have another method with player underscore collision. All we want to check in there is pygame.sprite.spriteCollide with self.player, self.enemy, sprites, and for do kill, I want to go with false. Although this value doesn't really matter. All that we want to do is check if there's any return value. And if that is the case, self.running should be false. Finally, to make all of this work, besides the bullet collision, we also want to have self.player collision. Now, truth be told, you could combine these two collision methods, since for both of them, we are not doing very much. But I think it's a bit better organized if you have them separately. Anyway, let's try. And if I now collide with an enemy, the game simply ends. I suppose what we should also be doing is use a mask with pygame.sprite.collide mask. This part is actually really important, because remember, the surface of the player is actually really large, which means that the collision would actually be really easily triggered. But if we do include it, you can see that we have to hit an enemy straight away. Now, for the balancing of the game, I didn't spend too much time on it, so it is very, very easy to die. And you might want to include a health mechanic, but that you can do in your own time. The last thing that I want to add are the sounds, and then we are done with this project. For that, I want to work inside of dunder init and add an audio section. We don't really have that many audio files. If you look at the audio folder, we have an impact sound, a music sound, and a shoot sound. To import all of those, we want to have self.shoot_sound, which we get with pygame.mixer.sound. Then we will use the join method to go to audio and then shoot.wav, for which I also want to set the volume right away. Shoot sound.set volume with 0.4. Besides that, we have self.impact_sound, which we can get with the same method that we have used for the shoot sound. The only thing that we have to change is that this is impact.ogg. Finally, we want to have self.music. One more time, we will need pygame.mixer.sound, go to audio, and then import music.wav. And I realized there's a typo, this should be OGG. Cool, that covers all of the imports. If I now run the game, it doesn't crash, so that looks pretty good. Meaning we just have to figure out when to play these sounds, and then we are good to go. For the shoot sound, I want to check the input, because in here we are creating a bullet. which means I can get self.shootsOund and play the entire thing. That sounds pretty good. Cool. After that, we have the impact sound, and this we check when we have a bullet collision between the enemies and the bullets. Or in other words, if there are collision sprites, we want self.impactSound.play. That should be all we need. If I now hit an enemy, we're getting a sound. Finally, we will need the background music. And that part is the easiest because the music we want to play right away. Self.music.play. And for loops, we want to have -1, so this one plays forever. And I think for the background music, we do want to set the volume a bit lower. Self.music.setVolume to 0. Let's say 0.3. And with that, that is working pretty well. Now, this game isn't terribly well balanced, so what you could be doing, for example, when you are in the sprites, you could update the enemy movement speed. The lower this one is, the easier the game will become. You could also work on the timer. If enemies spawn less often, then they are easier to handle. On top of that, you could also add a health mechanic for the player, so that we could be hit multiple times without dying. But in my case, I'm going to call it a day at this point. For the next project, we are going to make Pong. Now, the overall game isn't going to be too difficult, but there are 3 major things that I want to focus on. The most important one are collisions between moving objects. We have already seen some basic logic for that, and we are going to refine this quite a bit. And for the collisions between the ball and the paddle, this kind of logic is fundamental. Besides that, I want to use a lot more inheritance. For example, the player and the opponent are very, very similar, so we can use inheritance to make our code much more efficient and elegant. Finally, I want to add a saving mechanic, so that when we are restarting the game, the score is sticking around. However, before we can work on any of these topics, we have to start with the setup. And this can be an exercise right away. I want you guys to do a whole bunch of things. Number 1, create a basic game loop and the player. Then get the player input and then move it up and down while constraining it to the screen. Also create a ball that bounces around the window, without any collisions yet. And finally, for all of this, use the info from settings.py. Speaking of which, here is the project folder, and we only have 2 subfolders, code and data. Data actually at the moment is entirely empty. And inside of the code, we have main.py and settings.py. Let's have a look at those 2. Here we are, and inside of main.py, we are simply importing everything from settings. In settings, we have a bit more. We are importing pygame, and then we are importing the join method. Besides that, we have window width and window height, and then finally, we have a bunch of dictionaries. For example, in there, we have the size of the paddle. This can be both the player and the opponent, and the ball. Besides that, we have various speeds, and we have a whole bunch of colors. With that system, we can customize the game from inside of the settings, which is generally a good idea. You want to have all of the really important stuff in one place, so you can make changes really quickly. And that is what I want you guys to use to create the basic outline. The end result should look something like this. I suppose I should also mention, we are not importing any images. Instead, when you're creating the player and the ball, create a surface from scratch. For now, all of those can be perfect rectangles. Anyway, pause the video now and see how far you get. I want to get started by creating a class called game. No need for inheritance, but we will need a dunder init method. In there, first of all, we want to call pygame.init and create a display surface attribute, which we get with pygame.display.set_mode, in which we want to add a tuple with the window width and the window height. I can copy all of that from settings, and then we are good to go. Besides that, we can also change the window title with pygame.display.set set_caption, and Pong. Finally, I want to create self.clock via pygame.time.clock. That should be the basic setup, although I forgot one thing, self.running for the while loop, and by default, this one should be true. After that, we want to have a run method without any custom parameters, and then while self.running. In there, we first of all want to get delta time, for which we need self.clock.tick, don't forget to call it, and then divide it by 1000. That way we're getting delta time in milliseconds. Afterwards, for event in pygame.event.get. At the moment, we only want to check if the event.type is equal to pygame.quit. If that is the case, self.running is going to be false. Next up, we have the actual game logic. In there, later on, we want to have an update part and a drawing part. At the end of the drawing part, we have to call pygame.display.update or flip. Also, after the while loop, we have to call pygame.quit. Cool, with that, we have the basic game class. Back in the global scope of main.py, I want to check if dunder name is equal to dunder main. If that is the case, I want to create one instance of the game class and then call game.run. Let's try all of this, and we are getting a black window. That looks really good. Next up, from settings.py, I want to start using the colors, and we already have a background color, which means I can copy the key from colors and then inside of the drawing method, self.displaySurface.fill with colors and BG. Let's try that. And we are getting a much nicer background color. That looks good. With that covered, we can start working on the sprites. First of all, for that, we will need self.allSprites, which is going to be pygame.sprite.group. On top of that, I also want to have self.pedal_sprites, which also is pygame.sprite.group. Pedal sprites is just going to be used to have collisions between the ball and the pedals. They are not going to do anything else. Self.allSprites, however, we want to update, i.e. self.allSprites.update with delta time, and after we are filling this screen, self.allSprites.draw on self.displaySurface. That's a good setup. Next up, inside of the code, I want to add another Python file. Let's call it sprites.py. We will need from settings and import everything. And then we have to create at the moment two classes. One is going to be the player and the other will be the ball. Although for now, let's focus on the player. This one will be a pygame.sprite.sprite. Then we will need a dunder init method with self. Then we will need the groups and an x_position. Don't forget, afterwards, we have to call super dunder init and pass in the groups. Finally then, for the sprite to work properly, we will need an image, we will need a rectangle, and I guess along with that, we also want to cover the movement. For the image, if you look at the files, we don't have a folder with images, so there's no point in trying to import anything. Instead, what we're going to do for self.image, we want to have pygame.surface, for which we are going to use settings.py. In there, we have the size of the pedal. Or in other words, size and pedal. That's all we need for now for the image. Besides that, I want to have self.rectangle, which we get with self.image.getFrectangle, in which we want to place this center. This one requires a tuple with x and y. X is going to be set via x_position, what we're going to get in just a bit from the x_position parameter. For y, we simply want to be in the middle of the window, i.e. window height divided by 2. I suppose with that, we have a very basic player sprite class that we can use right away. Which means inside of main.py, I want from sprites import everything. And then, after we have the groups, self.player is going to be the player, for which we're going to need the groups, first of all, self.allSprites and self.paddleSprites. And then we need an X position. For this one, I went with window width minus 50. I suppose you could also set this value inside of the settings. It's entirely up to you. And while looking at this, I feel like this value should be inside of settings.py as well. So what we can do, under size, we can also have a position, for which we have a player key, and the value for this one is going to be a tuple with window width minus 50, and then window height divided by 2. On top of that, I want to have one for the opponent, which is simply going to be 50, and window height divided by 2. With that set up, we don't need this argument at all. Also inside of sprites, we don't need an X position. For the center, we simply want to have pos and then get the player key. That does feel a lot cleaner. And with that, if I now run the code, on the right side, you can see the player. Doesn't do very much, and it's also not looking great, but at least we have something. First of all, what we can do to make all of this look a bit better is self.image.fill with colors, and I believe the color for this one is called paddle. That way, we're getting some more colors. Now, we are going to refine the image in just a bit, but for now, I think this is good enough. What is much more important is the movement, for which we are going to need a direction. And since the player can only move up and down, this doesn't have to be a vector. It can simply be an integer. And by default, I want to go with 0. And to move this thing, I want to have a move method with self and delta time. For now, let's add pass in here. And then I want to have a define get underscore direction, which is going to cover the input. Now, you might be wondering, why am I not calling this input? And the reason is, later on, we are going to have two get direction methods. One for the player that takes keyboard input. The other is going to be for the opponent, and this one is going to check the ball position. Since I want to call both of them at the same time, they are going to have the same name. For now, don't worry too much about it. When we get to it, I will explain it in much more detail. Anyway, for now, for get direction, we simply want to get the keys with pygame.key and get rest, and then set self.direction to the integer of keys and pygame.k underscore down minus integer of keys and pygame.k underscore up. With that, we are getting a direction. So next up, for move, I simply want to get self.rect.center y plus equal self.direction multiplied with self.speed. This one doesn't exist yet, and multiplied with delta time. To make this work, we will need self.speed, which we are also getting from settings.py. There we have the speed. This I want to turn into an attribute of this class. In other words, speed and player. Finally, we have to create an update method with self and delta time, and then call self.getDirection and self.move. That way, inside of main.py, I can move up and down. That's looking pretty good. The one limitation is that the player can leave the screen. That's no good, although fairly fixable. We want to check self.rect.top and set it to 0 if self.rect.top is smaller than 0. If that is not the case, else we simply want to keep self.rect.top. Then I can duplicate all of this and set self.rect.bottom. This one should be the window height if self.rect.bottom is greater than the window height. If that is not the case, we simply want to keep self.rect.bottom. Or in other words, we don't want to make any changes. And that is actually all we need. I can now try to run the game, and the player cannot leave the screen anymore. The same with the bottom side, so that is working pretty well. And alright, with that, we have a basic player class. Next up, we can work on the ball class, which is also going to be a pygame.sprite.sprite. And we don't need the player anymore. We are going to need a dunder init method with self, the groups, the pedal underscore sprites, and that's it for now, although later on there's going to be a bit more. First of all, as always, super dunder init with the groups. Then we need an image and the rect and movement section. For the image, at the moment, the pedal is simply going to be a rectangle, i.e. self.image will be pygame.surface with the dimensions of the ball, size and ball. On top of that, self.image.fill with colors, and I believe this one is called ball. Or in other words, we are grabbing this key value pair. For the rectangle, we want to get self.rect, which will be self.image.getFrectangle. We want to place the center straight in the middle of the window. Or in other words, window width divided by 2 and window height divided by 2. Once again, we have a basic outline of a sprite that we want to use to create self.ball, which will be one instance of the ball class, for which, first of all, we will need the groups. We only want the ball to be in all sprites. And then make sure that the ball class has access to the pedal sprite group. What I really want to mention at this point is that the ball itself is not inside of pedal sprites. It simply has access to them. A really important difference. Let's try all of this, and we can see something that looks like a ball in the center of the window. To make this ball move, we first of all need self.direction, which has to be a pygame.vector2. We need a value for x and y. Both of those should be random. For that, we will need from random import choice and uniform. For the x value, we simply want to get either 1 or -1. Or in other words, we are going left or right. That we can get by putting them into a tuple and then putting the tuple into the choice method as an argument. Now for y, I want to have a random value between two floating point values. That we can get via uniform. It works like random integer, except for this one, we're getting random floating point values. I want to get a value between 0.7 and 0.8. Both of those are positive, which isn't ideal. If we didn't make any updates to it, the ball would always go down, because we always have a positive y value. To fix that, I'm going to multiply this with choice and -1 and 1. That way, we get a direction that can be randomly up or down. I hope this part isn't too complicated. We are basically just creating two random values for x and y. Next up, to actually get some movement, we want to have a move method with self and delta time, and all we want to do is self.rect.center plus equal self.direction multiplied with the speed of the ball, which we get from settings. In there we have speed and ball. And finally, we will need delta time. After that, to make sure we are calling the move method, update self delta time and self.move with delta time. Let's try all of this, and the ball is moving in random directions. Let's try this a couple of times. And that is looking pretty good. Cool. We are nearly done with the basic setup. The one other thing that I want for now is that the ball should be able to bounce around the screen, for which we will need another method. Let's call it wall collision. No need for custom parameters. All we really want to do in here is, for example, if self.rect.top is smaller or equal to 0, then self.rect.top is going to be 0, and self.direction.y we want to multiply with -1. Or in other words, if this is the top of the window and the ball crosses it, then we are going to set the top of the ball to the top of the window and move the ball in the opposite direction, at least on the vertical axis. The same thing we want to do on the bottom side. For that, I can copy all of this and then check self.rect.bottom is greater or equal to the window height. If that is the case, self.rect.bottom is going to be equal to the window height, and self.direction.y is going to be multiplied with -1. That would cover the top and the bottom. Those two parts we're going to keep in the final game. Although for now, for testing purposes, I also want to have a bounce on the left and right side of the window. That is going to make it much easier to test collisions in just a bit. For that, I want to basically duplicate all of this 2 more times, because now we want to check self.rect.right is greater or equal to the window width. If that is the case, self.rect.right will be equal to the window width, and self.direction.x we are multiplying with -1. Finally, I want to copy the first if statement, and then self.rect.left is smaller or equal to 0. If that is the case, self.rect.left is going to be 0, and self.direction.x we are multiplying with -1. With that, we have bouncing. We just have to call self.wall_collision and then run main.py. And we have some bouncing behavior. No collisions yet, but that we are going to work on in the next part. Other than that, this is working pretty good. And I hope at this point, this kind of setup isn't too difficult. You should be able to create basic sprites and make them move via a vector. On top of that, you should also be reasonably comfortable at this point to get player input. We have covered this kind of logic twice already, so I hope it's not too difficult. Now, before we finish up this part, there's one more thing that I would like to do. At the moment, we only have perfect rectangles, which doesn't look great. I want to have, for the ball, a proper circle. And for the player, I want to have rounded corners. Let's start with the ball. And for that, I still want to keep the surface, but I'm going to add another argument, which is called a flag. And for this, I want to get pygame.src_alpha. With that value, we enable alpha values on this image. If I don't fill the entire thing with a color and run main.py, we cannot see the ball anymore, but the ball does exist. It's simply not visible. That is actually super useful, because now we can get pygame.draw.circle. So basically what we are going to do, we're going to make the original surface invisible and then draw a circle on top of it. With that setup, we cannot see the background. The only thing visible in the game will be the ball itself. For this, I want to draw on self.image and then get a color value, which we already have, colors and ball. Finally, we will need a position. And now you have to be careful, because so far, whenever we use pygame.draw, we drew on the display surface. But this we are not doing anymore. We are drawing on self.image, which is a surface that is much smaller. This self.image is a surface like this that is 30 by 30 pixels. And when we are getting the position for the circle, we want to get the center of this thing, which will be relative to the top left, or in other words, we want to go 15 pixels to the right and 15 pixels down. And those values we want to get from settings as well. I want to have a tuple with x and y. For x, I want to get the size, then I want to get the ball size. On there, I want to get index 0, and then divide all of this by 2. For the y value, I want to do basically the same thing, except now it's going to be index 1. And finally, we're going to need a radius, which is going to be one of these values. Let's simply go with size ball 0 divided by 2. If I now run main.py again, we are getting a circle. So that is working pretty well. Now looking at this line, it does get a bit more complex, especially the position and the radius. All that we are really doing in here, we have a surface That is 30 by 30 pixels. Those values we're getting from size and ball. After that, when we are drawing the circle, we want to get the center of this surface. And for that, we are getting the width of the ball and divide it by 2. That way, we are going from the top left and going halfway. After that, for the Y position, we are once again starting from the top left and we're getting half of the height of the surface. Combined, we are defining this center point. Finally then, for the radius, we simply go from the center and then get a radius that touches the outer border of the surface. Once we have all of that, we can draw a circle around that point. That is basically it. We don't need the image fill part anymore, and after that, we can work on the player, for which we first of all have to set a flag with pygame and src alpha. After that, I want to use pygame.draw.rectangle. I want to draw on self.image. The color is going to be colors and paddle. And finally, I need to get a pygame.fRectangle that I want to use for the drawing. And for this one, once again, it's really important to understand that we are not drawing on the display surface. We are drawing on self.image, which at the moment I believe is a surface that is 40 pixels wide and 100 pixels tall. The rectangle that we want to create should start in the top left and then have the same width and the same height compared to the surface. Which means when we are defining the position, we want to have 0 and 0. That way we are in the top left of the surface. And those I want to have inside of a tuple. Or in other words, when I'm defining this rectangle, I want to have a tuple for the position and a tuple for the size. For the position, I want to have 0 and 0. And for the size, I can simply reuse the size of the paddle. The same thing we have used inside of pygame.surface. Once we have that, we have a rectangle. But when we are drawing all of this, we can define more arguments. For the width, I want to have a value of 0. And then for the border radius, I want to go with, let's say, 10. Then we don't need self.image.fill anymore. And if I run main.py, we have rounded corners for the player paddle. So that is working really well. Although I think they are a bit strong, let's go with 4 instead. And I think that is looking a bit better. But once again, play around with these numbers and just see what looks good. Anyway, with that, we have a pretty good start. Next up, we can work on collisions. With the basic setup out of the way, we can work on collisions. And really important for this project, we have collisions between two moving objects. Or in other words, both the paddle and the ball are moving, which is not something we can account for with the collision logic we have used so far. But let's go through it step by step and start with a recap. At the moment, we have covered collisions between a moving and a static object. We first of all separate the dimensions, and then we check for overlaps via the rectangles. For example, we could have the player and an obstacle. After that, we use the direction of the moving object to determine the collision side. Or in other words, if we have the player and the obstacle again, if the player is moving to the right, then we know the collision must have happened on the right side of the player. Or in other words, if you have only a single moving object and this object is moving to the right, then we can only really have a collision on the right side of that moving object. Once we have that, we have to update the position of the moving object. Or in other words, we are setting the right side of the player to the left side of the obstacle. That would be one side. If we cover the 3 others, we have a proper collision system. However, there is a major weakness, and that is once the other object starts to move, then all of this is falling apart. And the key issue is, once both of these objects are moving, we cannot reliably tell on which side the collision happened. For example, if this is the player and the obstacle and the player is moving to the right, we would assume that the collision happened on the right side of the player. However, what happens if the obstacle is moving to the right at a much greater speed? So that, for example, in the last frame, the player was roughly here, and the obstacle was somewhere here. If that is the case, we should have a collision like this, where the right side of the obstacle is colliding with the left side of the player. To account for all of that, we have to make some updates to our collision logic. That being said, we are going to keep some parts. We are still going to separate the dimensions, and we are checking for overlaps via rectangles. This part doesn't change. After that, however, we are going to check the current and the previous position of both objects. Or in other words, if this is the obstacle and the player only on the horizontal axis. For example, this would be the center of the player, this would be the left side of the player, and this would be the right side of the player. And we can tell at the moment we have a collision on this point, or rather an overlap to be a bit more specific. And this happened on the current frame in the game. But on top of that, we also want to store what happened on the last frame. And then let's say the player was here and the obstacle was here, which means we know that the obstacle was further to the left than the player and is simply moving really fast to the right. And this we have to include in our collision calculation. For example, to check for the right collision of the player, we still want to check if the player right is greater than the obstacle left. This is what we have done here. We know that the player right is greater than the obstacle left. This is giving us one overlap. But on top of that, we are checking this second condition, where the right side of the player needs to be below the left side of the obstacle. With that, we know that on the previous frame, the player was on the left side of that obstacle, which in this case is not going to be the case. Overall, we know there was no collision on the right side of the player. However, if we are doing all of this from the other side, the obstacle, then we do get a collision. And let's go through it one more time. We have the first collision, where we are checking if the right side of the obstacle, this point, is greater than the left side of the player. Which in this case very much is the case. The right side of the obstacle is a much greater value than the left side of the player. On top of that, we want to check if the right side of the obstacle on the last frame was below the left side of the player on the last frame as well, which is also the case, meaning this condition triggers as well, which means overall we know that the obstacle should have collided on the left side of the player. And this logic we can apply to all of the other sides as well. Once we have all of that, we have a proper collision mechanic. For all of that, I want to work inside of the ball class and add a right below move, define collision, for which we will need self and the direction we are working in. First of all, in there, we want to check for sprite in self.pedal_sprites, which is something that I should have created inside of the dunder init method. In there, we need self.pedal_sprites, which is the value we are getting from the parameters up here. At the moment, this one simply contains the player sprite, and later on the opponent will also be in there. Once we have that, we want to check if sprite.rect.collide rect with self.rectangle. We are checking if there's an overlap between the player and the ball, something we have also done before. After that, I want to check if the direction is equal to horizontal. And now we want to check for two conditions. If self.rect.right is greater than sprite.rect.left. On top of that, we want to have a second condition where self. Let's call it the old_rectangle.right is smaller or at least equal to sprite.old_rect.left. These two old rectangles don't exist at the moment. We are going to create them in just a second though. If that is the case, we simply want to set self.rect.right to sprite.rect.left. And this is the logic I have just talked about, where we are checking a moving object and then first of all check if we have an overlap at all on the horizontal axis. And then we check if the old rectangle was to the right of the left side of the sprite on the previous frame. The question now is, how can we get this old rectangle? Or in other words, how can we store the rectangle position on the last frame? That part is actually fairly simple. Inside of dunder init, when we are creating the rectangle, I also want to have self.old_rectangle. And for now, I simply want to get self.rect and then copy the rectangle. That way, we are getting a new rectangle with the same position and the same size. After that, inside of the update method, before we are applying any kind of movement, I want to self.oldRect and then get self.rectangle once again and copy it. Via that system, on every single frame, we are storing the position of the rectangle and then updating the position of that rectangle. We have the last frame and the current frame, and that is all we need. Although the same thing we also have to do to the player. In there, for the player below the rectangle, we will also need self.oldRect, which is going to be self.rect.copy. And this we want to do before we are doing anything else inside of the update method. Nearly done. The last thing that we have to do is to call this collision method. And this is going to happen inside of the move method. In there, I first of all want to separate the dimensions for the movement. We want to move self.rect.x and self.rect.y. For each, plus self.direction.x and self.direction.y multiplied with speed and delta time. After the horizontal movement, I want self.collision and horizontal. After the vertical movement, self.collision and vertical. This part doesn't exist at the moment, but that we can work on later. First of all, inside of main.py, if the ball now collides with the player, we are getting a collision. This isn't too amazing yet, because the ball simply keeps the direction. To account for that, we can simply set self.direction.x multiply equal with -1. That way, we're getting a proper bounce. So let's try this one. And there we go. This part is working, and it would also work while the player is moving. Although, truth be told, this part isn't too impressive yet. What is going to be much more interesting is the vertical collision. Let's say I want to check if self.rect.bottom is greater or equal to sprite.rect.top, and self.oldRect.bottom is smaller or equal to sprite.old_rect.top. If that is the case, I want to set self.rect.bottom to sprite.rect.top. Or in other words, we are checking if the bottom of the ball is colliding with the top of the player. And besides that, we are checking if on the previous frame, the bottom of the ball was on top of the player as well. Now, testing this is going to be a bit of a challenge, and I think to test all of this a bit better, let's set the ball speed to something much lower, 50. If we now test all of this and it's going to be really slow, let me speed this one up just a bit. Okay, you can now see we have a collision between the pedal and the ball. And this is also the basic logic for collisions between two moving objects. All you really have to add is the overlap and then the position of the rectangles on the last frame. Now, in our case, I always want the ball to bounce if there's a pedal collision, which means self.direction.y multiply equal -1 if we have a vertical collision. I suppose what we could be doing is set the ball speed back to 450, and let's try this, and there we are getting a proper collision. That looks good. With that, we are nearly done. We just have to add 2 more sides to our collision logic. That part is going to be your exercise. I want you to add the last 2 sides of the collision logic. Pause the video now and see how far you get. At the moment, we are checking the right side of the ball and the left side of the player. The alternative would be if self.rect.left is smaller or equal to sprite.rect.right. And I think it's generally a good idea to use greater than or equal to for all of these comparison operators. Although in practice, it's not going to make much of a difference. Besides that, and self.oldRect.left is greater than or equal to sprite.old_rectangle.right. If that happens to be the case, self.rect.left is going to be sprite.rect.right. And also in our case, self.direction.x multiply equal -1. And besides that, for the vertical collision, we want to check self.rect.top is smaller than or equal to sprite.rect.bottom. And self.oldRectangle.top is greater than or equal to sprite.old_rectangle.bottom. And then self.rect.top is equal to sprite.rect.bottom and self.direction.y multiply equal with -1. That is all we need. I can now try main.py and we have a collision on the top of the player, and we can try this one again. There we could see a pretty good collision, and you can play around with this quite a bit more. But fundamentally, it looks pretty good. And I hope overall the logic here isn't too complicated. The major thing that you have to understand is that we are always checking the current overlap and the previous overlap. That's literally it. Since overall we are checking for a ton of conditions, this can get a bit complex, but I think it's still manageable. Once you have been using this a couple of times, it becomes fairly straightforward. The next really important part that I want to cover is going to be inheritance. Via that system, we are going to create the opponent with only a couple of lines of code. The way it's going to work is that for now, you have to understand that both the player and the opponent pedals are really similar. They are going to have the same setup and move code. So we can share quite a few things between them. The only real difference between them is how the move direction is updated. For the player, we are getting keyboard input, while for the opponent, we are checking the ball position. Because of that, we can create a pedal parent sprite that covers setup and move. And then the player and the opponent both are going to inherit from that. With that system, it's going to be much easier to write reusable code. So let's have a look. Inside of sprites, we have the player class. And for the opponent, we want to have the same dunder init method and the same move method. Also, we want to keep the update method as well. As a consequence, all of this should go into another class called pedal. This one needs to be a pygame.sprite.sprite. And for the dunder init method of this class, we want to use the one we have created for the player. We can simply cut it out and paste it in there. And now we are creating a very basic sprite. Unfortunately now, the player class is not going to work anymore. But what we can do is make the player class inherit from the pedal. That way all of this will become available. All we need to do is call a dunder init method inside of the player. And for that, we will need the groups. But now, if we are calling super dunder init inside of it, we are calling this dunder init method. And only inside of this dunder init method of the pedal class are we creating the actual sprite. Although the pedal itself doesn't really care. All that we need to pass through are the groups, and then we are done. Which means inside of main.py, we are getting the very same result. So that is looking really good. The only change that we want to make is that we want to have a custom speed for the player and for the opponent later on. Which means we want to have self.speed inside of the player. On top of that, what we can also do is move the move method into the pedal class like so. And the same thing we can do to the update method. Since those are going to be useful for the opponent as well, we do want to have them inside of the parent class. Which means all that's really left inside of the player is getDirection and a very basic dunder init method. However, inside of main.py, we still have the same functionality. So now, finally, we can create the opponent, which is going to be a child of the pedal class. All that we need inside of this one is a dunder init method, and we will need a get direction method. And creating those is going to be your exercise. I want you guys to create the proper opponent pedal. The parent class should be pedal. This is what we already have. And then to get the direction, you basically want to do something like if the vertical center of the opponent is smaller than the vertical center of the ball, then the opponent should move down. That's all you need for the direction. This can be done in a single line of code. So pause the video now and see how far you get. First of all, we will need dunder init with self, the groups, and we are also going to need access to the ball. After that, super dunder init with the groups, and that way we are calling all of this, which means we already have a sprite. And for now, I am going to comment out get direction, because what we can already do inside of main.py, I can create an opponent class. For the groups, we need self.allSprites and self.pedalSprites. For the ball, I want self.ball. If I now run all of this, we are getting an attribute error that opponent object has no attribute get direction. That happened because inside of sprites, we have a very basic setup, meaning we get all of this. But then, because of the inheritance, we are also getting this update method, which is trying to get the old rectangle, but then it wants to get the direction, which we can do for the player, but we cannot do it for the opponent, because we do not have get direction inside of it. If we uncomment all of this, and then for now add self and pass in there, then this problem should be solved. We can now get a direction. Afterwards, we are trying to call self.move, which does exist inside of the parent class, meaning it should be working. However, if we are trying main.py, we're getting another attribute error, that there's no speed inside of the opponent, which should be obvious because inside of this dunder init, there's no speed. For the player, we are creating a speed separately, which is also what we want to do for the opponent. Inside of the dunder init method, I want to have speed and opponent, the key value pair that we are getting in here. If I now run main.py, if I move the player, you can see that we have an opponent. Although the issue is that the opponent is on the wrong side. So this is no good. This happens because when we are creating the parent, we are setting self.rectangle to this position. How can we fix that? And well, when we are creating the opponent, we can simply overwrite self.rectangle. Or to be a bit more elegant, we can update self.rect.center to pos and the opponent, the value that we are getting from this dictionary. And now, inside of main.py, we have the opponent in the right position. That is working really well. All we need at this point is the get direction method. First of all, for that, we need to know where the ball is inside of the game. And we are already passing the ball as an argument into this class, which we want to store as an attribute. Self.ball is ball. And then, basically, we want to get self.direction, which, as a reminder, is simply an integer. It can be 1 or -1. In my case, I want this to be 1 if self.ball.rect.centerY is greater than self.rect.centerY. If that's not the case, else it should be -1. Imagine that this is the opponent and we have the ball somewhere here. In this case, we have the center of the opponent here. Let's say this is 100, while the center of the ball is something like 150. With those numbers, this if statement is going to trigger. As a consequence, the direction of the opponent will be 1. Or in other words, we are moving down. And that's the basic logic. If I now run main.py, we are already calling get direction. So this method is running already, and it's looking pretty good. Now the opponent is following the ball. And this is working forever, and at some point the opponent does miss the ball, which is perfect. So with that, we have the opponent, and we didn't have to write very much code to set all of this up. And the same for the player. The actual logic inside of this one is very, very simple. The actual work happens inside of the pedal, and this is going to be reusable, which also means that you can make updates in here very easily. And for a more complex project, this is basically always something that you want to do. It makes your code much more easily manageable. To finish up this game, I want to add a score and a saving mechanic. That way the game becomes much more interesting, and we also cover a really important game mechanic. After this, we are also going to add some more minor bits, but those aren't too important. First of all, saving in a game simply means that we want to store some data permanently. In our case, when we are closing the game, we are going to create some kind of text file with the score. And when the game is starting again, we are loading that text file. That's all that's really happening in here. The only thing that we really have to worry about is the file format. And I want to use something that is called JSON, or JavaScript Object Notation. This is a really common format to pass data around online, and Python can use it really, really well. Although, truth be told, you could also just create a text file or an Excel file, or if you really wanted, you could store the data in a JPEG file. It is entirely up to you, but JSON usually is the default. And just for an example, this is what a JSON file looks like. It is fairly similar to a Python dictionary. Although you do have to be careful here. JSON is not Python. It's an entirely separate file format. It just happens to look very similar. Now, to implement all of this, first of all, I want to have a score section in my dunder init method of the game, where we are creating a score dictionary, for which we have a player key with 0, and we have an opponent key as well. So this dictionary is going to keep track of the score, and that we want to display, i.e. define display underscore score. No need for custom parameters, and in there, we want to display the player score and the opponent score. For both, we are going to need some text, or in other words, we want to create a player surface, and for that, we want to do something like self.font.render. A font we don't have at the moment. Right below the score, self.font is going to be pygame.font.font. For the font style, I will go with the default one, none. For the font size, I want to have something fairly large, 160. With that, we have a font. That means we can get self.score and the player. That being said, inside of the render method, we always need a string. So we have to convert this right away using the string method. Afterwards, we have anti-alias, which should be true, and then we will need a color, which we are getting from colors, and in there is BG detail. I think I called it. The final entry, BG detail. That is going to give us a player surface. Next up, we need a player rectangle. Or in other words, where we want to display this surface. I want to get the player surface and then get F rectangle. I want to place the center, and for X, I want to have window width divided by 2 plus 100. For Y, I simply want to get window height divided by 2. Finally, self.display surface.blit with the player surface and the player rectangle. To make sure we are testing all of this inside of the run method, before we are drawing all of the sprites, but after we are drawing the background, I want self.display score. Let's try, and there we can see the player score. It doesn't do anything at the moment, but at least we have something. After that, I can copy all of this and then rename player to opponent. For all of those, I want to have the opponent. Also, for the score, we want to have the opponent. And then for the position, we don't want to go 100 pixels to the right. We want to go 100 pixels to the left. Let's try all of that. And there we have 2 scores. That looks good. Finally, I want to add a line separator. which simply is going to be pygame.draw.line on self.display surface with the BG detail color. Then we will need a start position and an end position along with a line width. For the start position, I want to get for x window width divided by 2 and 0. We are in the mid top of the window. Then for the end position, window width divided by 2 and window height. And for the line width, I went with 10. If I now run all of this again, we have a line separating the two sides of the field. That looks good. I suppose you could argue that the line width is just a bit large, maybe 6 is a bit better. Just choose whatever you like the most in here. There really isn't a universal answer. Anyway, with that, we are displaying the score. Which means whenever we are updating the score, we are actually showing the result. Now, to get those values, I want to create an update score method with self and decide that we want to update. Inside of this method, self.score, and then by default pick the player, but only if side is equal to player. If that is not the case, else I want to get the opponent. That way I'm getting one of the values, and I want to increase this value by 1. And that's all we need to update the score for one of the sides. And this method is going to be called from inside of the ball class, which means in there we want to have self.updateScore. After that, when we are working with the ball, we will need one more parameter. Update_score, and this we want to turn into an attribute right away. Self.update_score is going to be update score. That's a good start. Next up, when we have a wall collision for the left and the right side, instead of making the ball bounce, we want to update the score, which means we don't need those two if statements anymore. And we can replace them with if self.rect.right is greater or equal than the window width, or self.rect.left is smaller or equal to 0. If that is the case, we want to self.updateScore. For the argument, we will either need player or the opponent. By default, I want the player, but only if self.rect.x is smaller than the window width divided by 2. Or in other words, if the ball is on the left side of the field, then I want to insert player. If that is not the case, else we're going to insert opponent. Let's test all of this, and let me miss the ball, and the score should update. And it does, although the issue is we are not resetting the ball, so this method keeps on triggering. To fix that, I want to run self.reset, which is a method that does not exist at the moment. To fix that, define reset with self and no other parameter. All that we need in here is, first of all, self.rect.center. We want to place the ball right in the middle of the window, which means window width divided by 2 and window height divided by 2. On top of that, I want to randomize the direction again, the same thing that we have done up here. In fact, we could simply copy the line and paste it in there. If I now try all of this again, the ball is resetting in the middle of the window, and that's already feeling quite a bit better. That's a really good start. Now we can start working on saving the score. At the moment, the score is not permanent. Whenever we restart the game, this is the score that we are starting with. To fix that, we need to do two things. Number one, when we are quitting the game, we want to create a JSON file that stores the score data. And then when we are starting the game again, we want to load that file and override self.score. For all of that, first of all, we will need another Python module, which is called JSON. And this one comes with Python, so you should already have it. After that, when we are exiting the game, I want to create a file, which we are doing with open, and then we have to specify a file path, which we are once again doing via the join method. I want to go to the data folder, and then create a score.txt file. And in case you're wondering, in our file path, we have the code folder and then we have data, which at this point is entirely empty. This would be the first argument inside of open. The second one has to be a W, short for writing. Or in other words, we are indicating that we want to write this file. And then inside of Python, we have to store all of this data as a variable. I'm going to call it score_file. Inside of this with statement, we want to call JSON and then dump. In there, we want to pass in self.score, so the data we want to save, and then the score file, the file that we actually want to write in. And with that, we are done. If I now run the game, and let me get a different score than 0 and 0, if I now exit the game, we didn't get an error, but if I'm looking at our folders, inside of data, we have score.txt. And in there, we have the player score and the opponent score. That was literally it. With that, we can create external files. Next up then, when we are starting the game, we want to load that file, which we're doing in a similar way. Once again, I want to use with, open, and then the join method, in which I go to data, and then score.txt. Important now, we do not want to add a second argument like we have done down here, because we only want to read this file. We do not want to write any kind of data in there at this point. And this we want to store as the score file. We want to get JSON, load, and the score file. This is going to load all of the JSON data and return a dictionary. In our case, this is going to be self.score. And well, that is basically it. I can now comment out the original self.score. If I now run the game, we have the score from the last game. So this is working really well. And if I am getting another score, let me try to defeat the opponent at least once. And that is working. And if I am getting another few points in there, if I now open score.txt, we have once again updated the score. This is working really well. That means we are nearly done. There's just one more thing that we want to be conscious of. If the game starts for the first time and score.txt does not exist, so let me simply delete this file. If we are now trying to run the code, the issue is that we do not have score.txt. That is something we can fix fairly easily. We want to indent this if statement one more time and then add try, which is telling Python to try this line of code. And if we are getting an error, then we want to do an except statement. Or in other words, if we have this JSON file, we want to create a score from that data. But if we don't, so except, then we want to create a new self.score dictionary. I can run the game, and by default, we have no score, but once we are getting something, I can close the game, and we are getting score.txt. And that is all you need for a very basic saving mechanic. It wasn't actually so bad. That also nearly finishes the game. There are just two more things that I want to do. Both of those are going to be your exercise. Number one, I want to have a delay when the ball resets. That way the player has a bit of time to adjust. And besides that, I want to add shadows to the pedals and the ball. A fairly minor detail, but it's going to make the game look much better. By the end of it, you should have something like this. So pause the video now and see how far you get. Righty, let's get started with the ball reset, for which I want to create a timer inside of the dunder init method of the ball. We will need self.start_time, which is going to be pygame.time.get_ticks. On top of that, I want to have self.duration. I put this one at 1200. Once we have that, I want to create below reset a timer method, which is going to check if pygame.time.get ticks, so the current time, minus self.startTime is greater or equal than self.duration. If that is the case, we want the ball to start moving, which in my case, I'm going to do via self.speed modifier. If this timer times out, this value is going to be 1. If it doesn't, self.speed modifier is going to be 0. And then inside of the move method, we are multiplying the actual movement with self.speed modifier. So if this value is 0, we do not get any movement. For all of that, we have to, under movement, add self.speed modifier and set it to 0. Also, we have to call the timer. Before we are doing any movement, self.timer. With that, if I run main.py, after about 1 second, we're getting some movement. So that is looking pretty good. After that, inside of the reset method, I want to update self.startTime with pygame.time.getTicks. That way, inside of the game, once we are getting an update to the score, we have to wait a second and then the ball starts moving again. So that is working pretty well. Let's try it one more time. And that is working. Perfect. That covers the first part. Next up, I want to work on the shadows. For that, first of all, I want to give all of the entities another surface. Let's do it right below the image. I want to have a shadow surface, for which we will need self.shadow_surface, which is going to be a surface with the same size as the image. Or in other words, self.image.copy. On this new surface, we also want to draw a circle. In fact, I can duplicate this entire line. Although, we want to draw on self.shadow_surface. For the colors, I want to get the ball shadow. Although the position and the radius should stay identical. So with that, we have a shadow surface. How can we display it? For that, I want to create a custom sprite group, which means inside of the code folder, I want to add groups.py. First of all in there, from settings, import everything. And then class all sprites with pygame.sprite.group. After that, we will need a dunder init method with self and nothing else. And we need super.dunder init. Also, I want to get self.display_surface via pygame.display.getSurface. After that, I want to create a custom draw method. For this one, first of all, we have to get the default behavior, which we get via forSprite in self, and then self.displaySurface.blit with sprite.image and sprite.rectangle. After that, inside of main.py, I want from groups import all sprites. This all sprites is then going to be our all sprites group. And when we are running the game and drawing all of this, we do not need an argument anymore. Other than that, though, everything else is still working just fine. So that's a really good start. What we now need for the shadows, before we are drawing the actual sprites, we want to have another for loop, which is also going to be for sprite in self. Except that now we are calling self.displaySurface.blit with sprite.shadow_surface. And for the position, we want to have sprite.rect.topleft plus some offset. Let's say pygame.vector2 with 5 and 5. Now this at the moment is not going to work because the pedals do not have a shadow surface. That we can fix quite easily because both pedals have the same parent class. In there, below the image, we can add a shadow surface, which for now is going to be shadow surface with self.image.copy. After that, if I'm trying to run all of this, we are getting an attribute error that all sprites has no shadow surface. That is because this should be sprite.shadowSurface instead of self. Let's try this again. And now we can see some sort of shadow. So it's working reasonably well. To refine all of this, inside of the pedal, I want to draw another rectangle like we have done in the original, except now this should have a pedal shadow color, the one that we are getting from the settings. Also, we want to draw on the shadow surface. Let's try all of that, and definitely getting better. The one thing I don't like about this one at the moment is, let me draw this actually. If this is the pedal, our shadow at the moment would look something like this, where you can very much see that we have two separate surfaces, one here and one here. And I want to have them connect a bit better. In other words, I want to have a proper line like this, which would look much more like a shadow. To get something like this, I want to add another for loop, for I in range, let's say 5. And then, when we are drawing the shadow, the vector offset is going to be set by the I argument that we are getting from the for loop. That way, we are drawing multiple shadows at an offset, which is going to make all of this look much better. The rest of the game, though, still works just fine. Perfect. So with that, we have a proper shadow. Although this isn't a perfect setup, because we are drawing 5 extra surfaces on every single frame. What would be much better is to create all of these surfaces in the dunder init method and then blit them at once. But for our purposes, I don't think performance is ever going to be an issue. So I would say at this point, we are basically done. That covers another game. For game number 4, we are going to create a basic platformer game. In there, you can jump around and shoot at things. It's fairly straightforward. And most of the logic we already know. There are just 3 things that are going to be somewhat new. The most important one is going to be the platformer logic. Besides that, I want to have more organized imports, and I want to create better timers. 2 things that are incredibly helpful for any even slightly more advanced project. Although before we get to any of this, we have to start with the platformer setup. By the end of this part, we will have something like this. This part is also going to be an exercise. I want you guys to set up the level, and for that, load the level data from the tiled map, then create a player sprite that can move and collide, and for this one, the easier collisions are fine. Although you could also use the more advanced ones, but they're not really necessary for this project. And finally, add a camera that follows the player. And if you open the project folder, you can see that we already have a couple of things. Inside of main.py, we have a game class, and this one initializes the basic stuff, and then creates 2 groups. Then we have a run method, where we are doing the usual stuff. All of that is giving us a basic window with a background color. Inside of settings.py, we have a few more basic things, but none of them are too complicated. Also, if you look at the project folder, besides the code folder, with graphics, maps, and tile sets, we have a whole bunch of images. Those you don't have to worry about at this point. And we have a bunch of audio files. Those also don't matter too much at this point. What you want to primarily work in is code and data. And via those, try to finish the exercise. See how far you get. Inside of the game class, I want to create a setup method. And for now, I want to load the tmx map. Or in other words, I want to create a local variable. Let's call it tmx map. This I get via load pygame, where I want to go to data and maps. If I show this in the file explorer, we want to go to data, maps, and there we have world.tmx. This is the file we want to load, world.tmx. If you open that file, by the way, you are going to get something like this, where we have 3 layers: main, decorations, and entities. On the main layer, we have the actual level. On decorations, we have a whole bunch of, well, decorations. And finally, for entities, we have the player start position, this one up here, and then we have a couple of areas. All of those are for the warm enemies. Not too important for now, so don't worry about it. All that we care about at this point is decoration and main to set up the level. Which means, to get started, I want for X, Y, and the image in TMX map and get layer by name. The layer that we want to load is called main. Since this one is a tile layer, I want to add tiles at the end. That way I am getting X, Y, and image decoded right away. I want to create a very simple sprite class in which we can add an X and a Y position, then the image, and then the groups. The groups we actually already have, all sprites and collision sprites. Those we want to add in there right away. As a tuple, self.allsprites and self.collision_sprites. Also, remember, X and Y inside of tiled is a grid coordinate, but we want to have all of this as a pixel position. For that, from settings, we want to get the tile size and multiply it with both of those values. With that, we can create a basic sprite, for which I want to create a new Python file, sprites.py. In there, we want from settings and import everything. And then create a class called sprite with pygame.sprite.sprite. Then we will need a dunder init method with self, a position, a surface, and the groups. Afterwards, we can call super dunder init and pass the groups right through. Self.image is going to be the surface, and self.rect will be self.image.get_f rectangle, in which we are going to place the top left wherever the position is. That covers the basic sprite class. Back inside of main.py, I want from sprites import everything. That way, this sprite should be working. All that we have to do is let me add another section, load game, in which we want to call self.setup. And with that, we get one part of the level. That looks really good. While we are here, we can also duplicate those two lines, because besides main, we also have decoration, which should only be in self.allsprites. There should be no collisions with those tiles. But other than that, this is all we have to do for this part. After that, I want for obj in tmx map and get layer by name entities. That is an object layer on which we have the player starting position, which we can identify via the name player. Or in other words, I want to check if obj.name is equal to player, and if that is the case, I want to create a player class. For now, in there, I want to have the position, obj.x and obj.y. Then I will need self.allsprites for the groups and self.collision_sprites for the collisions. Later on, we are going to add a bit more, but that's not an issue for now. I first of all want to create another class called layer. And important for this one, I want to inherit from sprite, the class that we have just created. We will always need a dunder init method, and we need what we have specified here, a position, groups, and collision sprites. Self, position, groups, and collision_sprites. Then we will need super dunder init. And important now, we are calling this dunder init method, for which we will need a position, a surface, and the groups. Now we do have a position and the groups via the parameters. That part is fine, but we don't have a surface at the moment, which is totally fine. We can simply create a surface via pygame.surface. For now, the dimensions are going to be, let's say, 40 and 20. Also, while we are here, I want to create an attribute self.collision_sprites is going to be collision sprites. With that, if I'm running main.py, we can see a very basic player thingy. Although I think it should be quite a bit taller. Instead of 20, let's go with 80. That feels much more realistic. That would be the basic player. I want to call an update method with self and delta time, for which we are going to need self.move, and this move method is going to consist of two parts. The move method itself with self and delta time, and then we will need define collision with self and a direction. To get started with moving, we want to get self.rect.x plus equal self.direction, which doesn't exist at the moment. And for that, we can actually create a movement and collision section, which is going to contain direction pygame.vector2. That is a part we have seen a couple of times by now, and also in this bit, I want to have self.speed. For this one, I went with 400. With that, we have self.direction multiplied with self.speed multiplied with delta time. This I can duplicate because the next line should be self.rect.y. And I realized for x, we want self.direction.x, and for y, self.direction.y. That way, we have the horizontal and the vertical movement. Afterwards, we have to call self.collision with horizontal and vertical. That would cover the basic movement. To test all of this, I want to have an input method in which we are getting the keys and then pygame.key.get_rest. At least for now. I want to update self.direction.x and set it to the integer of keys and pygame.k_right minus, let me copy all of this and change k right to k left. Then we can duplicate all of this and then k down minus k up. Also, we want to get self.direction and set it to self.direction.normalize if self.direction. If that is not the case, we simply want to get self.direction. Also, before we are moving, I want to call self.input. With that, if I run main.py, the player can move around just fine. That is looking pretty good. For the collisions, I want to check for sprite in self.collision sprites. If sprite.rect.collide rect with self.rectangle. And by the way, for this project, you could be using hitboxes, but you don't really need to. If you want to add it, do it in your own time. Afterwards, if direction is equal to horizontal, then we want to check if self.direction.x is greater than 0, then we know self.rect.right should be equal to sprite.rect.left. Then we can duplicate all of this and check if the direction is smaller than 0. In which case, self.rect.left should be sprite.rect.right. Next up, I want to duplicate all of this and then check the vertical collisions, in which we want to check self.direction.y if this one is greater or smaller than 0. If it is greater than 0, we are moving down and want to check the bottom of the player. If this one collides with a sprite, we want to set the bottom to the top of the sprite. And vice versa, if the player is moving up and we have a collision, then self.rect.top should be sprite.rect.bottom. If I now run around, we're getting collisions with the level. Finally then, we are going to need a camera. For that, inside of the code folder, I want to add groups.py. As always, we will need from settings and import everything. Then class all sprites, which is going to be a child of pygame.sprite.group. A dunder init method is always needed, although this one without custom parameters, and we want to call super dunder init. Also, self.display_surface is going to be pygame.display and get surface. That's the easy part. Besides that, we want to have a custom draw method, with self and a target underscore position. Via this target position, we want to influence self.offset on X and Y. And at this point, I realized I have forgotten to create self.offset. This one is simply a pygame vector 2. Self.offset.x is going to be the negative value of target position 0 or the horizontal position of the player, and from that, we are subtracting window width divided by 2. A very similar thing we want to do for self.offset.y, except for this one, we want to get the vertical position and subtract window height divided by 2. That way, we are getting the offset for the camera that we can use with for sprite in self and self.displaySurface.blit with sprite.image and sprite.rect.topleft plus self.offset. With that, back inside of main.py, when we are calling allsprites.draw, we do not want to have the argument anymore, and also when we are creating all sprites, this should be all sprites. And for that to work, we have to add from groups import all sprites. Nearly done. The last thing that we have to do is when we are calling the draw method, we have to get the player position, for which we want to store the player in an attribute. Self.player is going to be the player sprite, and then self.player.rect.center. Let's try, and we have a camera. That is looking pretty good. With that, we have a basic setup via a few classes. So I hope at this point, this exercise wasn't impossible. And if you could follow along, you already know pygame pretty well. With the basics out of the way, we can work on the platformer logic, which is going to give us an actual platformer game. And quite honestly, we don't really have to make that many changes. For the platformer movement, the player is still going to control left and right movement. However, for up and down, the player doesn't have control anymore. Instead, we are using gravity and jumping. Or in other words, we have to increase direction.y by increasingly large numbers. That way it looks like the player is affected by gravity. And when the player jumps, we are setting direction.y to some static negative value. And we'll talk about this in just a second in a lot more detail. That being said though, including delta time with the full speed does include a bit more math, which I want to avoid. So we are going to set the frame rate to 60 frames per second. Although, if you want to have the full platformer experience, check out this video. In there, I create a proper Super Nintendo style platformer, including an overworld. If you have gotten so far, you can follow along with this tutorial just fine. Back in the code. First of all, I want to update the frame rate. And this I have actually already done, because when we are calling the tick method, we are passing in the frame rate. That we are getting from settings.py. There, we have a frame rate of 60. We already limited our frame rate, which for a platformer can be a good idea. It makes your math just a bit easier. After we have that, inside of the move method, I want to add a comment with the horizontal movement. This is the part we're not going to touch, but we do have to make some changes to the vertical bit. For now, what I want to do, if this is the player, we should have a downward movement that is getting larger and larger the longer we fall, just like real-world gravity. For that, in the dunder init method of the player, I want to add another attribute, self.gravity, which I have set to 50. Before we are updating self.rect.y, I want to update self.direction.y and increase this value by self.gravity multiplied with delta time. Afterwards, on the next line, self.rect.y is going to be increased by self.direction, although for this we don't need speed and delta time anymore. And what is happening now? On the first line, when we are increasing self.direction.y, we are making this value larger and larger on every single frame, because we keep on adding to the existing value. On top of that, this self.direction we are adding to the vertical position of the player. That way, we are falling at an increasingly large speed. Although, if I run main.py, we are falling and we have collisions, but if I keep on falling, we are falling at a constant rate. What is the issue here? And well, if you look at the player in the input method, we are normalizing the direction vector. Because of that, all of these values are normalized. Or in other words, the entire length of the vector never exceeds 1. Fortunately, that is very easily fixable. We simply have to remove those two lines, and then if I run main.py, we are getting proper gravity, although it's still not ideal. Let me run all of this again. So we have some basic gravity, but if I fall again, we are falling really fast. The issue for all of this is, imagine that we have the player standing on a platform. And also, because of those two lines, we keep on increasing the gravity. On the first frame, the player moved down by this amount and then be constrained by the platform, which is totally fine. A few frames later, we go a bit further down because of the gravity, and we are still constrained by the platform. However, after some more time, the gravity puts the player so far down that we are skipping the platform entirely. As a consequence, the player teleports right through, and all of the collisions stop working. We are simply moving too fast for them. To fix that, we want to work inside of the collisions. Specifically, when the rectangle bottom of the player collides with the top of an obstacle. If that is the case, then we also want to set self.direction.y to 0. With that, if we are on the floor, the gravity doesn't keep on increasing, which means we get proper gravity, and if I fall down again, we get a much nicer gravity behavior. Now, other than that, we can't really do very much, but at least this part is working. Next up then, I want to implement a jump mechanic, for which, inside of input, I want to check if keys and pygame.k underscore space. I want to set self.direction.y to -20. With that, inside of the game, I can now jump around, and this is giving us a very basic platformer. That's looking really good. But it's not ideal yet, because the player can jump the entire time, even if we are not on the floor. So essentially, we are flying. Which could be a nice effect, but not what I want for this game. We only want to allow a jump if the player is on the floor. For that, I want to add another attribute, self.on_floor, which by default, let's set this one to false, and only allow a jump if we are pressing space and self.onFloor. So how can we tell if the player is on the floor? That part is going to be your exercise. I want you guys to find a way to detect if the player is on the floor or not. Try to figure this one out on your own. I want to work inside of the collision method. And effectively, if we have a vertical collision where the player is moving down, then we are already setting direction.y to 0. That means we must be on the floor. Or in other words, self.onFloor is going to be true. Although you also need to be careful here, because at the moment we are only ever enabling onFloor. We are never disabling it. Or in other words, if I now run main.py, the player can still jump around in the air. To fix that, at some point we have to set self.onFloor to false. And this I want to do inside of the vertical movement. Before we are doing anything else in there, self.onFloor should be false. So that basically on every single frame of the game, we are first setting onFloor to false, then we are doing all of this, and inside of the collisions, if the player collides with the floor, then we are setting onFloor to true. Once we have that, inside of main.py, I can only jump if the player is on the floor. So I keep on pressing space, but we only ever get a single jump. That being said, I am not the biggest fan of this approach. Ideally, before we are getting the input, I would want to self.check underscore floor and put all of this into a separate method, which we can also do fairly easily. For that, I want to have a check underscore floor method without any custom parameters. Also, self.onFloor inside of collisions and inside of move should disappear. Instead, what I want to do, inside of check floor, I want to create a bottom rectangle, which we're going to do via pygame.f rectangle, in which we first of all need a position. This can be 0 and 0. We will change that in a second anyway. And the width of this rectangle is going to be self.rect.width and a height of 2. Imagine this is the player, and we want to check if this player is on the floor. What I want to do for that is create another rectangle right below the player and check if this rectangle collides with any of the floor tiles. And that rectangle is going to be the bottom rectangle. Although at the moment the position of this rectangle is off, I want this always to be at the bottom of the player. And for that, we can add another method, move_to, because in there you can specify a specific point that we can place. In my case, this is going to be the mid top. The position of this point should be self.rect.mid_bottom. So one of the limitations of pygame.rect or pygame.frect is that we are always placing the top left. So whatever point you're specifying in here is always going to be the top left, which very often isn't what you want. And using move_to is a really handy way to get around that. So next up, we want to check if this rectangle is colliding with any of the collision sprites. For that, you could write a for loop, but I prefer another approach. The way I approach this, I am first of all going to create a level rects list. I want to use list comprehension and then get sprite.rect for sprite in self.collision sprites. That way I am getting a list of rectangles that define the level. And then I want to get the bottom rectangle and check collide list with the level rects that we have just created. And just to demonstrate what is happening here, let me print the return value and then run main.py. We are now getting 34, 35, 51, 59, 60, and seemingly a random integer. What does it mean? And also really important, if we don't have a bottom collision, then we are getting -1. Essentially, collide list is going to look at the collisions between the bottom rectangle and the level rectangles, and is going to return an integer of the index of the rectangle that we are colliding with. And if there's no collision, we're getting -1. Or in other words, if we have a -1, then we know there's no collision. Which means we can do something like self.onFloor is going to be true if we have a bottom rect with collide list, and this value needs to be greater or at least equal to 0. If that is not the case, else this value should be false. Once we have that, the player can only jump if we are on the floor. Also, we can refine all of this by simply passing the list comprehension straight into collide list. That way, we are saving one line, and the code feels a bit more elegant. And if you want to have a more advanced platformer, being able to detect collisions with the floor or the walls is really important. So with this logic, you could also very easily detect a collision with the left or the right side of the player. But anyway, there's just one more thing that I want to do. Back inside of the game, there's one issue right now. If I jump and we have a top collision, the player hovers in the air for just a bit, which is a very strange effect. If I find another area, you can see it even better here. If once again, this is the player and the player is moving up because we are jumping. And then we have some kind of top collision. We are stopping the player at the bottom side of this collision, but the player direction is still pointing up, and it takes a while for gravity to pull it down again. That way, it looks like the player is hovering in the air. And this we can fix quite easily by setting self.direction.y to 0 if we have a top or bottom collision. That way, inside of main.py, I can collide with the top and the player falls down immediately. And this is feeling a lot better. And once again, all of this can be organized just a bit better. I want to remove the indent and cut out self.direction. Then for self.direction being smaller than 0, this should also not be indented anymore. And all we really want to do is set self.direction if we have the vertical direction. That way, back inside of main.py, we should be getting the same result. Let's try it here. That is looking really good. So this seems to be working pretty well. Perfect. And also our code is feeling a lot more organized. Quite honestly, there really wasn't that much of a change compared to a top-down game. Although for the animations, we do have to include a few more bits. That's going to be the next section. For the next part, we are going to cover imports and animations. By the end of it, we have a basic player animation, and we also have the very basic enemies. At this point, the enemies don't do very much, but that we can work on later. And there isn't going to be that much new stuff for this section. We are going to use basically the same animation logic that we have already seen. The only change is that we have to update the state management for the player to account for the platformer logic. That being said, when we are doing the imports, I want to centralize them quite a bit more. Or in other words, I want to have one method that loads all of the files, and then we don't have to worry about it anymore. Inside of the game class, I want to create a method called load_assets. No need for custom parameters, and in there, I want to load all of the graphics and all of the sounds. For example, in there, I want to have self.playerFrames, which should be a list with the animation frames of the player. Or in other words, to visualize all of this, inside of images, we have a very basic player animation. It really doesn't do very much. All of this we want to import. For that, I want to create a separate function, import_folder, in which we can specify the file path. I want to go to images, and in there we have the player. This I want to import, which doesn't exist at the moment, for which we want to create another Python file. Let's call it support.py. In there, as always, we will need from settings and import everything. And then I want to start by creating an import_image function. This is not going to import an entire folder, so we couldn't use it for the player import. But what we could be using it for, let me comment out the player stuff, and instead I want to import self.bullet_surface. Or in other words, what we want to start importing is inside of images, we have gun, and there's bullet and fire. I want to import the bullet for now via a more convenient method. Or in other words, I want to run import_image with a file path. We want to go to images, then we want to go to gun, and finally, we want to go to bullet. Notice here, I am not specifying the file type. We do not add .png at the end, and that is intentional. Also, what we are going to need is from support import everything. That way, we have this import image. And first of all, what I want in there is to unpack all of the arguments, which are going to be the path. So all of this stuff we want to have straight away. And just so you can see what we are getting, via this unpacking parameter, I want to print the path and then call load assets, which we have to do before we are calling the setup method, self.load_assets. And now if I run all of this, we are getting a tuple with the 3 arguments we have specified. And because of this unpacking parameter, we can specify as many arguments as we want. We are always going to get a tuple with all of them, which we can actually use to create a full path right away using the join method. We simply have to add the path in here, although for that, we want to unpack the path one more time. That way, we are splitting up this tuple into 3 values, and then we can use it inside of the join method. The end result is going to be, if I print the full path, we are getting the full path to this file, images, gun, and bullet. That is looking really good, although we are also going to need the file format. This I want to be able to specify inside of the parameters. In there, I want to have a format, and since we are almost always working with a PNG file, this should be the default. Or in other words, if we don't specify anything, we should be getting a PNG file. And to add that to the full path, I simply want to add an f string with dot and then the format. That way I can run main.py again, and we are getting images, gun, and bullet.png. That is working really well. That we can now use to import a surface via pygame.image.load with the full path. And now we have to decide, do we want to convert all of this or convert alpha all of this? Which depends on the image having alpha values or not, which we cannot really detect, meaning this has to be another parameter. I want to know if there are alpha values inside of this image, and by default, I am going to assume that there are some, because that's usually what you see. And then run convert alpha if alpha is true, and if that is not the case, we want to run all of this once again, except now only convert without alpha. And that is basically it. At the end of all of this, we want to return the surface, and then we are getting the surface inside of this parameter. I can print self.bulletSurface, run all of this, and we are getting a surface. We are still doing a basic import via pygame.image.load, but we are now adding a few more extra things to make all of this quite a bit more convenient. Not a major change, but if you have to import hundreds of images, this can be a massive difference. And by the way, all of this can be made quite a bit more elegant right away. We don't actually need a surf variable. We can return the surface from pygame.image.load right away. The result would be identical. So with that, we can import a single image much more elegantly. Besides that, I also want to be able to import a folder, for which, once again, we want to specify a path and unpack it right away. Via that, we are going to import all of the player frames. We are already calling import folder and getting images and player. Notice here, this is a path to a folder, not to an image. So what we want to do is import all of the images inside of this folder. I first of all want to create a local variable called frames, and this has an empty list by default. Afterwards, we want to do for folder underscore path, and then subfolders, and finally file underscore names in walk, join, and then unpack the path. This is the logic we have already seen a couple of times. We are basically using the walk method to walk through a folder and get the folder path, the subfolders, and the file names. In there, I want to have for file underscore name in file names, and then create a full underscore path, which we are doing via the join method, where we are getting the full folder path and then the file name. Via this, we can create a surface with pygame.image.load the full path. And for this, we basically always want to convert alpha. Now you could make this a bit more flexible, like we have done in import image, and add a custom parameter. Although I don't think this is really necessary. After that, I want to get the frames and then append the surface. By the end of it, I want to return the frames. With that, back inside of main.py, I can print self.playerFrames, run all of this, and we are getting a list of surfaces. That is all we need for the player animation frames, or rather the import of the player animation frames. Now this I want to change in two ways. The first one is easy. Once again, we don't really need this local surface variable. We can simply append pygame.image.load to frames straight away. Also, since we're not using subfolders, there should be an underscore. Besides that, the slightly more important change is that I want to sorted the file names, just to make sure that they are being imported in order. For that, we will need a key with a lambda function where we have a name parameter. And once again, as a reminder, what we are getting with the file name is something like 0.png. And we want to isolate the 0 and turn it into an integer. That way, we can sort all of these values. Which means I want to create an integer, get the name, and split it wherever we have a dot. And then pick the first value. The end result is going to be the same, but in some cases it might prevent a bug. But anyway, with that, we have the basic graphic imports. What we can now do, besides the bullet surface, we also want to have a fire underscore surface that we are getting via import image, and we want to get images, gun, and fire. Next up, I want to have self.b underscore frames, which we're getting from import folder. I want to go to images. There we have the enemies, and in there we have the B. Or in other words, if you look at the images folder, there we have enemies and the B frames. There are only 2 images in there. Besides that, we have the worm, and this one looks really similar. Or in other words, I can duplicate this line and then get the worm frames with images, enemies, and worm. And that is covering all of the imports for the graphics. Now we have to figure out how to use them. For that, I want to work inside of the sprites. For a basic animation, I want to have a class animated sprite, which is going to inherit from the sprite class that we have created. So let me open it. This is going to be the parent class, which means when we are calling dunder init, I want to specify besides self, the frames, a position, and the groups. After that, when we are calling super dunder init, we are calling this dunder init method, for which we do have a position, but we don't have a surface. But then once again, we have a groups parameter. So we have to figure out this surface. For that, we need just a bit more information. I want to have 3 attributes: self.frames, self.frame underscore index, and self.animation underscore speed. The values for all of them are going to be the frames parameter, the value 0, and for the animation speed, I went with 10. Once we have that, inside of super dunder init, we can get the surface via self.frames and self.frame index. That's basically it. Besides that, I also want to have an animate method with self and delta time in there, self.frame index plus equals self.animation speed multiplied with delta time, and self.image is going to be self.frames with an integer of self.frame index, then modulus with length of self.frames. That would be a really basic animated sprite class. And I hope you can see at this point why inheritance is quite useful. For this class, we never specify the image or the rectangle. All of that is handled via the parent class. And that system we are going to expand on quite a bit, because animated sprite is never going to be used inside of the game. The only way that we are going to use it is as the parent class for the player. And there we want to have the animated sprite. For that to work, we have to make a few changes. Most importantly, when we are creating one instance of the player, I want to have a bunch of frames. And also, we don't want to have a surface anymore. Instead, I want to pass the frames through to the parent class. Because now, when we are calling this dunder init method, we are effectively running all of this, for which we are going to need frames, positions, and groups. And I realized the order here is a bit messed up. The first argument needs to be frames, then we have the position, and then we have the groups. Once we have that, inside of main.py, when we are creating the player instance, we have to add one more argument, self.playerFrames. And now, if I run all of this, we have a very basic player image, which isn't animated yet, because we are not calling the animate method. That is a very easy thing to fix inside of update self.animate with delta time. After that, we are getting the animation. That is looking pretty good. And once again, notice here, we didn't write any logic inside of the player for the animation. All of that happens inside of the parent class, which makes it much easier for us to organize all of this. Although, truth be told, we do have to override the animate method. I want to have inside of the player define animate with self and delta time. Or in other words, at this point, from animated sprite, this method is not going to work anymore. That is necessary because for the player, we have to account for the different states. For example, if the player is not moving, then we shouldn't have an animation. But step by step. First of all, let's recreate the very basic logic. I want to have self.image is going to be self.frames. And then via the integer, we are doing self.frame index modulus with the length of self.frames. Also, we're going to need self.frame index plus equal self.animation speed multiplied with delta time. Although this we only want to do if a certain condition is true. In my case, if self.direction.x is different from 0. Or in other words, we only want to update the animation if the player is moving left or right. With that, back inside of main.py, if I'm not moving, we have no animation. However, once I'm going left or right, the player is animating. That is working quite well. Also, if the player stops moving, else, then I want to set self.frameIndex to 0. That way, we are going back to the starting position. Let's try. And I can move around. If I'm moving, we get the walking animation. But if I stop moving, the player is idle. The one major thing that is missing at this point is that the player is always facing to the right. To fix that, I want to, inside of the dunder init method, add another attribute, self.flip, and by default, this one is going to be false. Next up, after we have gotten the part from the animation, I want to add another thing to self.image. Or in other words, I want to run pygame.transform.flip with self.image, self.flip. This is for the horizontal flip, and for the vertical flip, this one should always be false. That way, by default, we are not going to get any change. However, if we are setting self.flip to true, then the player is always going to be flipped, with the animation still working just fine. Which means we just have to update this value in real time, which we are doing inside of this if statement. If we have movement, or in other words, if self.direction.x is different from 0, then we want to set self.flip to self.direction.x being smaller than 0. This is going to return a Boolean value. If we are moving right, it's going to be true. If we are moving left, it's going to be false. And this is then going to influence the flip method. I can move to the right and to the left, and we always get the proper facing direction. So this is working quite well. The last thing that I don't like is that if the player is jumping, we still are playing the walking animation, which looks really weird. To fix that, before we are doing anything in the image, I want to check if not self.onFloor. Or in other words, this if statement is checking if we are in the air. And if that is the case, self.frameIndex should be 0. Let's try now, and if I'm on the floor, we have the walking animation. But if I am jumping, we are getting the first frame. So this is kind of working. The issue is we don't want to have the frame with the index 0, we want to have the index 1. That is going to look much better. Now it looks like the player is jumping, which I like much better. And this we can make just a bit more elegant. I want to set self.frameIndex to 1 if the player is not on the floor. If that is not the case, else, then we want to keep self.frameIndex. And then we also don't need the other stuff anymore. and that feels a bit nicer. The end result, though, is still going to be just the same. Perfect. And with that, we have a very basic player animation, which is getting us very close to a proper platformer. To finish up all of this, let's do an exercise. I want you guys to do two things. Number one, create a class for the bee and the worm. Later on, those two are going to behave differently, so we will need two classes, although both should animate from animated sprite. Then create one instance of each in the level, and really important for this one, both of these enemies should be animated. Besides that, write a function to import all of the audio files. You don't have to play them at this point. I simply want to have all of the files inside of the game. That should be quite a bit of work. Pause the video now and see how far you get. Righty, to get started with the enemies, I want to create another class called bee. And this one, for the parent, is going to have an animated sprite, which means when we have the dunder init method, we want to have a bunch of frames, a position, and the groups. And then I want to call super dunder init, in which we are calling this dunder init method. For that, we already have all of the arguments. We need the frames, the position, and the groups. And that is all we need to get started. So inside of main.py, when we are calling the setup method, I want to create one instance of a bee somewhere on the level. For that, we will need self.bFrames. The import for that we have done earlier, this value here. For the position, let's go with 500 and 600, two entirely random values. Finally, for the groups, I want to have self.allsprites for now. After that, if I run the game, you can see we have one bee inside of the level. Doesn't do anything at the moment, but at the very least we have something. And to animate this bee, you could simply write an update method inside of the class, don't forget delta time, and then call self.animate with delta time. If you do that, we have an animated bee. So this is all we needed for this part. Next up, I want to copy all of this and then create a worm class, which for now at least is going to stay identical to the bee class, which means inside of main.py, I want to create a worm, and for that we will need self.wormFrames. For the position, let's go with 700 and 600, and then self.allSprites. I can run the game now, and we are getting a worm somewhere in the air. Not perfect yet, but that we can work on in the next bit. Before that, we want to import all of the sounds, for which we could do something like import image, or in other words, we could wrap pygame.mixer.sound in some other stuff to make it more efficient. But I want to go a bit further. I want to have self.audio, and this is going to be a dictionary that will be created via audio importer. The file path for this one is simply going to be audio. This function doesn't exist at the moment, so inside of support.py, I want to have audio underscore importer, for which we need a path parameter that we are unpacking right away. In there, first of all, I want to create an audio dictionary, which doesn't have any values by default. Then once again, I will need for folder underscore path. We don't care about subfolders, so underscore, and then file underscore names in walk, join, and unpacking the path. In there, we want to check for file underscore name in file names. And now we don't have to sort the file names because we don't care about the order of the sound files. This one simply doesn't matter. I want to create a full underscore path. Via the join method, I want to combine the folder path with the file name. Once we have that, I can get the audio dictionary and then create a key, which should be the name of the audio file. And I should actually explain, so at the moment, we don't need code, data, or images. I want to look at the audio folder. In there, we have impact.ogg, music.wav, and shoot.wav. For this audio dictionary, the key should be the name of the file without the file ending. which I can get via the file name, and then use the split method once again to split all of this wherever we have a dot, and then pick the first value. That way, we're getting the name of the file without the file ending. And the associated value should be pygame.mixer.sound with the full underscore path. And that is literally it. At the end of all of this, we can return the audio dictionary, and that we are capturing inside of self.audio. In other words, if I print self.audio and run the entire game, we are getting a dictionary with 3 sound files, or rather 3 key value pairs, the name of the file and then the sound object. And to use that, all we would really need to do, for example, to play the background music, is self.audio and then the music with play. Inside of the game, we are getting some music. Although this isn't something that I want to do because it would be really distracting. Anyway, with that, we have a whole bunch of imports and we have the player animations. For the next section, we are going to add proper timers, which are going to do quite a bit inside of the game. For example, we have a cooldown for the bullets, and every time the player shoots a bullet, we have a short fire animation. Both of those things are going to be heavily influenced by the timers. On top of that, we have a repeated timer that creates a bee enemy. And all of this we want to have as flexible as possible. Or more generally, games rely heavily on timers. For example, for this game, whenever the player shoots a bullet, we have a cooldown. We spawn a bee every X seconds, we have a fire sprite animation for a bit that gets destroyed after a few milliseconds, and all of the enemies will die after 0.2 seconds after being shot. For all of these things, we will need a timer. Or in other words, ideally, we want to have a reusable timer that can do number 1, be easily called anywhere. It should also call a function on timeout, and it should be repeatable. And for all of this, we have already seen the most fundamental logic for a timer. We are simply getting the current time, subtract the start time, and if the resulting value is greater than some duration, we are doing something. This is some very basic logic, but this I want to expand upon. And also at this point, I do not want to use the inbuilt Python events anymore, because those just aren't that flexible, and the system that we are going to create will be much better. For all of that, back inside of the code, I want to create another Python file, timer.py. First of all, we will need from settings and import everything. Afterwards, we have a timer class without any inheritance. I want to have a dunder init method with quite a few parameters. The most important one will be the duration. Besides that, we have a function with a default value of none. Then we have a repeat value, also with a default value of none. And we have an auto start parameter that by default is going to be false. After that, I want to set self.duration to the duration. I want to set self.start time to 0. And finally, self.active is going to be false. Via those 3 values, we can create an update method in which we are fundamentally going to check if the current time minus self.start time is greater or equal to self.duration. And if that is the case, we want to do something. Now, this is not going to work at the moment because we do not have the current time. For that, we would need pygame.time.getTix. Next up, if this if statement does happen to be the case, we want to run self.deactivate. And while we are here, I also want to create an activate method without any custom parameters, so we want to have activate and deactivate. For both of those methods, for self.activate, we want to have self.active being true, and self.startTime is going to be pygame.time.get_ticks. For deactivate, we are going to do basically the opposite. Self.active will be false, and self.startTime we can set back to 0. And that is all you need for a basic timer. To go over it really quickly, by default, we have the dunder init method, and to activate the timer, we are calling activate. In there, we're getting the start time, which we are using inside of the update method. In there, we are checking the current time and subtracting the start time. If the resulting value is greater than self.duration, then we are calling self.deactivate, which is going to set self.active to false and the start time to 0. So with that, via self.active, we can check if this timer is active or not. And the way you would be using that, let's start inside of the player. We don't need any of the other classes. I want to work inside of the dunder init method and create a timer section. For the player, we only want to have a shoot_timer, which is going to be the timer class we have just created. And for that, we have to import from timer, import timer. For now, we can only set a duration, 500, or half a second. We are working in milliseconds here. Next up, when we are calling the input method, I also want to check if keys and pygame.k_s. That is the S key on the keyboard that I want to use for firing a bullet. If that is the case, shoot bullet. If we run this without anything else, I can press S and we're getting shoot bullet on every single frame of the game. Or in other words, we would be shooting a bullet 60 times per second, which obviously would be way too many bullets. So we are going to need a cooldown timer, which we get via the shoot time. Or in other words, we want to check two conditions. If the player is pressing a button and self.shoot_timer.active. And also this should be self.shoot_timer inside of dunder init. Also, we want to check if this shoot timer is currently not active. Or in other words, after the player shoots one bullet, we want to get self.shoot_timer and activate it. So while the timer is running, the player is not able to shoot a bullet. Just one more thing before we can use all of this. The timer is only going to work if we are calling the update method, which at the moment we are not doing for this self.shoot_timer, so nothing would happen. To fix that, inside of the update method, before we are doing anything else, self.shoot_timer.update. That way, inside of the game, if I hold down S, we are only getting one bullet every 500 milliseconds. And if I increase the duration to, let's say, 1500, I can try all of this again. And now we are getting much fewer bullets. Looking pretty good. Besides that, inside of the timer, I want to have 3 more things. We want to call a function once this if statement triggers. Then we want to make the timer repeatable and be able to auto-start all of this. And auto-start, just to explain it, basically activates the timer when we are creating it. So we don't have to call activate on it. To get started with the function, I first of all want to store this as an attribute. Self.func is going to be func. Before we are deactivating the timer, I want to check if self.func exists, and if that is the case, I want to call it. Although before we continue, there's one more thing that I want to add. Self.startTime is different from 0. When we are getting started, the start time is going to be 0, and there is a chance that pygame.getTicks is also going to return 0, which means all of this would be running, and then we would trigger this one as well. And via this second condition, we are avoiding all of that. A fairly minor point, but it can be a bit annoying. Anyway, to test all of this, inside of dunder init of the game class, I want to have a timer as well. Let's call this one the b_timer, for which we will need a timer class that we don't have yet from timer import timer. The duration of this one is going to be 200. And then we want to call a function, self.create_b. This one doesn't exist at the moment. So we have to create it, define, create_b without any custom parameters. Inside of this method, I simply want to create a b, which we have already done. So in there, we have a b. And once again, don't forget, we have to call, before we are doing anything else, self.be_timer, and I realized once again I have forgotten the self. Anyway, after that, self.be_timer.update. Now this is still not going to work because this timer does not start by default. What we would have to do is call self.be_timer.activate. And let's add a slightly larger value. So let's say after 2 seconds, we want to call this method, which would create one instance of a bee. If I run the game, and after 2 seconds, we get a bee. This has worked really well. With that, we can do an exercise. I want you guys to add the repeat and the auto start functionality to the timer. Pause the video now and see how far you get. Auto starts is the easier part actually. All we have to check for this one is if auto start is true, then we want to call self.activate right away. With that, inside of main.py, we don't need this activate anymore. Instead, when we are creating one instance of the timer, I want to add auto start and set this one to true. If I now run all of this, we should still be getting a bee. And we do. Perfect. Besides that, we have to work on repeat. That should be an attribute. Self.repeat is going to be repeat. And basically all that we have to do, once all of this is running out and we are calling deactivate, we want to check if self.repeat is the case. Self.activate. That way, inside of main.py, for the bee timer, I want to set repeat to true. And I guess to make all of this a bit more visible, I want to have random values. From random import rand int. And then for the bee position, for now, I want to have a random integer between 300 and 600. And the same I want to have for the y position. Also for the timer, I want to have a duration of 500. And now let's try all of this. And we should be getting a whole bunch of bees. That is looking really good. Perfect. And I hope from looking at this thing, you can tell that this is much better than the inbuilt Python events. We don't have to create a custom event or work in the event loop. We are simply creating a timer and then call a function whenever it times out. And that's basically it. Nearly done. There's just one more thing that I want to do. Because in actual larger projects, what I ended up doing a lot is checking for self.shootTimer.active. And this .active you can get rid of. You would need, let's do it right below dunder init. We want to have define dunder bool. This is what's being called if you put this timer inside of an if statement. The default functionality for this one is that you are always returning true, which is not what we want to do. In our case, we want to return self.active. That way, inside of the player, we can simply check and not self.shootTimer, and the return value would be this timer being active or not active. Or in other words, if I run main.py and I press S and hold it down, we are only getting shoot bullet every 1.5 seconds, I believe. Whatever we specified inside of the timer. And well, with that, we have a really powerful timer that we can now use to add a whole bunch of things to our game. Right below the sprites, I want to create a class called bullet, which for the parent is going to have a sprite. After that, we will need dunder init with self, a surface, a position, a direction, and the groups. After that, we have to call super.dunder init, in which we are calling this dunder init method, for which we will need a position, a surface, and the groups. Besides that, I want to have some extra stuff for the movement. Self.direction needs to be an attribute, and then we have self.speed, which I have set to 850. Besides that, we will need an update method with self and delta time, and then call self.rect.x plus equals self.direction multiplied with self.speed multiplied with delta time. So with that, we have a very basic bullet that we now want to create whenever the player presses the S button and the timer isn't active. Also, the bullet we want to have inside of another sprite group, self.bullet_sprites. pygame.sprite.group. This is the part we have seen plenty of times by now. To create a bullet, below create B, I want to have create_bullet. For the parameters, we will need a position and a direction. Both of those we are going to get from the player. Although for now, I simply want to create a bullet where we already have a surface. Self.bulletSurface, we imported this inside of load assets not too long ago. For the position and the direction, we are simply going to use the parameters. Finally, for the groups, I want to have a tuple with self.allSprites and self.bulletSprites. This create bullet we now have to add to the player. I want to have self.createBullet inside of the player. For that to work, back inside of the sprites, the player is going to need one more parameter, create_bullet. I suppose we can store that one as an attribute right at the top. Create_bullet is going to be createBullet. And this createBullet we want to call instead of the print statement, createBullet, and then we are going to need a position and a direction. For the position, at the moment, I simply want to get self.rect.center, and for the direction, this one should be -1 if self.flip, and if that is not the case, else it should be 1. Or in other words, if the player is facing to the left, then we are returning -1, and if not, then we are facing to the right, so the bullet should have a direction of 1. Let's try all of this, and if I press S, we are getting a bullet. Not too many because the timer cooldown is really large, but at least we are getting something. I suppose for that, we can change the cooldown to 500 milliseconds. That way, all of this is going to feel quite a bit better. Next up, the main issue we have at the moment is that the bullet is always facing to the right, because we are not making any updates to the surface. For that, I want to have an adjustment section where we are updating self.image. All we need in here is pygame.transform.flip with self.image. And then for flip x, the only thing that we really care about, we want to get direction and check if this value is equal to -1. Or in other words, this is only going to be true if the bullet is going to the left. For flip y, we want to have false. If I now run main.py and I look to the right, we get a bullet facing to the right, and if I face left, the bullet is also facing left. Although, if you look at the player, the starting position of the bullet just isn't ideal. Or in other words, the way you have to the issue happens because if this is our player, the starting position is always the center. And the point we are placing for the bullet is the top left. We would always get something like this, which really is not ideal. To fix that, I want to work inside of createBullet and create a custom X value. I always want to get the original player center position, or position 0. To that, I want to add the direction and multiply it with a value that I think is large enough. After some testing, I landed on 34. But this we only want to do if direction is equal to 1. Or in other words, we are going to the right. If that is not the case, else, we still want to do all of this. But then we also want to account for the top left position. In other words, self.bulletSurface and then get width. After we have that, instead of the position, I want to have a tuple with x and position 1. Just to test all of this, inside of sprites, I want to set the bullet speed to 0. If I now run main.py and I look to the right, I can create a bullet. It's right in front of the player. And on the left side, we are also right in front of the player. That means we can set the bullet speed back to 850 and we get bullets that look significantly better. Cool. Now to understand this line, we have a player with a center position. That is what we are getting from the position parameter. If the player is facing to the right, then we want to do all of this, meaning we are going from this point a bit further to the right by 34 pixels. And then we are placing the top left of the bullet. I think that part is fairly straightforward. However, if we are moving to the left, then we are doing all of this. We still start from the center of the player, and then we are going to the left by 34 pixels. That covers this bit. But then you have to remember that we are placing the top left of the bullet, meaning the bullet would be roughly here, which obviously is wrong. What we want to place is the right side of the bullet. In other words, we want to move the entire thing by its own width, and this we're doing with this last line. And that is basically it. With that, we have the bullets. That covers all we need for this class. Besides that, I also want to have a fire class, which is also going to inherit from the sprite class. Now, for this one, we first of all want to have a dunder init method with self, a surface, a position, groups, and we also need the player. Basically for this one, every time the player fires a bullet, we also want to have a fire animation. Or, well, fire animation might overstate things just a bit. If you look at images, gun, there we have a fire image. This we want to show for a very short amount of time if the player fires a bullet, and then via a timer destroy it right after. And for that, we're going to need the player, so this fire animation moves with the player. It would look really weird if it didn't do that. For that, we will need a super dunder init method with the surface, the position, and the groups. That way, we are getting all of this. On top of that, I want to store self.player as an attribute. And also, I want to know when we are creating all of this, if the player is flipped or not, which means self.flip will be player.flip. On top of that, I want to create self.timer, which is going to be a timer that has a duration of 100, and it's also going to auto start. And once this thing times out, we want to call a function, which is going to be self.kill. We want to call the inbuilt kill method of the sprite, which we can totally do. Let's try all of this. Inside of main.py, besides creating a bullet, I also want to create a fire instance. For the surface, I want to have a fire surface. For the position, for now, let's stick with the position of the player. Groups is simply going to be self.allsprites, and the player will be self.player. If I now run all of this, we are getting an error. The tuple object has no attribute getFRectangle. And I think that usually means we are adding some wrong arguments somewhere. You probably saw it already. The order of the arguments are wrong. We first of all need a position, then we need a surface, and then we need the groups. If we now run all of this, we are getting a fire sprite that is pointing mostly in the wrong direction, and the position is also not great, but at least we have something. Oh, and on top of that, it also doesn't disappear. That happens because the timer is not being updated, which means we need an update method with self and delta time, although delta time we don't care about. And then self.timer.update. If I now run all of this, I can shoot a bullet, and we get a very short fire animation. That's a good start, but we also have to update the position. For that, since we have the player available, we can do all of that fairly easily. If self.player.flip, then I want to set self.rect.midRight to self.player.rect.midleft. On top of that, since we are now facing to the left, we want to flip the entire fire image. Or in other words, self.image is going to be pygame.transform.flip with self.image true and false. If that is not the case, else, then we simply want to set self.rect.mid-left to self.player.rect.mid-right. That is a good start, but on top of that, I want to copy all of this, and then inside of the update method, do all of this except updating the image. That way, this fire animation goes along with the player, which is quite important. If I now fire all of this, you can see that we have a basic fire animation, although the position is a bit off. This thing has to move down just a little bit. That is quite easily done. Inside of dunder init, I want to have self dot, let's call it y offset, which is going to be a pygame.vector2 with 0 and let's say 8 pixels. After we have that, whenever we are updating the position of the rectangle, we always want to add the y offset. That way, if I shoot the bullet, we get the proper nozzle fire animation, and that is looking pretty good. And I think now I can also demonstrate why you need this part. If I comment it out and run main.py again and shoot a bullet, sometimes you can see if the player is moving, the fire animation doesn't move along with the player, which is kind of a weird effect. Meaning we really want to include this part. Nearly done, there's just one more part I do want to work on. Let me move away from the bees, and if I shoot a bullet and turn right away, we are getting a slightly weird effect. When we are creating the fire animation and the player is facing to the right, and if we are then turning around, the entire thing falls apart. To avoid that, if the player turns around while we have a fire animation, we want to simply destroy the entire thing. Or in other words, if self.flip is different from self.player.flip. If that is the case, self.kill. That way, if I run main.py, I can move a bit further to the right, and as soon as I shoot and turn around, the fire disappears. And with that, we have the fire animation. That covers another really important part. With that covered, we just have to figure out the enemy logic and the bullet collisions. To finish up the game, I want to work on the enemy logic. For the bee, we want to have a sprite that is slowly moving to the left, with some vertical movement as well. And for the worm, we are going to move this thing in the predefined area. On top of that, we will also add the collisions between the bullets and the enemies and the player. Finally, we can add some audio files, and then we have the entire project done. Shouldn't be too difficult. For all of this, back inside of the code, I want to work inside of the sprites. And looking at all of this, we don't need the timer.py, groups.py, or support.py file anymore. Instead, we want to look at the worm and the bee. Those two classes are identical at this point. On top of that, they are going to share a bit more code in just a bit. To account for all of that, I want to create another class called enemy, which is going to have an animated sprite as the parent. For this, we are going to need a dunder init method with self, frames, position, and groups. In there, we are going to need super and dunder init, which means we are calling animated sprite dunder init and then pass through all of the arguments, which means for the bee, the parent class should be the enemy class, and the same for the worm. That already means inside of the enemy class, we can call update with self and delta time, and then self.animate also with delta time. Because of that, we don't need this update method anymore, and we are already simplifying the code. Inside of main.py, the animations should still work, and they do. Cool. For both of these classes, I want to create a move method which is also going to need delta time. And for now, we're going to add pass in there for both of them. This move method we are going to call inside of the parent class self.move. Now we have to figure out the actual movement. For the b, this is fairly simple. We want to have self.rect.x minus some amount. For that value, I want to create self.speed, which is going to be random. And this we want to multiply with delta time. For that to work, we will need self.speed, which is going to be set by a parameter, speed. With that, back inside of main.py, when we are creating a b, we will need one more argument. Also, to organize all of this just a bit better, I want to use named arguments. We have frames, we have a position, and then we have the groups. Besides that, we will need speed, which is going to be a random integer between 300 and 500. If I now run all of this, we have bees that are moving to the right. So this is already working quite well. Perfect. Although now the starting position doesn't really work anymore. What I want to have, if this is the entire level, the bees should be spawning on the right of it. For that, first of all, when we are setting up the level, we need to know how wide this tmx map is. We need tmx map and then dot width. If I now run all of this, we are getting the number 45. To understand this value, you want to go to the tile map and then map and map properties. That is going to give you this dialog on the left. And all the way at the top, you can see the width, which is 45 in my case. Or in other words, our map has 45 columns. That's literally all that this means, which we can use. I want to define a self.level_width, which is going to be tmxmap.width multiplied with the tile size. Once we have that, back inside of create b, for x, we want to have self.level_width plus some kind of offset. Let's go with the window width, just to be sure. And since the player cannot see this value anymore, we don't need randomness, meaning randint can disappear. That is looking pretty good. If I now run all of this and I move all the way to the right, at some point there should be some bees coming our way. And that is working pretty well. Next up, we also want to cover the entire height of the map, meaning we have to do basically the same thing we have done before. Besides a level width, I want to have self.level_height, which is going to be tmxmap.height multiplied with the tile size. After that, for this value, we do need randomness. We want to have a value between 0, so all the way at the top, and self.level_height. Once we have that, I can run the game, and at some point, we should be seeing bees covering the entire height. And that is working pretty well. Although for the movement of the bees, I want to add a bit more randomness. And for that, I want from math import sin. This is giving us a signed function. And what that is doing, if you put this on a graph, we need some kind of x value. And along this value, the signed function is going to look something like this. We basically get a wave that fluctuates between 1 and -1. And in our case, the x value is going to be the time. And just to demonstrate what we are going to do, inside of the player, I want to, in the update method, print the signed function with pygame.time.getTicks. If I now run all of this, you can see that we are getting a whole bunch of output. And this output is always between nearly 1 and then nearly -1. And it goes between those two values really, really quickly. That is all that we are doing in here. Now in the player, we don't need it, but inside of each instance of the bee, we want to use all of that to influence self.rect.y. To that value, we want to add the sign value of pygame.time.getTix. Don't forget to call it, and this value will now be between 0 and 1, which is not going to do very much for the vertical position. But we can multiply it with some sort of amplitude. And also don't forget, whenever we have movement, we have to multiply things with delta time. Now amplitude doesn't exist at the moment. Although we can create it, self.amplitude is going to be a random integer that we have to import from random import rand int. I want to have a random value between 500 and 600. With that, if I run all of this again, and we have to wait for the bees for just a second, we should be getting something. And well, this is kind of working, but it's not ideal yet. That is because the frequency is way too high. To fix that, I want to have self.frequency, which is also going to be a random integer. In my case, between 300 and 600. And this value we want to use to divide get.tix, or in other words, divide by self.frequency. With that, we should be getting a proper outcome. If I now run the game, and we should be seeing bees moving in a much more organic way. This is much nicer. Perfect. That covers the movement of the bee. Next up, I also want to have a constraint. Because once again, we keep on creating bees, and we have to make sure that we are getting rid of them at some point as well. Now, in this case, this is fairly simple. We simply want to check if self.rect.write is smaller or equal to 0. If that is the case, we want to kill the sprite. And also, this constraint method we want to call inside of the parent class, self.constraint. To make sure that the game doesn't crash, we also have to add the same method to the worm class, meaning in here, constraint without any custom parameters, and this one is going to get pass for now. With that, we have the bee enemy. Next up, we have to work on the worm. Inside of tiled, we have an object layer called entities. This one contains the player. That's the part we have already seen. Besides that, we have a whole bunch of rectangular areas. And the way those are going to work, I want to spawn a worm roughly here, and then make it move to the right. If the worm goes too far to the right, let's say we are ending up here, then the direction of this enemy should be reversed. The same thing we want to do on the left side. And I think you know where this is going. This is going to be your exercise. I want you guys to create the worm movement logic. Pause the video now and see how far you get. First of all, we have to import all of the areas. That is going to happen inside of setup after we are creating the player. Now, we already are creating one instance of the worm that we want to keep. However, first of all, we want to check if obj.name is equal to worm. And just to make sure, if you go back to tiled and you click on one of these areas, you can see name worm. If that is the case, we want to create one instance of the worm and then add a couple of arguments. The frames can stay as they are. And at least for now, we can also keep the groups. But we have to update the position. This one simply doesn't work anymore. And what I want to do instead is create a pygame f rectangle with the size of the rectangle inside of tiled. That we can get via obj.x, obj.y, obj.width, and obj.height. With that, we have a rectangle that defines the area that the worm can move in. Although to use that inside of the worm, we need to update the parameters. Instead of a position, we now have a rectangle. To turn that into a position, at least for the super dunder init method, we want to get rect.topleft. And that should already do something. If I now run the game, we're getting multiple worms, and they are in the area position, at least roughly. Now, obviously, the worm should always be on the ground. For that, I want to update self.rect.bottom left and set it to rect.bottom left. That way, the worms are always going to be on the floor, which is already feeling a lot better. I also want to keep the rectangle, let's call it main underscore rectangle. This is just going to be the rectangle from the parameter. Other than that, we want to have self.speed, which can be a random integer between 160 and 200. Also, we will need self.direction, which can be 1 by default. Afterwards, for the move method, I want to get self.rect.x plus equal self.direction multiplied with self.speed multiplied with delta time. With that, since we are already calling the move method, all of the worms are moving to the right, which is a good start, but not ideal yet, because they are supposed to turn around. For that, we will need the constraint method. And the basic logic, just to reiterate, if this is the area, the worm is starting in the bottom left and also moves to the right. If we are then outside of this area, we want to go the other way. Now for that, you could check if the right side of the worm is greater than the right side of the area. And do the same thing for the left side. Although that would be a bit of an overkill, because what we can do instead is to check if not self.main rectangle.contains with self.rectangle. This way, we are checking if the rectangle is not entirely contained by the main rectangle anymore, which can only happen if we are too far to the left or too far to the right. If that is the case, self.direction multiply equal -1. With that, we should be getting the proper constraint. This is looking really good. Just one more change that we have to make. Whenever we are doing this, we also want to invert all of the frames so that it looks like the worm is moving in the right direction. All we have to do for that is override self.frames, which we can do via pygame.transform.flip. And in there, we want to get a surface and then true and false. This we're doing for every surface in self.frames. Once we have that, we're getting the proper animation, and that is looking pretty good. Now, once again, this could be optimized just a little bit more, because now inside of the game, every time the worm is hitting a specific point, we are transforming two surfaces. What you could do instead, inside of load assets, load the worm frames and then invert them right inside of this method. Afterwards, you can simply load the right frames depending on what you have inside of the worm. That would also work, but for this game, it's not too much of an issue. And I think at this point, if you want to implement it, you can do it on your own. Anyway, with that, we have both of the enemies, which means now we can work on the collision methods. Define collision, and those are going to be the collision between the bullet and the enemies and the player. First of all, I want to have the collision between the bullets and the enemies. For bullet in self.bullet sprites. And then get all of the sprite collisions, which we're getting via pygame.sprite.sprite_collide. In there, we want to get one bullet and then self.enemy_sprites. This one doesn't exist yet. We will change that in just a second. Finally, we will need to kill, which should be false. Now, before we can continue, we want to work inside of the dunder init method and then create the enemy sprites group. This we want to use both for the worm and for the bees, meaning those should be in self.allsprites and self.enemysprites. The bee we are creating inside of the createBee method, and in there, for the groups, I want to have allsprites and self.enemysprites. With that, this line should be working. And I suppose while we are here, we can also add pygame.sprite.collide mask right away. Next up, we want to check if sprite collision. Then we want to get the bullet and kill it. And for sprite, in sprite collision, we want to call sprite.destroy. Once again, this method does not exist. But that we can change because inside of the enemy class, we can have define destroy, which for now is simply going to call self.kill. All we have to do now is, after we are calling all sprites update, self.collision. Let's try all of this now, and if I shoot at one of the worms, they disappear. This should also work a second time, perfect. And once I hit a B, there we go, this is also working. Although this I want to refine a bit by using a mask inside of the enemy. Or in other words, first of all, I want to create self.def_timer, which is going to be a timer with a duration of 200 milliseconds and the function self.kill. As soon as we are calling the destroy method, we are starting this timer, self.devtimer.activate. Besides that, I also want to set self.animationSpeed to 0, and then self.image should be pygame.mask.from_surface with self.image, and that we want to turn to a surface straight away. Also self.image and set color key with a black color. That way, once the sprite is being destroyed, we don't have an animation anymore, and the entire image is going to be a white silhouette. On top of that, I want to stop the movement of the enemy, which we can do inside of the update method. I only want to call move and animate if not self.devTimer. As soon as the dev timer is running, we don't want to call move or animate anymore. You could also put a constraint in there, it doesn't really matter. Once we have that, if I now shoot at a worm, we're getting a white silhouette for a short time, and this doesn't change. That happens because self.devtimer.update was not called. Let's try this again, and I can shoot at a worm, and it disappears. Perfect. This happens a second time as well. Very good. And now I have to hit a B. Let's hope I get one. There we go. This is also working. Which means with that, we have the proper enemy logic. That was basically it. And I hope from the logic here, you can see how inheritance can be incredibly powerful. Inside of the bee and the worm class, we are not actually doing very much. We are simply initializing a couple of basic values, then we have a very simple move method, and then a fairly simple constraint method. That's pretty much it. A lot more of the logic happens inside of the parent enemy class, the animations are covered inside of animated sprite, and the very basic setup happens inside of the sprite class. That way, the entire thing is much more manageable, and for a larger project, we would be writing a lot less code. The last thing that we really have to work on is the collision between the enemies and the player. All we need for this part is if pygame.sprite.sprite collide with self.player, self.enemy sprites, and the do kill argument doesn't really matter. Let's go with false, and then we want to have pygame.sprite.collide _mask. If that returns anything, then we want to set self.running to false. Let's try that part, and now as soon as I get hit by a worm, the game should be over, and it is. Perfect. That means the last thing that we have to implement is the audio. That means inside of dunder init, after we are loading all of the assets, we are running the setup method. I guess in there we can start the music. All the way at the bottom, I want to get self.audio and then get music. Remember, for this part, the name of each of the files is the file name without the file ending. This file we want to play with loops being -1. Let's try. Cool, that part is working. And just while we are testing the other audio files, I want to comment out this part. So next up, we have to work on the shooting mechanic. That means whenever we are creating a bullet, we also want to self.audio shoot and play. And now, every time I'm shooting a bullet, we are getting another sound. Whenever we are hitting an enemy that happens inside of collision, we want to play self.audio. This one is called impact, and then play it. With that, we are getting a sound every time we are hitting an enemy. And with that, we are done. This is the entire game. The last thing I suppose that we have to do is uncomment the background music. This covers another pretty fancy game. So I hope this was useful, and at this point you should have a really good understanding of pygame. Which means there's just one more game to go, and for that we're going to work a lot more with user interfaces. There is just one more game that is left to make, and that is the Pokémon inspired one. The major focus here is going to be on the UI system. Essentially, we are going to create a menu and the player can select different options. Generally, Pokémon games aren't terribly sophisticated. You essentially have a database and you access all of that via a UI system. Although the details can become a bit more advanced. Now, if you want to make a really fancy RPG in this kind of style, check out my dedicated video. For all of that, I am also using pygame, meaning if you could follow along so far, you will feel right at home. Anyway, for now, we want to set up the basic sprites, so that we have the player monster and the opponent. Let's jump right in. We already have a couple of things ready. Most importantly, inside of main.py, we have a game class with all of the basic setup, and then we have a game loop. If you run all of this, you are getting a basic window. It doesn't do anything at the moment, but that we can work on later. Besides that, we have support.py. In there, we have a folder importer, and it stores the data as a dictionary, which means the file name is going to become the key, and the associated value will become a surface. Besides that, we have an audio importer function, which is going to work in a very similar way. We have an audio dictionary, and in there, we are creating key value pairs, with the file name becoming the key, and the mixer sound file becoming the value. Besides that, we have a timer that we have already seen in the last game, and then we have settings, in which we have pygame, the join and the walk method, then we are defining a window width and a window height, and then we have 4 dictionaries. Colors is a very simple one. In there, we are simply defining a couple of colors. Then we have monster data, and this one gets a bit more complex. We always start with a key, and this is the name of a monster. The associated value is then going to be another dictionary with the monster element and the amount of health. And that is all we have for the monsters. There are no levels or attack points, we simply have the element and the health. Besides that, we have the abilities. This is going to be another dictionary where we have the name of the attack and then a damage, an element, along with an animation. Finally, we have the element data, which is going to tell us how well an element works against another element. For example, if we have fire and we attack a plant, then we are doing twice as much damage. For now, this data isn't too important, but later on, we are going to rely quite heavily on it. Anyway, before we continue, here is the project folder, and so far, we only looked at the code files. Besides that, we have a couple of audio files, and then inside of images, we do have quite a bit more. For now, the most important files are inside of back. There we have the back sides of the monsters, and then we have the front of the monsters as well. There are a few more things. For example, inside of simple, we have each monster in a much smaller graphic. Then we have the other folder. In there we have the background and the floor for each monster. This folder is fairly simple, but then we have attacks. And inside of attacks, we have something that we haven't seen yet, where we have multiple graphics on a single PNG file. Later on, we will have to break up those into individual parts. But once again, this isn't something we have to worry about at the moment. Below the groups, I want to create a data section. where first of all, we are defining all of the player monsters. And this is going to be a list of names. For example, in there, I want to have the individual strings of the monsters. Let's go with 3 examples for now. We want to have Sparchu, Cleave, and Jakana. And by the way, to get all of the monster names, you want to look at monster data, and in there, you can find all of them. For now, I want to have some static data, so it's a bit easier to go along. But later on, this will be randomized. Once we have that, I want to create self.player_monsters, for which we want to create another list. And in there, we have a monster class that doesn't exist at the moment. We will work on that in just a second. First of all, though, for name in player monster list. For each monster, we want to have a name and a surface. The name we are getting from the list comprehension. The surface we have to import. For that, I want to create another method. Define import_assets without any custom parameters. And for now, I want to have all of the back_surfaces, for which I can use support.py. I simply want to folder import and then go to a specific folder, which in my case is going to be images and then back. In there, we have a whole bunch of images that we want to import and then store inside of a dictionary. Images and back, and also I want to print self.back surfaces. After we have that, inside of the dunder init method, self.import assets. If I now run all of this, we are getting name error monster not defined because this class doesn't exist. That is totally fine. First of all, though, what is much more important, if you scroll up, we have a dictionary with the monster name and the monster graphic. So next up, for the surface inside of the monster class, we want to get self.back surfaces and then pick one of the surfaces via the monster name. And for that, it's really important that the monster names you define inside of the player monster list aligns with the file names that you are importing in back surfaces. If that doesn't work, you are going to get an error. Anyway, once we have that, inside of the code folder, I want to create a new Python file, monster.py, in which we want from settings, import everything. And then class monster with pygame.sprite.sprite. Then we will need a dunder init method with self, a name, and a surface. At this point, you might be wondering, don't we also need the groups? And well, this is what we have done so far. But for this particular game, I don't want to do it. Which means inside of this dunder init method, I simply want to call super dunder init without any arguments, which is totally fine to do. The reason for that is, when I am creating all of the monsters, I only want one of the monsters to be visible. And only that one individual monster that is visible should be inside of all sprites. We'll cover that later. First of all, though, we will need self.image and self.rectangle. The image is really simple. We simply get the surface. For the rectangle, I want to have self.image and get f_rectangle, in which we are placing the bottom left. For the position, I want to have 100 and the window height. If this is the main window, we want the player monster to be here. Or in other words, we want to place the bottom left in the bottom of the window with a bit of padding to the left. Finally, I want to store the name as an attribute, which means self.name is name. Once we have that, inside of main.py, I want from monster import monster. Once we have that, inside of the game, we still cannot see anything, but at the very least, the game doesn't crash anymore. After we have the player monsters, I want to get a single monster and store it in an attribute. Self.monster is going to be self.playermonsters with index 0. And this one monster, I want to add to all sprites, which I'm doing via self.allsprites and add self monster. With that, we can see one of the monsters in the bottom left. And to make all of this look a bit better, I want to import all of the background surfaces. Inside of import assets, self.bg surfaces is going to be folder importer. We want to go to images, and in there we have other. If you look at images, there we have other, which contains bg.png and floor.png. Once we have that, before we are drawing anything else, I want to get self.bg surfaces and then bg. This we want to blit on the display surface, self.displaySurface.blit with the surface, and the position is going to be a tuple with 0 and 0. I can now run all of this, and this is already looking a lot better. Next up then, inside of the monsters, I want to create another class called opponent, which is also going to be a pygame.sprite.sprite, for which we will need a dunder init method with self, name, surface, and this one is going to get groups. Since we are only ever going to create a single opponent, we can add those to the groups, which means super dunder init with the groups. Then we will need self.image, which is going to be the surface, and self.rectangle, which is going to be self.image and get f rectangle, in which I want to place the mid bottom at the position window width -250 and 300. I hope at this point you get some intuition where these points are. But just to go over it really quickly, we are placing the mid bottom at position window width -250, going from the right 250 pixels. From the top, we are going 300 pixels, so we'll be on this point, which is going to define the bottom of the monsters. So we're getting something like this. To see all of that inside of main.py, I want to import monster and opponent. Afterwards, inside of the data section, I want to create self.opponent via the opponent class. And for that, I will need a monster underscore name. I will need a surface and self.allSprites. Getting the monster name and the surface is going to be your exercise. Or in other words, I want you guys to import different surfaces and then use them to create one opponent. This opponent, by the way, should be random. Try to figure this one out. First of all, inside of import assets, we will need the front surfaces, which we are getting via folder importer. There we want to go to images and then front. And just to test things, I want to have an opponent underscore name, which for now, let's go with Aatrox. Then this opponent I want to use for the name, and for the surface, I want self.frontSurfaces, and then pick one entry via the opponent name. I can now run all of this, and we are getting the opponent. This is working. For another example, let's go with Syndril. Should also work just fine. And it does. This is looking good. Which means we just have to get a random name, for which we will need from random import choice. And then use the choice method, for which we are going to need a list, which in our case is the monster data, and we want to get the keys. I can now run all of this again, and we are always going to get a random opponent. Next up, inside of the monster, I want to add some data. To get started, I want to get the element of the monster and store it as self.element. This we get via monster data, the monster name, and then the element. Or in other words, we are going to monster data, pick this dictionary, and then get the element. Also, while we are here, I want to create self.health and self.max_health, which we are also getting from the same dictionary, which means I want to have monster data, name, and not the element, but health. And by default, when we are creating the monster, health and max health should be the same. Which means we can do something like this, where self.health is the same as max health is the same as monster data, name, and health. Via that system, we can easily create two identical values. Nearly done. The last thing I want to get is self.abilities, for which I basically want to get 4 random values from the abilities data. That we can do via another submodule of random. The one we want to import is called sample. What this one is going to do, if you call it, you have to add some kind of list, which in my case, once again, is going to be the abilities data, and I want to get the keys. And then I have to specify a second argument, which is the number of values that I want to get. In my case, 4. That way, we are getting 4 random values from this dictionary. And just to make sure all of this is working, I want to print self.name, self.element, self.abilities, and finally self.health. If I now run main.py, we're getting a monster name, the monster element, the monster abilities, and the monster health. Now, all of this we also want to do for the opponent. Ideally, we want to create another class called creature, which would give us all of this stuff. The issue is, when we are creating the rectangle, we are placing different points. The bottom left for the player and the mid bottom for the opponent. Getting both of those into one parent class would be kind of a hassle. To get around that, I am going to create a class without dunder in it. I simply want to have a method get_data, in which we have to enter as an argument self and a name. Once we have that, I want to get all of this and paste it in there. That way, we are setting self.element, self.health, and self.abilities simply by having the name. That means we don't need all of this inside of the monster anymore. We only want to call self.get_data with the name. And to get access to this method, I want to use multiple inheritance. The sprite should inherit from pygame.sprite.sprite and the creature. Since the creature doesn't have a dunder init method, we can keep the super dunder init method. The end result is going to be the very same. We are still getting all of our monsters. On top of that, what we can also do for the opponent is add creature and then call self.getData, for which we will need the name. Also, for the opponent, we will need self.name, which we are also doing inside of the monster, so this we can put in there as well. That way, all of this looks a lot more organized. If I now run main.py, we are getting one additional output. This monster is called Pouch, and the data for him we're getting down here. Once again, we're getting a monster name, a monster type, a list with the attacks, and the health amount. That is a really good start. Next up, I can get rid of the print statement, and we have created a basic setup for the game. I suppose there's one more thing that I would like to do. To make the monsters stand out a bit more, there should be a floor below them, which we can get via floor.png. This I want to display below all of the monsters. Now for that, you could create a custom sprite group, but since we don't really want to do anything in there, I think it's a bit overkill. What is a bit more straightforward is another method, raw monster floor. No need for custom parameters. All that we want to do in here is for sprite in self.allSprites, and then create a floor_rectangle, which we are getting via self.bg surfaces with the floor image. On this thing, we want to call getFRectangle and then place this center to sprite.rect.midBottom. And for some offset, I want to add pygame.vector2 with 0 and -10. Once we have that, self.displaySurface.blit with self.bg surfaces and the floor along with the floor rectangle. This we now have to call before we are drawing all sprites, but after the background. Self.draw monster floor. And now we can see a floor below the opponent and below our own monster, which I think looks much better. Anyway, with that, we have the very basic setup. Next up, we can work on the UI. Now that we have the basic setup, we can work on the UI. For now, we are only going to cover the general menu and the attack menu, which work basically in the same way. And for all of that, the theory is actually really simple. A menu is just some text surfaces placed together. For example, if you want to create a menu like this, all you really need is some kind of background, this could be a surface, and then a few text options. That's basically it. Usually you create those via some kind of for loop. That way you can access all of the options via the index. This would be 0, 1, and 2. That is basically all that we are going to do. For all of that, back inside of the code, I want to create a new file, ui.py. Once again, we will need from settings and import everything. Then I want to have a class called UI. In there, we will need a dunder init method with, for now, self and a monster. This thing is first of all going to need the display underscore surface via pygame.display and get surface. And we are also going to need a font, for which we are going to use the inbuilt one, pygame.font.font with none and 30. Besides that, I want to set a left side and a top side of the menu, for which I'm going to get the window width divided by 2 and then subtract 100 pixels. For the top side, I am going to get the window height divided by 2 and add 50 pixels. We basically want the top left of the menu to be roughly in the center of the window with just a bit of an offset. Once we have that, I want to create a draw method. And all we really want to do in here is, for example, draw the general menu, which is just going to be another method, general. At the moment, I simply want to add print and general in there, because to test all of this inside of main.py, we will need from UI import UI. After that, in the game's dunder init method, we want to have a UI section with self.ui and UI. This one wants to have one argument, which is going to be a monster that we have been storing inside of self.monster. With that, we can go back to the UI class, although there's one thing I forgot. We want to store self.monster as an attribute. Self.monster is monster. After we have that, inside of the game class, in the run method, under draw, after we are drawing all of the sprites, self.ui.draw. I can now run all of this, and we are getting a general output that is looking really good. That means inside of this general method, we can start working on a basic menu. First of all, I want to define a rectangle that defines the size of the entire thing, which is simply going to be a pygame f rectangle with a left, a top, a width, and a height. The width is going to be 400 pixels and the height will be 200. For the left side, I want to have self.left and add 40 pixels. For the top side, self.top plus 60 pixels. And just to make sure we can see what's going on, pygame.draw.rectangle on self.display surface. For the color, I want to go to colors and then get the white color. Or in other words, inside of settings, there we have the colors, and I want to pick the white one. Next up, we need the rectangle to draw, the one we have just created. The border width will be 0, and the corner radius will be 4. Then I want to duplicate all of this and choose the color gray. We are still going to draw the rectangle, but now I want to have a border width of 4. That way we are getting a gray rectangle around this area. Or in other words, inside of main.py, we are getting an area for the menu. That is looking pretty good. With that, we have the background. Next up, we want to have the actual menu part of this menu, for which we will need the amount of columns and the amount of rows, which in my case are both going to be 2. After we have that, I want for col in columns and for row in rows. That way I am getting either 0 and 1 for the columns and 0 and 1 for the rows. And the general way that you want to think about it, if this is the menu we have just created, this bit here, we want to separate this thing into 2 columns and 2 rows. Inside of each cell, we then want to display some text. And for that, we are using this for loop. Effectively, we want to get a center position for each of those. Or in other words, inside of the inner for loop, I want to get an x position and a y position. The x position is simply going to be rect.left plus rect.width divided by 4 plus rect.width divided by 2 multiplied with the column. A bit more logic, but I hope it's not too complicated. Let's go through it step by step. We first of all starting on the left side of the rectangle, this line here. Then we're adding rect.width divided by 4. That way we are getting from the left side to the first horizontal center, this side here. Finally, rect.width divided by 2 multiplied with the column. And remember, the column we are getting from the for loop. This one could either be 0 or 1. If it is 0, then this entire value will become 0. So we are staying on this line. If it is 1, however, then this value will become 1, and we are adding half the width of the rectangle, which would bring us to this horizontal center. And with that, we have 2 center points. That is basically all we need. A very similar logic we want to apply for the vertical points. We want to go rect.top plus rect.height divided by 4 plus rect.height divided by 2 multiplied with the row. Once we have that, we can create a text surface and a text rectangle. The text surface is going to be self.font.render. And for now, the text is simply going to be option. Anti-alias should be true, and for the color, I want to go with black. These values, by the way, we are going to change in just a second, so whatever you put in there isn't too important at the moment. For the rectangle, I want to get the text surface and then get f rectangle, in which we want to place the center, and the position will be x and y. Finally, self.displaySurface.split with the text surface and the text rectangle. With that, we are nearly done. The last thing that I have forgotten is that the columns and the rows need to be inside of a range function. That way, we can use them for a for loop. If I now try all of this, we are getting 4 options that cover the entire size of the background. That is looking pretty good. Next up, I want to customize what I am displaying. I don't always want to display option. For that, inside of dunder init, I want to have, let's call this a control section, in which we are setting the general options, which is going to be a list with a tag. Then we have heal. Next up, we have switch. And finally, we have escape. Those are the 4 options that we want to display, which means inside of the text surface, I don't want options for the string. I want to get self and general options, and then pick one index. For that, we will need this index. I suppose for now, to test if this is working, let me add a 0 in there. If I now run main.py, we're getting the first value, so this is working, which means we just need to customize this. For that, once again, we have the entire menu with 2 columns and 2 rows. In there, for the indexes, I want to have 0, 1, 2, and 3. The formula to get these values is column plus 2 times row. For example, if column is 0 and row is 0, then the overall output is going to be 0 as well, which would bring us in this top left part. However, if column is 0 and row is 1, then the overall result will be 2, which would bring us down here. And that's basically all you need. If I now run main.py, we are getting the 4 general options. That's basically all you need. Although there's one thing that's missing, and that is input. For that, I want to have another method, define input. I want to get all of the keys in there, and then pygame.key and get just pressed. The just part here is really important. We only ever want to get a single button press. We do not want to check for button being pressed down continuously. Now we have to figure out how to connect the input to the general menu. And for that, inside of dunder init, I want to create one more attribute, self.general_index, which is going to be a dictionary in which we have the column, which by default has a value of 0, and a row with the same default value. Once we have that, inside of input, I want to get self.general_index and update the row first of all. I essentially want to increase this value by the integer of keys and pygame.k_down. And from that, I want to subtract basically the same value, except this is going to be k_up. And this should look somewhat familiar. It's basically a top-down movement system. I also want to duplicate all of this because besides the rows, we want to update the column in which we are getting k right minus k_left. That covers the very basic input. We just have to call the method, which I want to do inside of an update method. Self.input, and then inside of main.py, self.ui.update. I can now run this, and nothing is going to happen. That is because we are not doing anything in terms of output. To fix that, I want to print self.general_index. If I now run all of this, we're getting column 0 and row 0. If I press to the right, we're getting column 1, column 2, column 3, and so on. And if I go to the left, then we're getting negative numbers. The same also works for the row. This is a pretty good start. Next up, we have to figure out how to use the general index inside of the method to highlight one bit of text. For that highlight, I want to set a custom color. If an item is selected, I want to get colors and then get the gray color. And to figure out if we are selected, I want to check if the column, the one that we are getting from the for loop, is equal to self.general_index and the column. On top of that, I also want to check if the row is equal to self.general_index and the row. If both of these conditions are met, then we know the current item is selected. If that is not the case, else we simply want to get colors and black. Once we have that, instead of always drawing a black color, we want to get the color we have just defined. Which means now, inside of main.py, I can select one of these 4 options. That is a really good start. However, if I go further and further to the right, at some point the menu doesn't work anymore. If you try this on your own, it's going to be a bit more visible. But basically, if you go too far to the right, you are selecting index 5 or 10, which we don't have anymore. Our menu only goes to 2 and 2, so we want to limit those values inside of the input. For that, I want to remove the plus equal and then get the starting value. And to that, I want to add what we have already added. So far, we are doing the same thing. But all of this, I now want to put into a tuple, and then I can use the modulus operator and limit all of this to 2 rows. The same thing I want to do for the columns, so I can simply copy all of this, then put the entire thing into a tuple, and finally, modulus 2. That way, inside of main.py, if I only press down, we are still always getting the right value. This also works with left and right. And now we are always staying inside of the menu. Next up, I want to check if keys and pygame.k_space. If that is the case, I want to print the currently selected item, which I can get via self.general options and then indexing. And the formula we have already seen to get the value. We want to have the column plus 2 times the row, which in this case means self.general index and the column plus self.general index and row multiplied by 2. If I press space, we're getting attack. This also works for heal, escape, and switch. So with that, we have a very basic menu. So next up, if the player is selecting attack, then we want to display a different menu, the one for the attacks. To get that system rolling, I want to add one more attribute, self.state, which by default is going to be general. And inside of the draw method, I only want to call the general method if self.state is general, which we can check via a match case statement. Match self.state, and we want to check the case general. If we have that, we want to call self.general. Finally, instead of printing the output from the value, I want to update self.state, and it should be the return value that we are getting. Meaning if we click on attack, then the state should also be attack. With that, inside of main.py, if I click on attack, the menu disappears. Simply because we are not doing anything anymore inside of the draw method. After that, we have to implement the attack menu, which is going to be your exercise. I want you guys to modify UI general to also display abilities. On top of that, you can make this method a bit more flexible to account for any number of rows and columns. At the moment, we are setting rows and columns as a local variable, but inside of the for loop, we always assume that we have 2 rows and 2 columns, which isn't particularly elegant, so try to make this more flexible. Pause the video now and see how far you get. First of all, I want to rename general to quad select. Since we are going to use this method for attacks and general, we should have a name that reflects all of that. That also means inside of draw, self.quad select. Next up, we have to make this thing a bit more flexible so that we can display any kind of list. At the moment, we are displaying the general options. Besides that, from the monster, we also want to be able to display the abilities, which I think were inside of creature. The abilities is a list with 4 values. And this we also want to be able to display, which we can actually do fairly easily because we have the monster available. Or in other words, instead of general options, we could get self.monster.abilities, and since that is a list as well, inside of main.py, we're getting the 4 attacks of this monster. To get those values dynamically, inside of the parameter, I want to specify an index and I want to specify the options. Then for the color, I don't want to have the general index, I simply want to get the index. Same thing for the row, and with that, we are using the index. Besides that, for the text surface, I don't want to have the abilities, I want to have the options. Oh, and also this shouldn't be self.index, this should just be the index. We are using the parameter value. With that, next up, if the case is general, I want to have quad select, the index is going to be self.general index, while the options are going to be self.general options. Let's try all of this, and it's still working. Good sign. After that, if the case is the string attack, then self.quad select with self. Let's call this one the attack which does not exist at the moment. After that, self.monster.abilities. Just one more thing that we need. Inside of the control section, I want to have a self.attack index. After that, inside of main.py, I can click on attack, and we are getting the different attack options. Although at the moment we cannot do any kind of input, that is because inside of the input method, we are only updating the general index. That we only want to do if self.state is equal to general. If that is not the case, or in other words, if self.state is equal to attack, then we want to do all of this. So for now, we can duplicate it all and update self.attack index for both the row and the column. The values for that is going to be basically the same thing we have done before. And for now, I simply want to print what we are getting. Instead of general options, I want to have self.monster.abilities and then self.attack index for the row and the column. All of this we want to print, and then I can still select the different options. On attack, I can click on one attack, and we're getting the output. That covers the basic exercise. Next up, I want to clean all of this up and make it a bit more flexible. We are specifying that we have 2 rows and 2 columns. But when we are getting x and y, we always assume that we have 2 values. Or in other words, these numbers shouldn't be static, they should be dynamic, depending on what we are specifying in the rows and the columns. Also, when we are getting the input, we're getting modulus 2, which should also be relative to what we are specifying in the rows and columns. For that, in the control section, I want to set self.rows and self.columns, which are still going to be 2 and 2. That way, we don't need those rows and columns anymore. And instead, I want to use self.columns and self.rows. This isn't going to change anything because we are still using the same values. But with that system, for example, in the input, when we are getting the row, we don't want to have modulus 2. Instead, we want to have self.rows. The same thing for the columns, this should be self.columns. The same thing we want to do for attack, self.rows and self.columns. The end result should still be the same. That is looking fairly good. Perfect. So next up, we can account for a greater number of options. And just to demonstrate what I'm talking about here, if we had 6 options in total, or in other words, we had 2 rows and 3 columns. And then for the general options, let's say I also want to have items and catch. If I now run all of this, we are getting something, but we should be inside of the available area. So how can we organize this better? For that, inside of UI, I first of all want to update rect.width divided by 4. This should be divided by self.columns multiplied by 2. That way we are getting the proper start position, and then when we are adding the value, we don't want to get rect width divided by 2. This should be rect width divided by self.columns. With that, inside of main.py, we are getting everything inside of one menu. The same thing we want to do for the vertical position, self.rows multiplied by 2, and then rect.height divided by self.rows. That means when we are specifying the rows and the columns, I can flip this one around to 3 and 2. We are still getting 6 values overall, but now we have 2 columns and 3 rows. That is looking really good. Although not actually what I want to do. I don't want to have items or catch, and we should only have 2 rows and 2 columns. But now all of this is much more flexible. If you want to have a larger menu, this is how you would do it. Now you could also streamline the input method a bit But later on, I want to add more stuff in here, so I'm not going to do it. Also, I think at this point, this part has gotten quite long, so let's finish it for now. With the first part of the menu covered, we can start with the second part, in which we are going to switch between different monsters. Or rather, we're going to get the menu to switch between different monsters. The actual functionality is going to come later. And fundamentally, the system for all of this is going to be similar compared to what we have already done. In some ways, it's even going to be easier because we're only working in one dimension. But there are some other parts that are going to be a bit more complex, so let's jump right in and do all of this straight away. I want to keep on working inside of ui.py and then add another case inside of draw. The case is going to be switch. If it is the case, I want to call self.switch, which does not exist at the moment, so define switch. No need for custom parameters on this one. And once again, first of all, we want to create a rectangle for the entire area, which is going to be pygame.f_rectangle. For the left side, I want self.left plus 40, the same thing we have seen inside of the quad select rectangle. In fact, we can copy most of the arguments. The left side and the width should be the same, although for the top, I want to keep self.top, but then subtract 100 pixels from it. For the height, I want to have 400 pixels. To test all of this, I want to call pygame.draw.rectangle like we have done before in quad select. In fact, I can copy all of this and paste it in there. Since we are setting the state to what we're getting from general options, and general options include switch, this should already work, which means inside of self.py, I can click on switch and we are good to go. This menu looks alright. That means, once again, we have covered the background, so next up, we want to cover the menu part of this menu, for which we have to create one more attribute, self.visibleMonsters, which I have set to 4, but this is going to be flexible. Basically, for this menu, we want to go through every single monster that the player has, which we're getting from main.py. In there, we have a list with the player monsters. The issue now is though that we don't have this available inside of UI, which means we have to create one more parameter, the player_monsters, which we also want to store as an attribute. Self.player_monsters is going to be player monsters. That means inside of main.py, when we are creating the UI, I also want to add self.player_monsters. After we have that, I can add a for loop with for I in range of the length of self.player_monsters. Via that, I want to get an x position and a y position. The x position is simply going to be rect.centerx, while the y position is going to be rect.top plus rect.height divided by self.visibleMonsters multiplied by 2. And to that, we want to add rect.height divided by self.visibleMonsters multiplied with I. This is the same formula that we have used inside of quad select. This one or this one. Or in other words, this is the entire menu, and we want to create vertical cells, like this. For all of that, we always want to get the center, which will be the center of the rectangle. That part is super easy. And for y, we want to start at the top of this rectangle. Then we get rect.height divided by self.visibleMonsters times 2. That would get us to this original point. Finally, we want to add the vertical movement to get to the next center, like this, and so on. Once we have that, I want to get the name of the monster, which we have via self.player_monsters, which, as a reminder, is simply going to be a list, which means we can use indexing via I. This would give us one monster from which we want to get the name. Or in other words, we are getting one of those monsters, and each monster has a name. Via that, we can create a text surface with self.font.render with the name of the monster, and the alias should be true. And for the color, I want to go with black. Next up, I want to have a text rectangle, which is going to be the text surface and get f rectangle, in which for now, I want to place the center with the position x and y. Finally, self.displaySurface.split with the text surface and the text rectangle. Let's try. If I now click on switch, we're getting 3 monsters. That's looking pretty good. Although we should have a few more monsters to test all of this. Let's say another monster could be dolphin, then we have pouch, and let's say larvia. Just to make sure all of this is working, this is looking good, and inside of switch, we can see 4 of the monsters. But in the code, we have 6 monsters. The reason why you can't see them is because the last 2 monsters are outside of the window. Or in other words, if I from self.top subtract something like 300 pixels and go to switch, then you can see all of the monster names. Although this part isn't ideal yet, but we can work on it. For now, I'm going to keep this position, but later on we will change it. First of all though, we only want to display elements that are inside of this rectangle, which we can do with if rect.collide point and text rectangle.center. Only if that is the case do we want to display the text. If I run all of this again, we can only see some of the monsters. That is looking pretty good. Next up, I want to work on the input. In there, we will need another elif statement. Elif self.state is equal to switch. If that is the case, I want to update self.switch_index, which does not exist at the moment. That we can fix inside of the dunder init statement. Self.switch_index is going to be 0. And then self.switch_index is going to be pretty much what we have seen up there with the rows for attack or general, except now we want to have this switch index, and this one is an integer, so no indexing needed. To that, we want to add the integer of keys k down minus k up, and limit all of this with modulus and self.visibleMonsters. Next up, to select anything inside of switch, we want to select a custom color, which is going to be another local variable, which should be colors and gray if I is equal to self.switch_index. If that is not the case, else it should be colors and black. And that color we want to use when we are rendering the text, which means instead of black, I want to have the color. Let's try this one, and inside of switch, I can select different options. That's looking pretty good. However, that is not the system that I actually want. If this is our menu, at the moment, we can display 4 elements. 1, 2, 3, and 4. If we go beyond that, we are simply going back to 1. But that's incorrect, because what you cannot see is that below we have 2 more monsters. Those are not visible because of this if statement. If I temporarily comment it out and fix the indent and run main.py again, inside of switch, you can see that we are entirely ignoring the last 2 monsters, which obviously isn't ideal. What I would rather want is that if we go with the index below 4, then I want to move up all of the elements. For that, I want to, first of all, re-implement the if statement, and then before the for loop, add a vertical offset, which by default is going to be 0. And this v offset we are going to add to the y position. At the moment, this is not going to do anything. However, if I change this to, let's say, 150 pixels, then we are drawing everything a bit further down. And if I make this number negative, then you can see that we can see a couple of other elements. We cannot select them because of the modulus, but that's something we can work on. For now though, the default value for the offset should be 0. Also, inside of input, something better would be the length of self.playerMonsters. That is going to cover an important part. Next up, I want to work more on the offset, because this should only be 0 if self.switchIndex is smaller than self.visibleMonsters. If we are between 0 and 4, then this value should not do anything. However, if that is not the case, then we want to move up all of the items so we can see the monsters a bit further down. We just have to figure out by how much we want to move up. And in my case, this is going to be self.switchIndex minus self.visibleMonsters. This number should be negative. That way, if switch index is 5 and visible monsters are 4, then we know from this calculation that we have to go up by 1 entry. And this we want to multiply with rect.height divided by self.visibleMonsters. That way we get the height of one of the cells. With that, if I run main.py and go to switch, I can go down, and if I keep on going down, at some point the entire menu moves up, although there's an offset of 1 element. That we can fix quite easily by simply adding +1. If you now try all of this again, we are getting a menu that shows all of the monsters, which is feeling significantly better. And that is going to give us the vertical offset, although there's a problem. If I run main.py again, and I click on switch, you can see that the first monster we can select is the current active monster. They are both called Sparchu. This we want to avoid. And while we're at it, we want to add a few more restrictions. So at the moment, we simply get all of the player monsters. But later on, we do not want to be able to select the monster that's currently on the field. On top of that, we do not want to select a monster that doesn't have any health. For that, I want to create another attribute, available monsters, which we are going to get via list comprehension. I want monster for monster in self.playerMonsters, but only if the monster from this for loop is different from self.monster. That way we are excluding the currently active monster. And I want to check if monster.health is greater than 0. And as a reminder, once again, inside of monster, we are getting the health for the monster, which is later going to change, although for now, this part isn't going to do very much. With that, we have available monsters. Those we want to use inside of input. We want to check modulus and then self.availableMonsters. On top of that, inside of switch, we want to use for I in range length self.availableMonsters. When we are getting the name, this should be available monsters as well. Via that, if I run main.py again, inside of switch, we have gotten rid of the first monster. But other than that, we still have 5, the ones that we have defined earlier. Looking pretty good. Besides that, if you look at the project folder, there we have images, and then we have a folder called simple. In there, we have the simple monster images. Those I want to display next to the name inside of the switch menu, which means we first of all have to import all of this and then display them next to the name. That part is going to be an exercise. I want you guys to display the simple images next to the name. And for that, you can choose a position that you like. The specifics here don't really matter. I want to work inside of main.py and specifically in import assets. I want to create another attribute self.simple_surfaces, which we are getting via the folder importer I want to go to Images, and in there we have Simple. So in the folder, Images and Simple. Those simple surfaces we have to get into the UI, which we can do fairly easily via another argument, self.simpleSurfaces. Next up, in the UI, I want to have another parameter, simple_surfaces. We can store that right at the top. Self.simple_surfs is going to be simple surfaces. That covers that part. Next up, inside of switch, we already have the monster name. From that, we can select a surface. I am going to call this one the simple_surface, for which I will need the simple surfaces and then use indexing to get a key value pair. The key will be the name of the monster. After that, I want to have a simple rectangle, which is going to be simple surface and get f rectangle, for which I want to place the center at position x minus 100 and y. Let's display all of that right below where we display the text. I also want display surface dot blit with the simple surface and the simple rectangle. Also, I realized this should be self.simpleSurfaces. If I now run all of this again and I go to switch, we can see all of the monsters. That's looking pretty good. Another thing that I would like to add for the text position, I want to place the mid left. That way, the text is aligned to the left side, which I think looks just a bit better. But anyway, with that, we have a pretty functional menu. Although at the moment, if I press space, nothing is going to happen. To fix that, I want to work inside of input and then check in the elif statement for switch if the space key is pressed, which we have already done a couple of times. This should be straightforward. For now, I simply want to print the current selected monster, which we can get from self.availableMonsters and then indexing with self.switchIndex. Let's try, and in switch, I can select this monster, and well, you can see a sprite, so this doesn't do very much. But on the sprite, we have one attribute, which is going to be the name. Then we can get the name. So that is looking pretty good. Although this we can make a bit more elegant. Instead of printing one attribute, inside of the monster, I want to set a method that returns a value whenever we are printing this class. The dunder method we need for that is called wrapper, in which we can return a value whenever we are printing this class. In my case, I want to have an f string with self.name, and I suppose then we can add self.health divided by self.maxHealth. With that, if I now select a monster, we are getting the name of the monster along with the monster health. This is working pretty well. One last minor thing while we are here. If the player goes to the attack menu or the switch menu, there's no way to go back. To implement that, I want to add if keys and pygame.k_escape. Then I want to set self.state back to general. And then also I want to reset all of the indexes. The general index, the attack index, those I want to set back to 0 and 0 for everything. And also I want to get the switch index, and this one should also be 0. That way we are starting back from scratch. Let's try this one. I can select attack, press escape, and we are back in the main menu. If I go to switch, I can also reset, and that's looking pretty good. Finally, for the switch menu, the top side should be self.top minus 100. Although minus 140 I think is going to look a bit better. Let's try all of this now, and we have the monster menu. We can go back, and that's working pretty well. Perfect. That covers another really important part. Now that we have the basic menus in place, I want to make the entire game interactive, meaning we can attack the opponents and the opponents can attack us. The logic for all of that isn't going to be too difficult. Let's jump right in. Back in the code. First of all, in the game class, I want to have another method that I called get_input. This one doesn't really get direct user input. Instead, we're going to pass this getInput into UI, and then via that, whenever we are getting input in UI, we are returning values to main.py. You will see in a second how that works. But for now, for the parameters, I want to have this state and some data. Although the default value for that is going to be none. And I suppose for now, we can simply print the state and the data. After that, when we are creating the UI, I want to insert self.getInput. And important here, we are passing around the method. We are not calling it. That way, inside of UI, we can capture getInput and store it as an attribute. Let's do that at the top. Get_input is going to be getInput. What that means, inside of the input method, for example, when we are selecting an attack, I can call self.getInput and then insert the state, so self.state in my case, and some data. For that, at the moment, we are only printing the data, but I want to store it as a local variable called attack. And this attack, we are passing into getInput. I can run all of this, and inside of attack, we're getting the attack state and the attack. This also works with the other attacks, so a pretty good start. After that, when we are switching, I want to call self.getInput once again with self.state and the monster that we have selected. This doesn't need to be in a separate variable, although you could do that as well. Next attempt, just to make sure everything is working, I can select a monster and I get switch and the monster. Perfect. While we are here, I can also add two more elif statements. Elif self.state is equal to heal, and if that is the case, I want to call self.getInput with heal. No need for extra arguments. Heal doesn't do very much. Also, after the player selected heal, I want to set self.state back to general, which in fact is something I want to do whenever the player presses space. Or in other words, if the player is switching between monsters and selects one, then we want to go back to the main menu. That was quite a bit. Let's try. If I now go to attack and select one, we get the output and we are going back to the main menu. The same for switch. That's looking pretty good. And if I click on heal, we're getting heal and not much else happening. Finally then, for escape, I want to add one final elif statement if self.state is equal to escape. If that is the case, self.getInput with escape. And if that is the case, inside of main.py, what we can already do is if state is equal to escape, then self.running should be false. That way, I can escape and the game is over. That way, we can get data from the UI. Now we have to figure out how to actually use it inside of the game. For all of that, let me minimize everything actually. I want to work inside of getInput, because in there, we have to check for a couple of different possibilities. And I suppose we can organize this a bit better. I want to check if state is equal to attack. If that is the case, we want to call the method apply_attack. A method that does not exist at the moment, but in there, we want to target self.opponent and then use an attack, which we are getting via the data. The check for the escape state is going to be an elif statement. Also, we don't need the print statements anymore. That looks a bit cleaner. Next up, I want to have define apply_attack with self, a target, and the attack. For now, in there, I simply want to get the target and update the health of that target. I suppose for now, to keep things simple, I want to reduce that amount by 20. Just to make sure that this is working, inside of the run method, all the way at the end, I want to print self.opponent.health. If I now run all of this, I can attack the opponent, and we're lowering the health of that opponent. That's a good sign. Although not exactly the system that I have in mind. What I want instead, after the player gets the input, we are switching over to the opponent. Then the opponent does something, and then it's our turn again. For that, inside of dunder init, I want to have the attribute player_active, which by default is going to be true. Also, inside of the run method, we are only updating the UI if self.playerActive. Next up, after we have gotten input from the UI, I want to set self.playerActive to false. That way, at the moment, we should only be able to attack once. After that, we cannot update the menu anymore. That's looking good. After that, I want the opponent to do something, but there should be a delay between the player turn and the opponent turn. If you don't include that, the entire thing is going to feel much too fast. Fortunately for all of that, we have timers that we are already importing, and those timers we have created in the last game. To use them inside of dunder init, I want to have a timers section, which is going to be self.timers. And there we are going to have two key value pairs. First one is player end. That is going to be a timer with a duration of 1000. And if it times out, I want to call the function self.opponent_turn. While we are here, I want to create a second key value pair. That one is going to be the opponent end. If that is the case, we are going to call player turn. For all of that not to crash, we have to create two more methods. Opponent_turn, and we will need player_turn. Both of those get passed for now. And then, after we have gotten the input, I want to get self.timers with the player end, and then activate it. Also, never forget, you have to call the update method on all of these timers, which I also want to do in a separate method. Define update_timers with self, and all we have to do in here is for timer in self.timers.values, and then timer.update. That way, we are updating all of the timers inside of this dictionary. Then we have to call the method inside of the run method before we are updating anything else, self.updateTimers. With that, we have the basic setup. To make sure that this is working, when we are calling opponent turn, which happens after the player input, when the timer times out. Then I want to print opponent turn. Let's try. I can attack the opponent, and after a second, we are getting opponent turn. That's looking good. We first of all want to get a random attack, which we can get via the choice method, which we are already importing. The list we want to pick from is self.opponent.abilities. Once we have that, self.applyAttack, the method we have already created, this one. And then we want to target self.monster and the attack. To make sure that this is working, inside of apply attack, I also want to print the attack that we are getting. Let's try this one. I can now attack the opponent with, let's say, Scratch. Then we're getting Scratch, and a second later, we're getting Splash. And that's all we can do. We are not updating the menu anymore. That we can fix right away, actually. After the opponent turn, we want to call self.timers with the opponent end timer and activate this one. Once this timer times out, we are calling player turn, in which for now, we simply want to set self.playerActive back to true. That way, I can attack with nuke, we're getting another attack, and then after a second, I can use the menu again. Let's say I want to use another attack, spiral, and then after a second, we are getting another attack. And do we always get the same attack? No, we don't. That was coincidence. Perfect. Randomness can be a bit tricky. Next up, I want to properly calculate the damage that we are getting. For that, if you look at settings, we have two dictionaries that we have to work with. The first one is abilities data. There, we're getting all of the attacks and then the base damage along with the element. This dictionary we can access via the attack. Besides that, we have element data, which is telling us how good an element is versus the target. This I can use to calculate the proper damage amount. And getting that value is going to be your exercise. I want you to calculate the proper damage amount. Pause the video now and see how far you get. First of all, I want to get the attack data, for which we want to get the abilities data dictionary and then pick the one key value pair that we're getting from attack. Via that, I can print attack data, and let's see what we are getting. If I attack with spark, we're getting damage, element, and animation. And damage here is the base damage, which we can already use. We have the base damage that we are getting from attack data and damage. Next up, we want to calculate the element multiplier. We will need the target underscore element, which we can get from the target, and that is going to be a monster which has an element. Or in other words, we can simply get target.element. For the attack underscore element, we simply want to get attack data, and in there we have an element. We are simply picking this key value pair. Once we have that, we can get an attack underscore multiplier, for which we want to use this final dictionary. For this one, we want to pick the element of the attack and then the element of the target, which means I want to get the element data, then the attack element, and finally, I want to get the target element. And just to make sure that this is working, let's print all of this. Via an F string, I want to print the attack element, then I want to have the target element, I want to have the base damage, and finally, I want to have the attack multiplier. Let's try all of this, and if I attack with spark, which is a fire attack, we are getting fire, plant, 35, and 2. That's looking pretty good. Also, we got a second entry for fire, 35, and 1. Which means we are attacking fire with fire, so our damage multiplier is going to be 1. This is working quite well. With all of that, we can calculate the full damage amount. It's simply going to be base damage multiplied with the attack multiplier. And all of this we can clean up quite a bit. We don't need this many lines of code. For example, the base damage we are only using once, so we can use it directly in there. For the attack multiplier, we are also accessing another dictionary, so in there we can get the target element straight away, and we can get the attack data element. That way, we are doing all of this in 3 lines of code, which I think is also much more readable. Finally, to make sure everything is working, I want to print an F string with target.health and then target.max_health. If I now run all of this, I can attack a plant monster with a fire attack. Let's go spark. And that does quite a bit of damage. Just to double check, we have done 70 damage with this one attack, and we have used the spark attack, which we can check inside of abilities data. We have spark, which has a base damage of 35, which we have multiplied by 2 because we have attacked a plant monster with a fire attack. Whereas the opponent attacked us and only did 20 damage. That could have been, for example, because the opponent used Scratch, which does 20 damage, and the attack element is normal, which has no multiplier for anything. I suppose we should be a bit more careful. I also want to print the attack that we are getting. So one final test. I can attack a fire monster with a normal attack, and we are doing 20 damage. Whereas the opponent has used Nuke, which is doing 50 damage. And the multiplier is 1 because we are attacking fire with fire. Back in the game, I want to attack now with a splash attack, which is doing 60 damage overall. We went from 100 to 40. That is because splash does 30 damage, and we are attacking with water, and our target is fire. I think this is working pretty well. So with that, we have made the game interactive. Although this isn't terribly visible yet because we have no attack animations and no health to display. That we're going to do in the next section. So for the next section, we want to make the entire thing much more visual, which means we have a health bar and attack animations. The health bars are going to take a bit of math, but it's not too bad. The attack animations are also going to be a fairly basic animation. The one difficulty might be if you open the project folder. Under images, we have the attacks. And for each attack, we have one PNG file, which contains multiple graphics. Those we have to separate inside of pygame, which we can do, but it will take just a bit more logic. And start inside of the UI. In there, I want to add one more thing. Define, I call this one stats. As always, first of all, I want to have a background, which is going to be a rectangle via pygame.fRectangle, in which I want to have self.left, self.top, and for the dimensions, I want 250 along with 80 for width and height. After that, I can copy from switch the pygame.draw for the background and the border, like so. To see the result, inside of the draw method, I want to call self.stats. Let's try main.py, and there you can see one additional box. Although, if we're calling switch, this one is looking a bit weird. To fix that, inside of UI, I only want to call this method if self.state is different from switch. Let's try this again. And if I select switch, we cannot see the name of the monster anymore. That's working pretty well. After that, once we have the background, I want to get the actual data, which means I most importantly want to have a name surface. Self.font.render with self.monster.name. For anti-alias, I want this to be true, and for the colors, I want colors and black. Then we need a name underscore rectangle, which is the name surface, get f rectangle, in which I want to place the top left, for which I want to have the rect.top left plus pygame.vector2 for just a bit of an offset. For x, I want to have rect.width multiplied with 0.05. Which means when we are getting this background rectangle, we have 5% of the width as padding to the left side. For the top, I simply want to have 12 pixels. Also, I can see a typo. This should be monster.name. Finally, self.displaySurface.split with the name surface and the name rectangle. Let's try this one, and we are getting the monster name. Perfect. After that, I want to have the health bar, for which, first of all, I want to define a health rectangle. Pygame.fRectangle. And now I have to figure out some numbers that define the size and the position of the health bar. I want the left side to be aligned with the monster name, which means name rectangle.left. For the top, I want to have name rectangle.bottom plus a bit of padding, let's say 10. For the width, I want to have rect.width multiplied with 0.9, or 90% of the width of the entire background. For the height, finally, I want to have 20 pixels. Just to make sure we can see what's going on, pygame.draw.rectangle with self.display surface. Then I want to have colors and gray, and finally the health rectangle. If I now run main.py, we can see a rectangle for the health of the player. Doesn't do anything at the moment, but that's going to be the next part. I want to have self.draw_bar, for which I want to use a couple of arguments. The first one is the health rectangle for the size and the position. Besides that, I want to have self.monster.health for the current amount, and finally self.monster.max_health. This method doesn't exist at the moment, so we have to create it, draw bar, with self, a rectangle, a value, and a max value. And now we have to talk about the basic problem in here. At the moment, via the rectangle, we are getting some area that we want to use for the health bar. Let's say for simplicity, this thing has a width of 100 pixels. And let me add pixel in there just to be clear. The issue we now have for the player monster, let's say the current health is going to be 60 and the max health is going to be 100. How can we get the width of the bar from these two numbers? And for that, first of all, inside of the health bar, we have to know how many pixels do we get from one health point. That is a value we can calculate fairly easily. I'm going to call this ratio. I want to get rect.width and divide it by the max value. That way, in our example, if the width of the rectangle is 100 pixels and max health is also 100, then each pixel represents one health point. And all of that we are storing in the ratio variable. Via that value, we can create, I call this the progress rectangle, which is going to be another pygame.f rectangle, in which we want to get a top left position and a size via two tuples. The top left is simply going to be rect.topleft. For the size, I want to have a width and a height. The height is easy. We simply want to get rect.height. Or in other words, the height we're getting from the rectangle that we are passing in there as an argument. For the width, though, we want to get the value and multiply it with the ratio. And that is basically it. I can now call pygame.draw.rectangle on self.displaySurface with colors and red, and finally the progress rectangle. If I now run main.py, we are getting some health. And if I attack the opponent attacks us, we are losing health. I can do this multiple times, and we keep on losing health. That's looking pretty good. Next up, below the UI for the player, I want to have another class that I have called opponent UI. And there I want to duplicate what I have done inside of stats, meaning I want to display the opponent monster name and give them a health bar. This part is going to be your exercise. So create a UI for the opponent with the name and the health bar. Pause the video now and see how far you get. To get started, I want to define a dunder init method with self and a monster. Then we will need self.display_surface with pygame.display.getSurface. Afterwards, I want to have self.monster as the monster, and we will need self.font, which will be a pygame.font.font with none and 30. After that, I want to have a draw method in which we are defining a background via a rectangle pygame.frect. And for the position, I will go with 0 and 0 for now. You will see in just a second why. For the dimensions, I want to have 250 and 80. The same thing we have used for the player. Although we don't need the player UI anymore. After we have that, I want to, on this rectangle, use move to. That way, we can place the mid left right away. I want this value to be 500 for x, and for y, I want to have self.monster.rect.center y. After that, we can do the usual. I want to copy pygame.draw for the background and for the border. After we have that, inside of main.py, under UI, I want to create self.opponent UI, and the value is going to be opponent UI with self.opponent. Opponent UI is not available at the moment. That we can change by changing from UI import everything. With that, we are getting the opponent UI. To display it inside of the run method, I want to call self.opponent UI and then draw. With that, we're getting an area for the opponent. And if I run this a couple of times, we're getting a different position for this box every time, because it updates along with the opponent. That's looking good. You could make all of this static as well. It's entirely up to you. That part isn't really important for me. What I want to work on is a name surface, which we are getting via self.font.render with self.monster.name, true for anti-alias, and then colors and black. Next up, I want to have a name underscore rectangle with the name surface get f rectangle, in which I want to place the top left. And this is going to be very similar compared to what we have done for the player. rect.topleft plus pygame.vector2 with rect.width multiplied with 0.05 and 12. Finally, self.displaySurface.blit with the name surface and the name rectangle. Let's try this one, and we are getting the opponent name. That's a good sign. Next up, I want to work on the health. Once again, we want to create a health rectangle, which is going to be pygame.f rectangle with name rect.left, name rect.bottom plus 10, rect.width multiplied with 0.9 and 20. The very same numbers we have used for the player monster. After that, I want to calculate the ratio to figure out how much health is 1 pixel. Or in other words, I want to get the health rectangle dot width and divide it by self dot monster dot max underscore health. Once we have that, I can calculate the progress underscore rectangle, which will be a pygame f rectangle once again with health rectangle dot top left for the position, and for the size, I want to have self dot monster dot health multiplied with the ratio. That would be the width, and the height is going to be health rectangle dot height. And that is all we need. We can now draw a couple of things. Pygame.draw.rectangle with self.displaySurface, then colors gray, and a health rectangle for the background. Then duplicate all of this. We want to have a red color with the progress rectangle. That's all we need in here. And now I can attack the opponent, and the opponent loses health. The same happens to us, and this we can do multiple times. Looking pretty good. To make all of this more visible, I want to create an attack animation. For that, inside of the code, I want to create attack.py. This is going to be a very simple sprite. From settings, import everything, and then create a class attack animation sprite, which is going to be a pygame.sprite.sprite. Define dunder init with self, a target, frames, and groups. Next up, we want to have super dunder init with the groups and self.frames, self.frame underscore index with the arguments frames and 0. Once we have that, we can create self.image, which is going to be self.frames and then self.frame index. Self.rectangle is going to be self.image and get underscore f rectangle, in which I want to place the center at target.rect.center. We are simply creating an animated sprite. This we have seen a couple of times by now. After that, I want to have an update method with self and delta time. In there, I want to have self.frameIndex plus equal 5 times delta time. And for this animation, I want to check if self.frameIndex is smaller than length of self.frames. If that is the case, I want to update self.image and set it to self.frames index integer of self.frame index. And else, if that is not the case, we want to call the kill method to discard this sprite. That would be a very basic attack animation sprite. Now we have to figure out how to use it. For that, inside of main.py, I suppose we can start by importing it. From attack import attack animation sprite. After that, every time we are applying an attack, I don't want to print anything anymore. Instead, I want to create one instance of the attack animation sprite, for which we will need a target. That we already have. After that, we will need some frames. This part we don't have at the moment. The groups though we do have self.all_sprites. So how can we get the frames? And basically for that, inside of import assets, I want to create self.attack frames, which I want to import via a tile_importer, in which we have to specify the amount of columns, which in our case is going to be 4, and then the folder path, images, and attacks. This tile importer doesn't exist at the moment. We will work on that in just a second. First of all though, inside of attack animation sprite, I want to get self.attack frames and then pick one frame via the name of the attack. That would be all we need for this attack animation sprite. So now we have to figure out the tile importer method. This I want to create inside of support.py. Define tile importer with the amount of columns and then unpack the path. To get started in here, we will do a couple of familiar things. I want to have a dictionary called attack frames. No values at this point. Then for folder_path underscore and file names in walk, join, and the path. This is something we have seen multiple times at this point. After that, for file_name in file names. Then I want to create a full_path via the join method, folder path, and file name. Via that, we can create a surface, pygame.image.load with the full path and convert_alpha. But this we do not want to attach right away to the attack frames. Instead, what I want to do, inside of attack frames, I want to create a key value pair. The key is going to be filename.split, wherever we have a dot, and then pick the first entry. Or in other words, we get the file name without the file ending. The associated value for now is going to be an empty list. And what I want to do, if I open all of the attack animations, let's have a look at Scratch. All of this is one image, which isn't ideal for me. I want to separate this thing into 4 separate parts and then attach every individual bit to the attack frames list, the one we have just created. For that, first of all, we will need to know how wide the cutout width needs to be. And for that, I want to get the full width of the surface. So surf and get width. This we want to divide by the amount of columns that we have. So by default, Pygame doesn't know how many images we have on this one PNG file. This we have to specify ourselves. And in my case, it's always going to be 4, which is why I added 4 in there. After that, I want for column in calls, and this calls needs to be inside of a range function. What we want to do in here is essentially create a cutout surface, which is going to be a very simple pygame.surface with the cutout width for the width, and then surface get underscore height. And don't forget to call this one. On this cutout surface, I want to blit the part that we have cut out from the original. The trick for that is we want to get the original surface and then position 0 and 0. And finally, we can specify another argument, which is going to be the area that we want to blit, which needs to be a rectangle. Or in other words, I want to get a cutout rectangle, which does not exist at the moment. To create it, cutout underscore rectangle, I want to have pygame.frect with the left side, the top side, the width, and the height. The width and the height are the really easy part. We want to have the cutout width, and for the height, we simply want to get what we have already used, surface and get height. For the top, this part is even easier. It's always going to be 0. Finally, for the left side, I want to get the cutout width and multiply it with the column. If this is the entire surface that we have imported, this one here, and we have 4 columns, this value would give us, first of all, this side, and this would happen on the first for loop. Then on the next loop, we are going here, then we are going here, then we are going here, and then we are done. And with that, we have a cutout rectangle. This we then want to attach to the list we have created earlier. For that, I can copy the name of the key that we want to use and then append the cutout surface. Nearly done with all of this. We simply want to return the attack frames, and then inside of main.py, we should not be getting an error message anymore. On top of that, if I now attack the opponent, we are getting an error, and the key error is spiral. That means when we are picking from the attack frames, there's no spiral file in there, which you can double check inside of the attacks. There's no spiral in there. That is because there's one thing I forgot. If you look at settings, there we have the abilities, and each ability has an animation. This is the actual name of the file that we want to import. Or in other words, we are already getting the attack data. From this, we want to get the animation. If I now run all of this and I attack, we are getting animations. This also works with different ones. So that is looking pretty good. Although, obviously, we have to get rid of the black stuff around them. All we need for that, when we are creating the cutout surface on this line, we want to set a custom flag, pygame.src alpha. That way, all of this is looking significantly better. And we are getting our attack animations. Nearly done with this part. There's just one more thing I forgot in the last part. When the player is getting input from the UI, at the moment, we only have attack and escape. Besides that though, another simple thing is elif state is equal to health. Or rather, this should be heal. If that is the case, I want to get self.monster.health and increase it by 50. Besides that, I want to create an attack animation sprite on self.monster. For the frames, I want to have the attack frames with the key green. You could make this more flexible, but for the healing effect, I always want to use the same animation, so this can stay constant. Finally, for the groups, self.allsprites. With that, I can heal, and the monster, well, we are definitely healing, but this is kind of strange. To fix that part, we can do something fancy. Inside of the monster, when we are updating the health, I always want to make sure that we are never exceeding the maximum health. And for that, we can use a property getter and a property setter. The way that is going to work, first of all, I want to turn health into a private attribute, which we can do by adding a single underscore. And afterwards, I want to have a decorator called property, below which we are going to create a health method with self and nothing else. And this is simply going to return self._health. With that system, we are storing the actual information inside of _health. But whenever from outside of the class we want to read health, we are calling this method instead. That way, by default, the game is still going to work just fine. Although if I try to attack, then we get property health of opponent object has no setter. That we can fix inside of the monster by adding a property setter. This we get via health.setter. And then once again create a health method with self, and this one is going to need a value. Basically now, whenever we are trying to update health, we are calling this method and adding the new value inside there as an argument, which means we are capturing the new value via the value parameter. And then, when we are updating self._health, I want to limit this to never go below 0 and never exceed the max health, which we can do, first of all, via the min function, which always picks the lower of two values. In there, I want to get the max health, and I want to get the value. So if I now run all of this again, I can heal, the monster does heal, but we never go beyond the maximum health. Looking pretty good. Besides that, when we are setting the value, I want to wrap this inside of a max function, which is going to pick the larger of two values. And in my case, I want to get 0 and the value. That way, this value can never become negative. And that is basically it. With that, we have a property getter and a property setter that ensures that the health of the monster never exceeds the maximum health, which is a really nice functionality. So for example, when you're calling something like monster health plus 50, you don't want to have to worry about the maximum or the minimum health. This part should be abstracted away, which is something you see very often with this kind of system. We are nearly done with the game. There are just a few more minor bits that we have to add. Most importantly, we need to be able to switch monsters and to defeat monsters. Then we can add some sound files, and then we are pretty much good to go. To get started with switching the monster, I want to work inside of getInput, and then check if elif state is equal to switch. That is only going to be the case if we are getting UI and input switch. In there, we are passing in self.state along with the available monster. If that is the case, I want to call self.monster and kill it. After that, self.monster is going to be data, or in other words, whatever we are getting from the UI, which is also going to be a monster. Next up, self.allsprites.add self.monster. After that, we have to update the UI, which means self.ui.monster is going to be self.monster. That is basically all we need. If I now switch to, let's say, Jacana, we're getting Jacana and we have another monster. Although if I go back to switch, we still have Jacana inside of the switch menu. This shouldn't be the case. To fix that, inside of UI, I want to work in the update method and then keep on updating the available monsters via list comprehension, monster for monster in self.playerMonsters if monster is different from self.monster and monster.health is greater than 0. That way we account for the currently active monster and for monsters being defeated. Let's try all of this again, and I can now switch to, let's say, Golfin, That looks good. And if I switch again, we are getting Sparchu. That's perfect. Now you could make this functionality just a bit more elegant. For example, by updating the available monsters every time monster health changes, or with switching a monster. If your framerate dips too low, this is something you might want to do. But in our case, performance isn't that much of an issue, so I'm not going to worry too much. After that, inside of main.py, I want to detect if a monster has been defeated. I suppose for that, we can start inside of the opponent turn. Every time it's the opponent turn, I want to check if self.opponent.health is smaller or equal to 0. If that is the case, I want to do something, but pass for now. If that is not the case, else I want to do the stuff we have already done. If the monster is, however, defeated, then I want to set self.playerActive to true. Besides that, self.opponent.kill, and then I want to get a new monster, which I want to store as monster_name, and get that via choice, list, monster data, and keys. That way, we're getting a random monster name. Via that, I want to create a new opponent. With the monster name, then we will need surfaces, which we can get via self.frontSurfs, and the monster name once again. Finally, for the groups, self.allSprites. After all of that, self.opponentUI.monster is going to be self.opponent. That's basically all we need. If I now run all of this, I can attack this monster with a fire attack, it disappears, and we're getting another monster. Although, if you paid close attention, you have seen something else. Let me pick another attack and pay close attention to what's happening on the screen. We're getting a shadow right below the attack, and something else went wrong as well. Step by step. First of all, when we are drawing all of the floors, that happens inside of Draw Monster Floor. In there, we are drawing a floor below all of the sprites, which worked so far, but now we also have attack sprites, which shouldn't have a floor. To account for that, I want to add another instance. If is instance, I want to check the sprite, and then check if it is from monster a creature. So in there, I want to have creature, which I believe we have to import. From monster, I want to import everything. Only if that is the case, do we want to draw a floor. Let's try all of this again. And now, if I attack, we can only see a floor below the monsters. That's looking pretty good. So next up, after we are defeating an opponent once, it disappears, and that's looking pretty good. Although the UI doesn't update. Something is going wrong here. The issue is, we are creating a new opponent, but we are not overwriting self.opponent. Once we are doing that, things should be working. If I now attack the opponent with a fire attack, it disappears, and we are getting another opponent. If I defeat this one with splash, we are getting yet another opponent. And this I can keep on doing forever. That's looking pretty good. And there's one thing I so far haven't covered. The kill method doesn't actually destroy the sprite. Instead, it simply removes it from any group, which in practice means you cannot see it anymore and it won't be updated. But the sprite is still there, which sometimes can be a bit confusing. But once you understand how it works, it's quite manageable. Anyway, with that, we have the opponent turn. Next up, the player turn. If the monster is defeated, so if defeated, then we want to have the next monster. Or in other words, if Sparchu is defeated, then we want to get the next monster with health, which might be Cleave. And then if no monsters, we end the game. Implementing this part will be your exercise. So change monsters if the current one is defeated, and end the game if all monsters are defeated. I want to check if self.monster.health is smaller or equal to 0. If that is the case, I want to get all of the available monsters, for which I can use list comprehension once again. Monster for monster in self.player monsters. But only if monster.health is greater or equal to 0. Then I want to check if there are available monsters in the first place. If that is the case, I want to kill the current monster, self.monster.kill, and then create a new monster with the first item from the available ones. After that, self.allsprites.add with self.monster. Finally, we have to update the UI. In there, I want to get the monster with self.monster. Let's try all of this. And I want to attack the opponent with Spiral. That's not going to do very much damage. And the monster gets defeated. And nothing is happening. And that is because this if statement should only check if health is greater than 0. If I now try all of this again, and let me just attack the monsters and hope I don't kill them too fast. We got defeated, and now we have another monster. Perfect. You might be wondering at this point, why for this list comprehension don't we have to check if we have the current monster, like we have done in UI for the available monsters. And there, we are checking if the monster is equal to the current monster. This we don't need, because this is only going to run if the current monster has been defeated, meaning it's going to disappear anyway. Besides that, if we don't have any more available monsters, then we simply want to set self.running to false. That covers everything, so next up, for the player, I only want to have 2 monsters. Let's try all of this now, and let's hope I don't defeat the opponents too fast. That was a good attack. That was too strong. That one doesn't do any damage. Okay, that's 1 monster gone. And next up, I should choose weaker attacks. This one doesn't do any damage. And now the game is over. Perfect. Although there's one issue I did realize. If we only have a single monster. So let's hope I get defeated quickly. There we go. If I only have a single monster and I go to switch, we are getting integer modulo by 0, which happens inside of the input. Inside of switch, we are doing modulus and then the length of the available monsters, which is a value that can become 0. And doing modulus 0 is going to get you, well, something really strange. To avoid that case, we simply want to check if self.available monsters. Only if that is the case, do we want to allow any input in there. With that, I can only have a single monster, run the game, and inside of switch, nothing is going to happen. And with that, we have basically the entire game. The last thing that we have to add are the sound effects, which we can already import quite easily under import assets. I want to add self.audio, for which we have inside of support audio importer. This I want to use, audio importer, and then go to audio, the same folder that we have already seen a couple of times. In there, we have a whole bunch of attack sounds and background music. That's all we need. To play those, I want to look at apply attack and then get self.audio, and then we need the file name. If you look at those files, you can see that we have the same name that we are getting from the animation from each of the attack. For example, we have scratch, fire, explosion, which means inside of audio, I simply want to get the attack data, and then once again, the animation. And this I want to play. We should be getting sound effects. That is working quite well. Perfect. The last thing then, we have to start playing the music, which I suppose we can do inside of dunder init. After we are importing all the assets, I want self.audio with music and play the entire thing. As an argument in there, I want to have -1, so this one plays forever. Perfect. That is working really well. Just one more thing that I forgot. When the player gets healed, we are also getting the attack animation, which means in there, I also want to get self.audio with the green animation sound and play that one. With that, inside of the game, we are getting a sound effect. Perfect. And that finishes up the entire game. So I hope all of this was useful, and thanks for watching.